क्यों गया?
क्या हो रहा है बार-बार? मुझे लग रहा है स्लीप पे तो नहीं जा रहा है बार-बार।
नहीं, स्लिप पे तो नहीं जाना चाहिए।
हाँ वो हो जाना नहीं चाहिए।
तो हाँ मतलब ऐसा नहीं कि जाएगा
बैटरी से डिस्प्ले सेटिंग्स
100%।
सर यहाँ स्लीप ही सर्च कर लेंगे ऊपर जल्दी मिल जाएगा।
कहाँ है?
सर्च
स्लीप,
कर लेते हैं।
पावर एंड स्लीप, ऑन बैटरी व्हेन प्लग्ड इन, नेवर,
हाँ तभी ये दिक्कत आ रही है सर।
नेवर नेवर।
नेवर
और बैटरी को
नहीं
भी
नेवर।
नेवर।
अब ठीक है सर। ये नीचे भी आ रहा है सर स्क्रीन।
ये है स्क्रीन, अच्छा, और ये है
इसको भी कर
स्लीप।
दो सर नेवर, सब नेवर।
ठीक है,
तो बस
अब
अभी
नहीं होगा।
एक लैपटॉप का इशू है, दो जगह सॉर्टेड है हमारा।
दो जगह सॉर्टेड है, एक जगह इशू है बस।
ठीक है।
ठीक है मैम, डन। APJ 4 का बस बचा है।
रखना। A very good morning to all the dignitaries, invited speakers, guests, delegates, participants, and all the members of NSUT. It gives me an immense pleasure to extend you a warm welcome on behalf of the organizing committee to the International Conference on Advanced Materials for Emerging Technologies, ICAMET-23. The objective of this conference is to provide a common platform for all the researchers from India and abroad to discuss and share their ideas and research achievements related to advanced materials and their applications for emerging technologies. I now request all the dignitaries, our chief guest, Professor Venugopal Lachanta, guest of honor, Professor A.C. Pandey, Honorable Vice Chancellor, Professor J.P. Saini, due to some avoidable reasons, he could not join us today. So in his absence, Professor K.P.S. Rana is here to grace the event. Then Dean of Faculty of Sciences, Professor Sanjeev Thakur, and I request Professor Ranjana Jha and Dr. Anurag Gaur to accompany our chief guest and guest of honor and other members. Now I welcome Honorable Chief Guest, Professor Venugopal Lachanta, the Director of CSIR, National Physical Laboratory, Delhi, and request Dr. Vinod Kumar to come forward and present him flowers. Thank you, sir. Now I welcome guest of honor, Professor A.C. Pandey, the Director of IUAC, New Delhi. He's on the way. Yeah. Now I welcome Honorable Vice Chancellor, Sir, Professor K.P.S. Rana, and request Dr. Amit to present him flowers. Thank you, Dr. Amit. Now I welcome Dean of Faculty of Sciences, Professor Sanjeev Thakur, and request Dr. Parkin to present him flowers. Thank you, Dr. Parkin. All the participants are requested to take their seats faster.
रिपीट करा देना, फोटो नहीं हुआ था तो
इनका
चीफ गेस्ट का आना सकता है।
फोटो नहीं हुआ है। Now I welcome the conference chair, Professor Ranjana Jha, and request Dr. Leena to present ma'am flowers. Ranjana ma'am. Thanks, Dr. Leena. Now I welcome Dr. Anurag Gaur, the convener of this conference, and request Dr. Jugal Bori to present him flowers. We will wait for some time for Professor A.C. Pandey. Or should we go ahead? Yeah. Now I request all the dignitaries to come forward and light the lamp before Ma Saraswati for her blessings.
सर लैपटॉप का यहाँ रहना बहुत ज़रूरी है। मैम इसको हिलाइएगा मत।
ठीक है।
खराब हो गया, हमारे पास और नहीं है।
ठीक है।
प्लीज़ कवर होगा। बैनर चलाना है।
ठीक है। उसमें ऐड आ जाएगा।
छोड़िए मैम, बैनर।
इसकी लैपटॉप में सेटिंग रखनी थी। देखो।
दो लैपटॉप खराब हो चुके हैं यहाँ पे।
मैम 2 लैपटॉप खराब हो चुके हैं।
मैम पता नहीं क्या प्रॉब्लम होती है, यहाँ लगा के खराब हो जा रहा है। या तो अर्थिंग की प्रॉब्लम है या कुछ और प्रॉब्लम है।
सुबह से बज रहा था। Thank you, dignitaries. Now I request Honorable VC Sir Professor KPS Rana to felicitate Chief Guest Professor Venugopala Chanta by a shawl and memento.
उनका करा देना। एक बार बोल दो कि वेलकम प्रोफेसर A.K. Pandey to join us. फेलिसिटेशन करा था।
We have our guest of honor here joined us, Professor A.C. Pandey. I welcome Professor A.C. Pandey to the conference and request Dr. Amit to present him flowers. Now I request Professor Sanjeev Thakur sir to felicitate guest of honor Professor A.C. Pandey with a shawl and a memento. Now I request Professor Ranjana Jha to felicitate Honorable Vice Chancellor today, Professor K.P.S. Rana, with a memento. Now I request Dr. Anurag Gaur to felicitate Professor Sanjeev Thakur sir with a memento. Now I request Dr. Jehovah to come forward to felicitate Dr. Anurag Gaur with a memento. Now I request Dr. Vinamrita to felicitate Professor Ranjana Jha ma'am with a memento. Thank you, Dr. Vinamrita. Now I invite Professor Sanjeev Thakur sir to deliver the welcome address to the audience.
Thank you. Honorable dignitaries sitting on the dais, guest of honor Professor Avinash Pandey, Chief Guest Professor Venugopal, officiating Vice Chancellor Professor K.P.S. Rana. He is the Dean of all the faculties of engineering also. Conference Chair Professor Ranjana Jha, Convener Dr. Anurag, Organizing Committee consisting of all the faculties of Department of Physics and many of the faculties of Chemistry and Maths. That's what I guess. Dr. Nancy belongs to Department of Chemistry, so I'm assuming that all of them are part of organizing committee. Pleasure to welcome you all in the inauguration of ICAMET-23 in the premises of NSUT. As you know, that NSUT has come a long way from Delhi Institute of Technology to Netaji Subhas Institute of Technology, and to finally Netaji Subhas University of Technology in September 2018. After becoming a university, the growth of the institution has been exemplary in terms of infrastructure, number of students, faculty, staff, placement, expansion, and overall development. We now have 2 more campuses, east and the west, and this is the main campus where we are sitting at the moment. This is the main campus. And our founder, Vice Chancellor, is Professor J.P. Saini, who is an inspiration to all of us. Under his visionary leadership, our university has progressed by leaps and bounds, and it is rated amongst one of the best in the country. And the ranking spells it out that where we stand today, it's an exponential growth. We have started from under 100 intake in 1988, and now we are ending up admitting around 3,500 students. I'm talking of the BTech admissions only. So we have come too far, and now we have a good rating, of course. Professor Ranjana Jha is the conference chair. She's a dynamic person who is heading the Department of Physics, and in fact, she's a source of inspiration for the Faculty of Science because she has taken up so many things simultaneously. I still remember that the master's courses, it was her initiative. I was not in favor, though I should admit. It has started, and now it has started with a bang, I should admit. So thanks a lot, and I congratulate Madam for all her efforts, due to which this conference has been made possible. And it is a very heartening, on a heartening note, I should admit that this is a very successful beginning, another feather in the cap of the faculty and the university. And many eminent speakers of international repute, they all are participating, either physically or in online mode as well. So in true sense, I will admit that this conference is of international standard. And the dignitaries who are all sitting over here, you can see the stature of all of them. So once again, I welcome you all present here and those who are connected online. Welcome you all, and I hope, sincerely hope, that you all will enjoy to the maximum and benefit quite a lot, and the academic interaction is going to be fruitful. Thank you.
Thank you, sir. Now I invite Conference Chair Professor Ranjana Jha to give a brief introduction about this conference.
Good morning, everyone. I, Professor Ranjana Jha, wholeheartedly welcome Chief Guest Professor Venugopal Achanta, Director, National Physical Laboratory, Professor Avinash Pandey, Guest of Honor, Director, IUAC, New Delhi, Honorable Vice Chancellor for today, Professor KPS Rana, Professor Sanjeev Thakur, Dean and Registrar, all the deans, HODs, faculty members, honorable guests, and all the participants to the first international conference, ICAMET-23, organized by the Department of Physics, Nsut. It is a pleasure to see so many young, brilliant minds come together in the pursuit of advancing and understanding the application of materials. Netaji Subhas University of Technology, consistently ranked as one of the top engineering institutes in India, provides education and research in branches of engineering and technology science, humanities, social sciences, and management. The Department of Physics, Netaji Subhas University of Technology, was established in the year 1983, was catering to the requirement of BTech students under the stream of School of Applied Sciences. Now it has grown many folds, and I feel immense pleasure in informing that now we offer UG as well as MSc and PhD programs in physics. A number of research scholars have been awarded PhD degree in physics. As we all know, materials are the foundation of almost everything, including the most pressing issue of global warming and climate change. The study of nanotechnology and material science is essential in developing new technologies that can improve our lives. Over the next 3 days, you will have the opportunity to explore a wide range of topics like functional nanomaterials, synthesis and characterization, optical, electronic, magnetic energy materials, smart materials, carbon-based materials, hydrogen and biomass energy, green energy, and environment. These topics are of great importance and relevant to global objectives of developing self-sustaining technologies. The thematic thrust of this conference is of global concern, which requires cooperative introspection, collaborations across the boundaries, and profound deliberations of cutting-edge research. It is our privilege to host the world's renowned scientists, faculties, academicians, and research scholars who have kindly consented to actively participate in ICAMET-23 at NSUT through presentations and interactions, plenary, keynote, invited talks, oral and poster presentations by eminent academicians and young researchers will deliberate on the recent developments in the field of material science. Among the fellow scientists working in this particular domain, we have an exciting program lined up that will challenge everyone's thinking and inspire the delegate to achieve the new heights of creativity. I would like to share that we have received the overwhelming response for this conference and received more than 300 abstracts from India and abroad for presentations. After review, the publication committee selected 213 papers to be presented in online and offline mode through oral and poster presentations. During 3 days proceedings of the conference, there will be 24 technical sessions having 3 plenary, 27 invited, 102 oral, and 111 poster presentations. The presented papers will be reviewed and will be sent for the publication in SCI Journal, that is Indian Journal of Engineering and Material Science, in December 2023 issue. May God bless us all to make this event an extraordinary, enlightening, enjoyable experience. Once again, I thank one and all. Thank you so much.
Thank you, ma'am, for letting the audience know about the conference, and I'm sure the audience is excited to gain knowledge in the mentioned areas of research, and I hope all the researchers, and especially the younger ones, will have more awareness about the materials after attending this conference. Now we have chief guest of the conference, Professor Venugopal Achanta. Professor Venugopal Achanta obtained his MSc from Central University of Hyderabad and PhD in physics from TFR Mumbai, again PhD in electronics from Tokyo University. He is currently the director of CSIR National Physical Laboratory, Delhi. He is currently on leave from Tata Institute of Fundamental Research, Mumbai, where he is a professor. His research interests are in the application of nanophotonics to single photon metrology. He has over 135 journal publications. He is a fellow Indian National Science Academy and honorary fellow of Meteorology Society of India. He is on the International Committee for Weights and Measures, CIPM. He is also on the Asia Pacific Metrology Program, APMP, and Optical Society of India as an executive committee member. He is a vice chair of IEEE Photonics Mumbai chapter and a member of the Asia Pacific Physics Conference's Condensed Matter Physics section. Sir has a long list of achievements and very exciting research interest, and now I request him to show some glimpses of his research and deliver his talk on materials and processes for circular economy efforts which are happening at CSIR NPL currently, and address the audience. Thank you, sir.
It is copied on the other. Maybe the talks. You copied on a different
Is it
laptop,
green
I think
energy?
Yeah, okay, that's. Great, thank you. Thank you, Professor Pandey, Professor Rana, Professor Thakur, and Professor Ma'am, Ranjana Ma'am, and Professor Anurag. So thank you for giving me an opportunity. And I feel it's very interesting because as chief guest, I've been given a chance to talk about science. So I'm happy about it rather than talking something general. But as coming from NPL, like I thought I'll cover some of the activities which we do at NPL and then show some of my own research under the broad topic of advanced materials for futuristic applications. Right. So what is NPL? Most of you know, just for the sake of younger colleagues who are here, in the world, the quality infrastructure, so when we go to a shop, whether we are buying 1 kg of something or 1 meter of something, is it really the right quantity and right quality? So that is decided by a complete network or infrastructure which is globally in place. Right. So when we go to a shopkeeper, is he using the right 1 kg or 100 gram material or not? So that starts right from, in every country there is a National Metrology Institute. For India, NPL is the National Metrology Institute. And we also heard about this Bureau of Indian Standards, which sets up the standards on paper. So the Indian standards, IS standards are there. So NPL works closely with BIS in setting up these standards, and then those standards are established, experimental facilities are set up, and these are called the national standards or the primary standards which are at NPL. And then these are made available through a chain of traceability through these, for example, NABL accredited laboratories or legal metrology laboratories across the country. Right. So just to show, this is the metrological traceability chain, NPL being the National Metrology Institute. We set up the national standards and make them available down the line, as I mentioned, to the shopkeeper level, to the labs. Whatever equipment we are using, whether it is giving the right value or not, has to be traceable back to the facilities which are at NPL. Now, this is all for within the country, but what happens is we are also importing and we are also exporting. Our government has grand vision of expanding our economy to 5 trillion economy and beyond in the next few years. So how do we achieve, how do we make our exports acceptable? So for that, we act as a bridge with the international community. So the NPL water facilities we set up, these are actually compared with the rest of the world through intercomparison. So we send, or one of the pilot labs, one of the NMIs, National Metrology Institutes, they act as a pilot lab. So you want to measure 1 volt, for example. So there is a sample which is sent across from country to country, and every country measures and puts up. So I'm measuring a value of this much. Nobody knows what is the actual value of the sample. So it's a blind sample, so we measure each of them and the value and the uncertainty with which we are measuring it. So once all the countries measure it, so we plot it, the intercomparison plot, and then that tells us, the pilot lab knows the actual value of the sample, so we know what is the exact value which we are measuring, what is our capability as a national capability for this particular measurement. So this takes 3 to 5 years, and at the end of it, we know what is our capability. So we call it CMC, the calibration and measurement capability for the country. Right. So we set these things, and these are all acceptable. When we measure, when we say we have a CMC for 1 volt, and we measure 1 volt with this much of uncertainty, that is accepted anywhere in the world. No questions asked. A certificate given at NPL saying that this is the value that is accepted rest of the world. Right? So this is how NPL acts as a bridge to the international community as well as to the quality infrastructure within the country. In addition to metrology, we also have very strong groups in material science and environmental sciences. For example, not many would know, but NPL scientists participated in every single Antarctica mission happened so far. Right. In fact, one of the scientists from NPL was in charge of the Maitri station when it was built at Antarctica. Right. So, towards circular economy, we do work together, metrology, material science, and environmental sciences all together. So we look at green energy, quality of life. For example, for improving the quality of life, as I mentioned, we set up these standards. Then we also look at advanced or futuristic facilities. For example, this is the phasor measurement units, the PMU for electrical grids. I'll show a little later. And green energy, traditionally solar cells, photovoltaics, all generations are made at NPL, and also the standards for that are being set. Carbon composites is another material aspect which we look at. I'll show the results on this, including waste recycling. When we talk about circular economy, the idea is that we reduce the waste. We take the raw material and move from the brain set of, okay, we are making some electronic components, electronic device. We use it for 2-3 years and then it just dumped. Nobody bothers about what is happening to that. But in a circular economy, what we look at is how to reuse those components again, how to reuse those materials, and the waste is minimized so that we are not continue to be a burden on the nature and the natural resources which we are continuously mining. Right. So as I mentioned, so we are working on this national primary standard facility for solar cell calibrations. So this is needed because we have the push in the country to make these solar cells and solar panels within the country. So we are setting up these things. So the idea is to have the best facility in the country. So right now, PTB Germany has 0.4% uncertainty in the values. This is the STC current. So India facility, which is going to come up in the next few months, is expected to have 0.35% uncertainty values. Right. So you're also looking at measurement and monitoring of energy. So if you're looking at the futuristic grids, so what we need to save is the voltage, current, the phase, and time, so that the grid failures, there is always, we're talking about modern warfare. In the modern warfare, we're also attack the enemy's electrical grids and every other. So how do we make sure that we protect our grids? How do we make sure that there are no untoward incidents, there are no attacks on our grid? So how do we do that is have an entire grid is mapped into finer points. At each location, we measure all the 4 of these parameters. For example, as I mentioned, the voltage, current, frequency, and phase. And this is the phasor measurement unit is what helps the electrical distribution companies to store these values. So we have set up this calibration measurement facility for these PMU units, and we are actually already providing these services to the industry so that our grids are, smart grids are available across. Right. So for materials development, we do a lot of semiconductor processing. So this is, for example, silicon photovoltaics. NPL has worked on every single generation, starting from silicon to the most recent perovskite solar cells as well. Right. So one of the ways to enhance these enhance the solar cell capabilities is to reduce the reflection. So you make sure that as much solar energy is passing into your device, so that like you have maximum conversion efficiency from light to the electronic charge separation, right? So we prepared these black silicon solar cells with the reflectance less than 2%, so and demonstrated about 18% efficiency in these. So these are different generations of solar cells which we have demonstrated at the lab scale. So for example, perovskite solar cells, we have about 13.3%. PV materials, perovskite and organic. So we developed these, for example, in organic solar cells, the charge transport layers are very, very important. So you need to have these, the band lineups to be lined up so that you have the P and N layers, those band lineups, and this in between charge transport layer. You need to make sure that there is sufficient or efficient transfer of this charge, and also high mobility within these, so that you'll have efficient transfer of charge through these layers. So we have indigenously developed, these are import substitute materials which cost about 1/10 of the import values for these. So these are commercially available now within the country. So these 9% efficiency for organic solar cells, and we also look at low-cost heterojunction solar cells. So typically of the order of like 13% is the average solar cell efficiencies which we have routinely getting for different generations of solar cells. So this is for perovskite based. We need to go to large scale or mass production of these. So towards this, we developed a printer. This is a 3D printer, completely in-house made. So we make these A4 size perovskite based solar cells now, and the efficiencies which we get is about, again, 13% or so. These are, this is polymer electrolytes, are also called the proton exchange membrane fuel cells. Here, for example, hydrogen, you're using hydrogen splitting as your energy source. These PEM membranes are very important because they help in basically separating out your anode and cathode regions, as well as transport of the charge across these layers. So we use these carbon composite materials. For example, this one on a graphite-based one, so which we prepared these layers, and then we tested it. This is again on carbon nanotube, platinum ink. One of the problems with this PEM is platinum is very expensive, so we need to look at alternatives or substitutes for platinum. That's where we are looking at these carbon composites, and we also look at carbon nanotubes. Then I'm just looking for a, so this is tin oxide multi-wall carbon nanotube based composite paper. Then we do these electrochemical studies. We work with our sister lab, SECRI, in Karaikudi. This is a CSAR lab where we actually put these materials inside lithium-ion cells, and for converting or transferring the technology to the industry. So these are carbon composites for supercapacitors. We also look at, as I mentioned, one of the major areas with us is waste recycling. So can we use agricultural waste, for example, pineapple peel, or agricultural waste like the paddy or wheat waste. So these are all like how we can convert it into carbon-based materials and then use them for these green energy applications. So this is one example for a supercapacitor. So this is patented, and these are again biopolymers. These biopolymer-based carbon nanofibers, which are converted into flexible sheets for again supercapacitor application here. So it's again, so far all the pigments, when you talk about our currency notes or passports or in stamp papers, so the security features are all, the inks or pigments which are used, they are all imported right now. So we first time made industry scale far superior than what is available commercially. So these are with quantum efficiencies greater than 60%. What we have commercially are of the order of like 10%, but the ones which are making are of the order of like 50% and more quantum efficiencies in emission. So you shine light, UV light, and then you look at different colors. So we also made special pigments where depending on the wavelength of the UV light, you can get red or green or blue emission from your pigments. So these are transferred, the technology has been transferred to private industry. The way we work is we have a tripartite agreement between the mint, government mint, which tells us which pigments are needed for the next generation currency notes. We make those pigments and then give the know-how to the local industry. So the Indian industry is ready to manufacture these. So we are hoping that this will be the import substitute for the next currency notes which we may see in the country. Right. Just coming to my own activity, I work on metamaterials and nanophotonics. So I cover optical, near-infrared, and terahertz regions. I have activities both in physics as well as applications. In physics, it's just looking at how these plasmon modes, I'll explain a little later like what plasmon modes are, how these plasmon modes interact with electrons, how they interact with excitons in semiconductors, and how we can control the optical properties of materials or the plasmon dynamics themselves. For example, if you want to have ultra-fast switches or something, then we can use these things. So from physics perspective, we look at these dynamics and how they can be used for different applications. For example, for application point of view, we looked at an on-chip Yagi-Uda antenna. This is for 5G or 6G networks, which are coming up. So we made this transceiver antenna for this. Then we have this switchable metamaterial, which we showed stealth application with this, and single photon application, single molecule detection. So I'll show some of these examples in the next few slides. So the basic idea behind this nanophotonics is to make use of these so-called surface plasmon polar return modes. If you have a metal and a dielectric is an insulator. So what happens is the large number of free electrons on the surface of the metal, you can excite them as a charge density wave which propagates along the interface. Right? So we solve these Maxwell's equations with boundary conditions and derive for the Snell's law. This is our standard textbook. But what we generally do not see in school or college is there a solution which propagates along this interface? So this is what we look for, and it turns out that if you have a metal and a dielectric, epsilon negative and an epsilon positive materials, and they form at the interface, under certain conditions you can excite a charge density wave which propagates along the x direction, along this interface. Right? You have less number of electrons, relatively positive charge, more number of electrons, relatively negative charge, and so this wave propagates along the interface. So this is a surface mode, which means that if you're moving away from the interface, so the field exponentially decays. Because of the small skin depth within the metal, the penetration is weaker or shorter, and it decays much faster than in the insulator. But the idea here is you are confining the electromagnetic radiation to within few nanometers to of the order of like 10 nanometer distance within the interface. Now when you're confining your field to this very small sub-wavelength features, you're beating the diffraction limit, you're having very strong local fields which can be used for nonlinear optical applications, and you can basically change the material properties themselves. So that's what we use them for. But one of the challenges is, if you look at the third plot here, so this is the light line. This is the dispersion plot, omega versus k is the dispersion. Right? So omega equal to ck is the dispersion relation for the light or photons. And compared to that, the dispersion relation for this charge density wave, the surface plasmon polar return mode, is given by this solid line, right? Given by this expression here, which depends on the epsilon 1, epsilon 2, which are the dielectric constants of your metal and the dielectric. Now, what is the problem? The challenge is that if you are using light of certain frequency or wavelength, color, then the omega is fixed. But then if you look at the k, the momentum axis, there is a mismatch in momentum. So the momentum is not conserved. So for directly shining light, you cannot excite this charge density wave on an unpatterned metal surface. Okay. So people do patterning of these metal surfaces so that you can get this additional momentum for your photon, so that you can excite a charge density wave which satisfies the energy momentum conservation properties. So I'll just show you one simple thing, just a catchy one. This is called the goose ancient shift. Sorry, the spelling should have been goose, not double S, it's double O. The goose and Hanshin, way back in 1947, they found that when light is incident on a surface, we consider that the light is incident and then gets reflected from the point of incidence. But in reality, it doesn't happen. There is always a shift in the centroid of the beam. So we ignore this small shift in the beam position because the shifts are of the order of like lambda by 10. So if you're taking blue light or red light, for example, 600 nanometer, so the shift is of the order of like 60 nanometer. So for practical applications, it really doesn't matter, so we don't consider this. But in reality, it does shift, and they have measured these shifts, and it's named after them. So just to understand the origin of this is like if you take, if you consider a beam is incident and at an angle, so you consider that this beam is a collection of plane waves. Right? So, and if you look at the beam profile, the electromagnetic field intensity, and then the profile of this beam, you see a sine square x by x square kind of profile here, right? So, but if from one edge to the other edge of the beam, if there is a shift in the phase, for example, if you're launching a circular spot on a surface, it remains circular. But if it is coming at an angle, it no longer is circular, but on the surface there is a slight elongation, it becomes elliptical in shape. So from one edge to the other edge, you do have some phase difference, and thus that phase, if you look at the interference pattern, so it's as if like the beam centroid of the beam is shifted. So it's coming because of this phase accumulation from one edge of the beam to the other edge. So we wanted to show, so we do quite a bit of instrumentation in my lab at TAFR, also started at NPL. So we set up this direct measurement of these shifts, and we could show that we can measure with 50 nanometer uncertainty, or shifts, direct shifts with 50 nanometer precision, we can measure them. The trick which we do is we take a beam, we make it into circularly polarized, then we take the two orthogonal linearly polarized components and modulate them at two different frequencies, F1 and F2, and then launch them together back into a polarization maintaining fiber so that the mode purity is maintained, and then collimate it onto a sample. Now my S-polarized light, which is modulated at F2, and the vertically polarized light is at F1. The vertically polarized light is coupled, the TM polarized light or a P polarized light is coupled to the plasmon mode, and the S polarized light is my reference. So what we did is just by, instead of measuring one single measurement, we moved this quadrant photodiode across the beam position, because of which we have multiple points corresponding to, in a quadrant photodiode, the way we do is you have 4 photodiodes, and then depending on how much or what fraction of the light beam is falling on each of those photodiodes, you can calculate A plus B minus C plus D. So you can calculate like where the position, the beam is positioned on your quadrant photodiode. So here by scanning this quadrant photodiode across the beam, so we could get different positions. The problem is if you have A plus B minus C plus D is limited by what is the minimum signal which you can measure, or what is the dark current or dark voltage which you are getting out of your quadrant photodiode. By scanning and interpolating to signal 0 volts, we could get higher precision here, and in addition by comparing with a reference beam, we could get about 50 nanometer precision in our measurement. So I'll show an example of what is known as a perfect absorber. The perfect absorber has applications in, for example, photovoltaics. So the idea here is that you have a metal, a patterned metal or an unpatterned metal on the top, and a very thick metal on in the bottom plane. So this is like the ground plane in antenna or electrical engineering concepts, and you have a very thin, say of the order of like few nanometer thin dielectric, with a very weak absorption inside. Now you design your structure in such a way that the current in the top metal and the bottom metal planes are in opposite directions, so the electric field cancels out within your thin dielectric layer, and you have a magnetic field resonance within this thin layer. Right. So because of which what you're saying is there is no transmission because you have very thick metal layer underneath, and the reflection is suppressed because your resonance is made in such a way that the field is maximum here, and there is zero reflection from this structure. So we made these broadband perfect absorbers for solar cell applications, for example. So the idea here is that we used different sizes of different shapes, squares covering 500 to 550 nanometers, circles covering 550 to say 675, and beyond that we used crosses or diamonds and go up to 850. We showed about 99.86% absorption in 10 nanometer silicon layer in these structures. Right? So, but then the problem with this is if you are going from off normal or oblique angle incidences, so your absorption reduces because these are periodic structure, and then there's always some dispersion coming out from the pattern. Right? So we went to show these quasi-periodic structures which have broadband dispersion-less responses. So here the idea is if you take an array of square lattice and you arrange them in a periodic fashion, and you look at the Fourier transform, what you see is the Fourier transform of a square lattice is again a square lattice. You have these discrete points. So these are the allowed k values for this periodic arrangement. However, you take the same density of periodic scattering elements, and then you arrange these scattering elements in a 5-fold rotation symmetry, a quasi-periodic pattern. Right? The Fourier transform of this turns out to be a very dense k-space, which means now you can have different, for example, you take one k vector, so the separation between these 2 points is the magnitude of k. So the same k is possible in different launch directions. So that means now you don't have launch angle dependence, you do not have any polarization dependence of your incident field, right? And you also have different magnitudes of these k's. So there is one k here, there is a different k vector here. K is nothing but 2 pi over lambda. So you're coupling a broadband light source into these structures. So we demonstrated such structures. So here, for example, the red band is the dispersionless surface mode. And we showed that because you have 4 orders of magnitude intensity localization at this interface, for example, gold air or gold quartz interface, you have these plasmon modes. So these two will help you in enhancing the local field. So we used it to show that we can have broadband second harmonic generation. Those who work with second harmonic generation know that in the nonlinear crystals, you have the phase matching condition. So you need to launch at one particular angle for K conservation so that you get the two the second harmonic components coming out. So you change your launch angle, the crystal may not work because it's cut at one particular angle. Right. So, but here because the thin metal nonlinearity, so there is no phase matching requirement here. You come at any angle, you can excite these or generate this second harmonic. Right. We use this for studying very basic fundamental physics problem of how does these plasmons are excited, but you can excite these plasmons at different energies. You can excite them way above the Fermi energy or at the Fermi energy. So these plasmons, they quickly, within a few hundred femtoseconds, they convert to hot electrons or hot carriers, which are having energies higher than the Fermi energy. So we excited them at multiple energies and studied how they decay down and how they affect the dynamics of plasmons which are at low energy plasmons. So from that we estimated the, for example, the dipole transition elements for each of these transitions, and showed that actually some of the misconceptions in the literature we cleared, saying that the metal band structure, though we are exciting these plasmon modes, the metal band structure do contribute to your to the physics what is happening inside. Right. So once we have this broadband structure, we are using it for label-free detection. So this is one example for urea. The idea here is that SERS, the surface enhanced Raman scattering, is very well known. So when you have a rough metal surface and you keep your analyte on top, so the Raman is much higher than a plane surface. So this is well known, but because of the strong local field, because of this plasmon mode, we do get, for example, almost like 30 times enhancement in the search signal. And the idea here is to use not just one of these single peaks, but have the complete spectrum within, because we have a broadband plasmonic structure now, we get these multiple peaks which get enhanced, the search signal from multiple resonances we pick up. And for a single molecule, not just one single resonance, but we have a fingerprint of multiple resonances. We take the resonant positions, frequency, as well as the intensity ratio between different peaks. We do the principal component analysis to identify specific molecules. So in this case, urea, and we're also working on cotinine, which is a residue of nicotine in the urine or blood samples. This is again a reusable biosensor. So this is a perfect absorber structure in which we have thin silicon layer absorbing, and this is in the asymmetric Fabry-Perot cavity kind of geometry. The trick which we did here is to have a silicon dioxide layer on the top, which we can integrate with a flow cell. So with and without the analyte, we do these ellipsometric measurements and measure this differential phase with and without analyte, and we could show 100 femtomolar sensitivity from this. So in principle, this structure can detect single molecule level concentrations. Right? So this is bound states in continuum. We study in quantum mechanics, basic quantum mechanics, a potential well problem. So we have the potential well, you have the barriers and a well layer in between. So because of the confinement, quantum confinement, you have these discrete energy levels, but above the barrier, you have this continuum of energy levels. However, if you have a roughness in your barrier, for example, as shown here, so within this continuum of energy levels, you have this red layer which is bound. So this is a bound energy state, bound state within the continuum. So these are interesting because these are mathematical abstractions. These are ideally expected to have zero line width or infinite Q factors. So that is why these became very popular over the last 15 years. People are looking at these nanophotonic structures, different elements which scatter light in different directions. And you have this so-called symmetry protected and accidental BIC. So basically, either you can get for normal incidence of your light, which is a symmetry protected because it's only mainly the dipole element. Each of these dipole and multipoles are all oriented in the same direction, and the vector sum of them will lead to scattering element coming in one particular direction. However, in accidental BIC, you can come at any angle, and the vector sum adds up to give scattering in one particular direction. Right? So we showed this kind of structures with polarization independent response. These are square lattice, but still we showed that we can get completely polarization independent response from these structures. Right? So the last example which I'll show is on reflectionless refractive index profile. So this idea is that you take the Schrodinger equation, solve the potentials, solve for the potentials which give zero reflection. There's 100% of the energy is transmitted in the forward direction. Now you compare the Schrodinger equation, which is second order differential equation, with the wave propagation equation inside a medium. Right? So if you compare them, the potential and the dielectric constant of the material, they are one-to-one related. Now if you can mimic this dielectric potential to mimic the potential in the Schrodinger equation, we can get basically zero reflection. So we made these structures with, this has about 98 layers of Al2O3 and TiO2. First we calculate the potential, then we discretize these layers to have sub-wavelength, deep sub-wavelength featured thicknesses and mimic this potential, and we showed we can get less than 0.5% reflection over, say, 500 nanometer to 2700 nanometer. This completely launch angle independent, so this is omnidirectional. You come at any angle, it couples to it. One unique feature of this is it has a broadband negative group velocity dispersion. So from interferometric measurements, we showed that indeed this GVD is negative over a broadband in the range which we measured is from 500 to 800 nanometer. So in this range, so basically we see this negative GVD for this structure. The consequence of this is if you have a short pulse, we showed a 5 femtosecond laser pulse. This is a glass substrate, just simple plain glass substrate with this optical reflectionless potential coated on top. So now, because the reflection is suppressed, the entire broadband 5 femtosecond pulse couples to the glass substrate. If you do not have the coating, only certain part of the spectrum couples to it, and the rest gets scattered out, reflected, transmitted, whatever. But here, because of the strong coupling, we could show that up to an order of magnitude or the even higher enhancement in the supercontinuum generation from these just simple glass substrate itself. Right. Coming back to NPL work for recycling, so waste recycling is one thing which I mentioned. So we do recycling of polysilicon ingot. One thing which people are not worried about is solar panels. We are importing a lot of these or most of our solar panels, though the promise is that they work for 20-25 years, so most of the solar panels go bad within few years, right? So we are looking from the basic physics point of view, what causes this damage to this, and on the other hand, what to do with these damaged panels. So we are recycling them, and we have generated, all these components we have extracted from that. We could get silicon to 4.9 purity right now. We are making the process industry compatible so that we can transfer it to the industry, and also increase the purity, enhance the purity of the recycled silicon so that we can reuse for electronic applications. Right. So this is waste biomass, as I mentioned. So we look at this for different applications, from supercapacitors to PEM applications, PEM membrane applications using carbon nanotube based or just plain carbon composite based sheets. Right. So thermoelectrics is other material which we use. So these are for waste heat utilization from industries to even simple circuits. So we have this large number of thermoelectrics which we work on, which we grow at NPL and make small devices out of it and test them. Right. Just to summarize, so NPL is National Metrology Institute. In addition to metrology, metrology is the science and science of high precision measurements. In addition to metrology, we also have strong presence in material science and also in environmental sciences. For this talk, like I have not mentioned anything about the environmental science activities, but trust me, we have quite a bit of activities there, including pollution mapping. You would be surprised to hear that in Delhi NCR region, people still use a lot of wood, different types of wood in their houses every day for cooking and other purposes. So what are the kinds of fuels, what are the kinds of woods which are used in different locations, and what are the effluents which come out, what are the pollutants which come out. So we mapped all those things for Pollution Control Board and other things. We look at Himalayan regions, so how the pollutants generated at one place because of our atmospheric conditions, how they travel across to different regions, and then how they affect our overall environment. So these are the kind of studies which we do. We have this baseline data coming from Antarctica and Palampur in Himachal Pradesh. So these are the activities which we do. Thank you very much. Any questions? Is there any questions?
Do you have any question from the audience? Any questions? If there is no question, then let us thank Professor Achanta for.
Fundamental question. You have shown such reduction of urea, plasmonic nanomaterial. So what is the role of charge transfer mechanism in respect to electromagnetic enhancement?
There's no charge transport here. In case of SIRS, it's just the Raman signal, right? So we measure the Raman signal and enhancement of Raman signal because of the local field enhancement, right? So at the interface, now we have 4 orders of magnitude enhancement in the intensity of the incident light, right? So that local field enhancement causes your nonlinearity, right, which is contributing to your Raman signal. So with and without the plasmon excitation, we see what is enhancement in the Raman signal. Right? So that is about 30 times. As I mentioned, unpatterned metal versus patterned metal, we get about 30 to 40 times enhancement. We can control it even higher. We showed the highest enhancement is about 200 times.
Any other question? So in the search system, the surface enhancement system, we are using gold as a noble metal. We require any of the noble metal for that. Why not you choose the platinum for that?
We can use, it depends on the wavelength region. So the plasma, there's a bulk plasma resonance, which we know for each material. And in the plasmon, for example, if you want to cover wavelength, right? If you want in the UV, preferably use silver or aluminum. Platinum, you go for the infrared or near infrared.
Thank you very much for the very nice talk. I have a question regarding the shift you were talking about, the cross section shift. Is this dependent on the structure size significantly? Like the light wavelength is 300 to 700 nanometer. So your structure has to be in the same dimension to have.
No, there is no dimensionality dependence. You can, I mean, this is there. If you just launch on any interface, there is a shift. As I mentioned, it depends on the launch angle, and there is a ellipticity which causes this. Now, in case of plasmon mediated goose engine shift, you're exciting light and the surface mode is excited, and it propagates depending on the plasmon lifetime, and eventually it comes out and couples to the far field. So this distance is basically the goose engine shift for plasmon mediated one. That depends on how you design your interface, the pattern.
P and S has a shift.
Right. In our case, the structure which we make is polarization independent. It can work with P, S, circular, whatever.
Okay.
Right.
Thank you, sir.
Any other question?
Hello. Good morning, Professor. There is a slide showing reflectance, and there is a graph, refractive index versus thickness. Maybe 4 or 5 slides back. Yeah, this one. No, go back. Yeah, this one.
Right.
So in this, this is the second graph, refractive index versus thickness. What does this negative thickness represent?
So it just with respect to the some reference center.
Reference.
Right. It
Okay.
just to show that it's a symmetric with
Right.
respect to certain.
Okay, thank you very much.
Any other question from the audience?
Good morning, sir. Sir, my question is that you talked about circular economy. So, does this relate to the econophysics? Sorry, physics again here. Yes. You talked about circular economy. Does this relate with the econophysics part, for example, like economy and physics, or just it deals with the waste recycling? Like, does it
Right.
relate with the creation of wealth through technology?
It requires both. If you make waste recycling, for example, silicon recycling, I said, buying a silicon wafer is, you can get a 4-inch wafer for $5 or $10, depending on how many quantity you're buying. So if I'm making a process by which the same silicon wafer at $500, nobody will buy, right? So the economics is part of it. When we make a process, when we do waste recycling process, it's always at the back of the mind that it should be industry compatible, where the industry should be able to take it up, use it so that it's it's not more expensive than buying a regular wafer.
All the students, please ask more questions. We have enough time, and this is the best time to interact with such a reputed professor. So please ask more questions. You won't get time like that. Live interaction. Anyone?
Right. Thank you.
Thank you, sir. Thank you for such a wonderful talk and to give background about the fundamental research which is happening at NPL. And it is really exciting to know that NPL is doing some research which can be transferred to the industry. And as well as it was such a nice thing to witness that NPL is associated for waste recycling, for recycling the waste also. And it's a good opportunity for all the master's students here and PhD students as well, that they could see what work is happening in NPL, and if they are interested in their future research, like in their PhD or their postdoc, they can definitely reach out to the scientists at NPL. Now we have guest of honor, Professor Avinash Chandra Pandey. I'll give a brief introduction about him. Professor Avinash Chandra Pandey obtained his MSc in Physics and Mathematics, MTech in Computer Science, and PhD in Physics. In addition to degrees in science, he also has obtained an MBA degree. The list of his achievements is very large. I'm narrating a few here. He is currently holding 3 positions. He is the Director of Inter-University Accelerator Center, Delhi, Director of Inter-University Center in Yoga Sciences in Bangalore, and Chairman of Governing Council, Indian Institute of Astrophysics, Bangalore. In the past, he has held the position of Director of IIDS at the University of Allahabad, Vice Chancellor of Bundelkhand University. He is also a professor in atmospheric and ocean science at the University of Allahabad. During his various positions, he has demonstrated academic leadership and achieved administrative excellence and developed the state-of-the-art research facilities. His research interests are in nanotechnology and ion beam physics, and he has published over 300 publications. He is a member of many scientific societies and professional bodies such as APS, ACS. So, he has also served on the editorial board of many reputed journals, and he has also contributed to the formulation of the policies of NEP 2020, which outlines the vision of new education system of India. Now I request him to address the gathering. Thank you, sir.
बाद में अभी बस बाद में है बस 5 मिनट इसको ठीक है So thank you very much for nice introduction. Dignitaries on the dais, Honorable Chief Guest, the Director of NPL, Professor Venugopal, Vice Chancellor of this university for today, Professor Rana, Dean Faculty of Science, Professor Thakur, and the Conference Chair, Professor Ranjana Ji, Convener Dr. Anurag Gaur, the distinguished participants, Honorable Dean Faculties, the Head of Departments, most importantly, the students, dear students. So I'll be speaking formally after this session is over, but just to fill the gap and also complete this ritual of completing this inaugural session, as you have gone through a very nice talk by Dr. Venugopal ji, he has given a good overview how the national laboratories are contributing. I also come from one such laboratory which has a mandate to develop capacity in the area of accelerator-based research. So that opens up many areas, and you know the third industrial revolution was based after this semiconductor devices, they came into picture.
Government of India is looking for an opportunity where we can harness those potentials when we are standing at the brink of the fourth industrial revolution, IoT. National education policy is geared up to take the challenge of making you capable, not in terms of only publishing papers, but also contributing to the economy in a big way. He has given the concept of circular economy. You all know that the development of science and technology in 300 years is more than what it was in last 5,000 years. And if you look at the perspective of societal evolution of 10,000 years, these 300 years of science and technology, the development which is spectacular, it gives some kind of overview and also a pause to think that we have to recalibrate the development in the sense of its sustainability. Reason being that the galloping consumption, overuse of many of the things which has stressed our planet, and the problems of energy, the health, coming days will be challenged with the drinking water. So these are some of the things which are because of galloping consumption, because of splendid isolation of development which took place in science and technology without considering how that society is evolved. So you go anywhere, all the river bodies are stressed. You'll find a lot of pollution. Polluted environment is affecting the health of human being, and not only human being, but also you have started noticing the extinction of species, which is again alarming. So given that kind of environment, as a physicist, as a scientist, we have to recalibrate the achievements in our science and technology, and we have to go for ways by which we can ameliorate the conditions of people, the coming generations, and that is what the take-home message is in view of the new policy which is coming up, national education policy. Don't go for rote learning, try to understand, try to go for higher competencies, developing the higher competencies, which should not be limited only to remembering, understanding, and also applying. We should go for creativity, the creation of knowledge. So with these words, I will close here, and I'll be speaking formally in terms of the requirements of this conference. Thank you very much.
Thank you so much, sir, and we hope we will be able to harness the potential of new education policy of India and new initiatives of Government of India. With that, I invite Professor KPS Rana to come and address the audience, and also request him to announce the open of the conference and release of the abstract book.
Good morning. Dignitaries on dais, good morning to one and all. Professor Venugopal Achanta ji, Director CSIR NPL New Delhi, and the chief guest of the today's function. Professor Avinash Chandra Pandey ji, Director Inter-University Accelerator Center IUAC New Delhi, guest of honor. Professor Sanjeev Thakur ji, Dean of Sciences and Registrar of the University. Professor Ranjana Jha, Head Department of Physics and Conference Chair. Dr. Anurag Gaur, Convener of the conference, distinguished guests, participants, HODs, Deans, faculty members, and my colleagues. It is indeed a great honor for me to address this august gathering today at the inaugural function of the International Conference on Advanced Materials for Emerging Technologies ICAMET 2023. On behalf of Vice Chancellor and Nsut, let me take a moment to brief you about the university. Delhi administration, now it is known as NCT of Delhi, with the approval of Ministry of Human Resource and Development, Government of India, established the Delhi Institute of Technology, DIT, in July 1983 to meet the growing demand of manpower in the field of technology. The institute was renamed as Netaji Subhash Institute of Technology on February 1997. Subsequently, under the Gazette published on September 26, 2018, the institute has been given the status of university as Netaji Subhash University of Technology, NSUT, Wide Delhi Act 06 of 2018. By now, NSUT has been over 40 years old legacy of academic leadership, placement record, strong alumni and specialized laboratories with R&D potential. I would like to share to you some of the recent developments at the university. NSUT is ranked 79th position by NIRF 2021. The university was ranked 3rd in Atal ranking by AICTE. NSUT comprises 18 departments offering 21 UG, 20 PG and 13 PhD programs in various streams of engineering and architecture, computer applications and IT, sciences, management and business administration, animation and design, etc. We follow a choice-based credit system scheme for all the programs of the university. The current intake for the session 22-23 is around 3,500. NSUT offers 20% additional seats for girls students in different courses. In line with the National Education Policy, dual degree programs in open distance learning mode, online mode, has been introduced recently. That includes BSc in Animation and Multimedia, BSc in Data Science, BSc in Artificial Intelligence, a dual degree program. We have a scholarship schemes also for the students. During 22-23, scholarship scheme of SC students sanctioned rupees 48 lakhs, which was paid through direct benefit transfer. Similarly, merit cum means income-linked financial assistance scheme from E-District for 21-22, it was sanctioned for 11 crores. The university equally promotes research and recently awarded researchers for around 42 lakhs for their distinguished contributions to publications and patents. The university has established few centers and that includes University Instrumentation Center for Research Facilities, the Center for Science of Happiness, and Artificial Intelligence Center of Excellence. Our campus placement for the year 21-22 and 22-23, which is going on, a brief about these. For the batches of 2018 and 22 BTech program, the Masters MTech 2022 and MBA 20 and 22. Students passed out in 22, around 255 companies visited the campus and 994 students were placed through campus placement. The various major companies which visited us are Google, Microsoft, Goldman Sachs, Amazon, Walmart, LinkedIn, Tower Research, Adobe, Flipkart, DSHA, McKinsey, Texas Instruments, Qualcomm, and PSUs like Gale, IGL, CDOT, BHEL participated for the recruitment drive. For the students passing in 2022, the average package has been around 17 lakhs per annum, and the maximum has been 1.2 crore by Amazon. We also have an Incubation and Innovation Foundation, which is a Section 8 company registered at our campus. So far, a total of 25 number of companies have registered, wherein 12 companies have graduated and 12 are presently being incubated. NSUT IIF has acquired the status of Atal Innovation Center, supported by Atal Innovation Mission, Niti Aayog, Government of India, with a grant of 10 crore for infrastructure and incubation support. Recently, the incubation facility has received a funding of rupees 2.88 crore from DSIIDC to establish IoT and Fab Lab Center of Excellence in our east and main campuses. With the advent of 20th century, new era for the growth and development of new physics has started, culminating in so-called modern physics. The process was perpetual, and the 21st century is witnessing the miraculous effects of a gamut of cutting-edge technologies with myriad of applications. Contemporary technologies such as nanotechnology, nanoelectronics, nanosensors, smart material, biotechnology, bioinformatics, bio-nanotechnology, information technology, optical fiber, laser, remote sensing, space, nuclear and radiation technologies can be quoted as most important out of the extensive list. It is beyond doubt that physics has played and is playing still the dominant role in the development of these technologies which have primarily affected our life. Material science and engineering is concerned with creating materials with novel properties, and their use in various fields ranging from ultra-fast computer chips and high-efficiency solar cells to high-powered jets and even beauty products. Today, engineering innovations are increasingly dependent on breakthroughs in materials at the micro and nano scale. I would like to cite three simple examples which indicate the promising advanced materials and needs a mention. Graphene. Graphene is an excellent conductor of electricity and heat, and it is incredibly strong and flexible. These properties make graphene ideal for various applications including energy storage, electronic devices and sensors. Nanocellulose is a lightweight, strong and renewable material made of plant fibers. It has high surface area and can be used as a reinforcement material in composites and biomedical applications. It can replace many traditional materials such as plastics and metals in various applications. Carbon nanotubes are incredibly strong and have unique electrical and thermal properties. They have the potential to be used in a wide range of applications from electronics to energy storage devices. Students in material science and engineering acquire solid background in basic sciences and engineering of materials. With hands-on laboratories experience in nanoscale materials, careers in nanotechnology, electronics, computing, biomedical, automotive, and aerospace industries, etc. The deliberations in this international conference will explore various aspects of advanced materials and emerging technologies. It would also inspire the young researchers to continue to work with dedication to improve their skill, further to update their knowledge. Once again, I would like to congratulate Professor Ranjana Jha and the whole team for their untiring efforts in attracting the great scientists to this conference, and a huge number of contributions in the form of plenary talks, invited talks, oral and poster presentations. With all present here, should give them a big round of applause, as that would be the proper acknowledgement for their untiring efforts, accomplishment and success in bringing the event to a fruitful notation. On behalf of Vice Chancellor Nsut, Organizing Committee, and my own behalf, I thank you all for participating in the 3 days international conference. I wish every success to the conference and a happy journey back home. Once again, thank you one and all. I declare the conference open. Thank you.
So now we are performing the opening of the abstract book and souvenir. you, Professor KPS Rana, for addressing the audience. Now, saying thanks is not sufficient for the hard work everyone has put to make this event grand and possible. However, this is the least we can do for them to boost their motivation. For that, now I request Dr. Anurag Gaur to deliver the vote of thanks and express the gratitude to the members who have worked hard to make this event possible.
Good morning, ladies and gentlemen. I feel honored and privileged to get the opportunity to propose a vote of thanks on this special occasion. At the onset, on behalf of the organizing committee, I express our gratitude to the Honorable Professor Venugopal Achanta, Director CSIR National Physical Laboratory, New Delhi, for having accepted our invitation and graced this function as the chief guest. Sir, we are very much thankful to you. I would also like to convey deep regards and hearty thanks to our guest of honor, Honorable Professor Avinash Chandra Pandey, Director IUAC New Delhi. Sir, we will ever remain grateful to you for being with us today. I would also like to give thanks and gratitude to our Honorable Vice Chancellors, NSUT Delhi, Professor J.P. Saini, who provide us constant support and motivation to organize this event. He has been with us as our leader, mentor, and supported in all possible manner to organizing this conference. However, due to some unavoidable circumstances, he could not join us today. I would also like to thank officiating Vice Chancellor Professor KPS Rana for gracing this function by his benign presence. Sir, we are very much thankful to you. I am also thankful to Professor Sanjeev Thakur, Registrar, NSUT Delhi, for his constant support. He helped us in obtaining the necessary administrative approvals for organizing this event in our campus. My special thanks to the conference chair, Professor Ranjana Jha, for her constant help and guidance that radiated a source of energy within us. I would also like to thank all the esteemed deans and respected faculty members present over this function. At this juncture, I would also like to thank our co-convener of this conference, Dr. Harsh Yadav, for his dedicated efforts to make this conference successful. I would also like thanks to all the delegates and the invited speakers who blessed us with their presence and will share their valuable knowledge. We will remain grateful to you and we thank you for being with us today. I am also very much thankful to all the program advisory and organizing committee members for various helps we received towards this conference. Words are not enough to thank their constant guidance and support to shape this conference. I am very much thankful to all the faculty colleagues and non-teaching staff members in particular, and administrative staff of the university in general, who always stand by us. I feel proud and thank you for making this event a successful one. An event of this dimension cannot happen overnight. The wheel starts rolling months in advance. So we have been fortunate enough to be backed by a team of very motivated and dedicated students committee and volunteers. I cannot thank everyone enough for the involvement they have shown and willingness they have expressed to take on the completion of the task beyond their comfort zones. If time is money, then today you have spent millions for us. I am also very much thankful to our sponsors, MTech and Gatan Instrument India Private Limited, Casio, Silicom Electronics Private Limited, Anton Par India, Lab India Instrument Private Limited, SS Scientific Instrument Work, Egg Metal, ABSS, Advent Technologies, and Trinity. It would have been impossible to organize it without the support of our sponsors. I would also like to thank Director CSIR, National Institute of Science Communication and Policy Research, Professor Ranjana Agrawal, for accepting our request to publish the quality papers of this conference in SCI Index, Indian Journal of Engineering and Material Science. I would also like to thank Mrs. Seema Goyal, Deputy Registrar Accounts, for her help in finance-related work, and Mr. Mukesh Garg for beautification and horticulture work. Thanks to all of you for making this event successful. I would also like thanks to Almighty God for showering the blessings by making Delhi like Simla in the month of May. So I wish a pleasant stay of our delegates at New Delhi and enjoy the conference and campus life of NSUT. Thank you once again.
Sir, thank you for delivering the vote of thanks. Now I request everyone to stand for national anthem. And if we have some good singers in the audience, please come forward for singing. जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंग विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा धन मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे. Thank you, everyone. We have now high tea. Yes, we have high tea outside. And everyone, please kindly assemble here after 20 minutes. We are already running out of time. So exactly after 20 minutes, we will start our plenary lectures.
All the speakers of next session, please submit your PPT to the technical team, any member of the technical team or me especially. All of you has to submit before your session. If you come in between, then we are sorry, it will be very difficult.
I request all of you, please join us for a high tea outside the hall on the right side.
भिजवा देना अच्छा भाई भिजवा दे स्टीम होगी ना आपके हम लोग
semiconductors which I have just listed, gallium arsenide, silicon carbide, gallium nitride, or for that reason, the other one. So you see the band gap starts from 0.7 to 6.1. So earlier applications, they were all around P-type, N-type, where the semiconductor, the band gap was around 1.1 or something. And you were trying to modulate the mobility by incorporating impurities, and that too part per million ppm, so that you can have several such devices which you had. But now, I refer to it that don't only consider that I should get some publication. Think of some application and develop material, have a control that you can engineer the properties of the material. That is now the requirement of this day. So everything is available in the country. Many facilities are available in many universities. You have to choose your problem of your thesis. Should not limit it only to have some kind of permutation combination and get some publication, but think of what modification you are expecting in a material and whether that modification will help you in coming out with a device or not. So that should be in your mind. So I'll give one such example. For example, in common semiconductors which we have used, germanium, silicon, or gallium arsenide, the band gap was 0.7 to 1.42 electron volt. So they were all used in all kind of commercial applications, which are there in military, right? But if you go for wide band semiconductors, wide band gap semiconductors, for example, gallium nitride, silicon carbide, in which the band gap is 3.4 or 3.2, or in case of this ternary one, it goes up to 6.1. So you can have high power and high temperature applications. For example, if you have a sensor which is sitting far away from your place and you want to manipulate from here, then you should have a way by which you can communicate to that. So different frequency ranges at different high temperatures, and sometimes these devices are kept into those conditions. So how we are going to use that facility, that should also be kept in mind. I would also like to remind you that now the Department of Space is having another vertical which is in space. So in space is for private developers. The institutions, they are developing many of the things, and ISRO is there to use those devices, sensors, everything, so that they can be put as part of payloads. So now you can also think of developing some sensors or some kind of actuators which can be used for space applications. The other category of semiconductors can be considered of narrow band gap semiconductors, indium and antimony, 0.17 electron volt, or again this mercury, cadmium, telluride, this is all like 0.1 electron volt. And now the application is entirely different. IR detectors, infrared. So you can see this example. If you have a simple sensor, you all have CCTV cameras with you. In CCTV camera, if you take a picture in the night, you will get this kind of information. A car is there and a fellow is standing here. But the same picture, if you take with the help of this narrow band gap semiconductors based IR detector sensors, you will have much more vivid details. What are those details? If you could see here in this particular picture, which is just next to this same picture. One is taken by normal sensor, visible region, and the other one is IR sensor. So you can see here somebody is lying under the car. So there is an accident. The fellow has been crushed, which you cannot see with the help of your CCTV camera. But if you have a IR camera, you can go to those details. So now the applications, you are moving from where the CCTV shall be equipped with IR cameras. And IR cameras, they will be using what? The band gap to the tune of 0.17 or 0.1 electron volt. So you see how the property of a simple, one important aspect is how you are going to tune the band gap and how you are going to use it for a variety of purposes. So this is one such view graph in which I have listed some of the applications. For example, in case of radar, in case of electronic warfare, in case of space remote imaging, if you wish to image having a satellite, there is an imaging tool is there, and you are visualizing some of the things at the Earth, and you are going to communicate with that. Then in that case, the material which is used is gallium arsenide or gallium nitride. If you have thermal imagers, why thermal imagers are important? Because somebody was referring in the morning that climate change is taking place. And climate change, I showed you one IR picture. If I take my picture right now with the thermal imager, you will see that you will have too much of activity in this side, the brain. The heat of this part is more than the heat of other parts. And if you see your thermal imaging of your gut or the inside body, the temperature varies, and that you can visualize. So these are some of the things which need to be looked at from that perspective. You can have cooled or uncooled different kind of infrared detectors. Another challenge which is coming up is detonators. People are bringing explosives with them. Till date, we have yet to mimic the nose. The electronic nose has not yet come. We cannot have that kind of sensor the way dog sniffs, the way dog finds that who is having explosive. So how we are going to mimic the electronic, the nose? That means how we are going to come out with the electronic nose. Electronic nose means it has a specificity that it will detect this particular. See, if you, when we were small, the kid, we could easily smell that who is my mother, who is going to feed us. But while developing ourselves as a full-grown youth, we forgot all those capabilities what we had. But some of the animals, the dogs, they have that kind of capability. For example, if when I come to my residence, my dog sniffs from far away, and she becomes alert and she comes to the door. Many cars come, but when my car comes, she knows that somebody has come whom she should meet first. Why can't we mimic the nature or the biological system which we have? That is a challenge before you. And again, keep in your mind that if you are going to mimic the biological entities, you will get Nobel Prize. Most of the things which you have done in physics will require too much of extraordinary thinking. But if you are going to mimic the biological systems, definitely you invite those kind of awards. So detonators are there, which need to be detected very swiftly, have good specificity to your detecting system. Then high acceleration switches, and we started listening about NEMS, MEMS, nano electromechanical system, micro electromechanical systems. Who is going to work for that? You have to take a challenge, and that requires silicon or SOI-based semiconductors. High acceleration switches for safe arms. Safe arms means now the arms are coming, AK-47, AK-57. Swiftly it pulls several rounds of your ammunition into body. So the safe arms can only be provided if you have this kind of detector. You can lock it so that it cannot be pumped. Other important thing I was talking about, the electronic nose in which gas and chemical sensors, and they are, Dr. Achinta, he talked about CNT, multi-wall CNT, single-wall CNT. So these are another opportunities where now we can harness the property. Most importantly, when avalanches take place, and you might have come to know that Joshimath is under threat. Likewise, those who are going to mountaineers, they also don't know when the snow avalanche will take place and they will get wiped out. So in that case, small trigger which is there in the snow that leads to avalanche, if you can detect that acoustic you can easily sense that now avalanche is going to happen. And for that, piezoelectric materials are. So this is a broad sort of classification. If you have something in your mind about how we are going to have devices for what application, which band gap is required, and for that band gap, which material is to be chosen. So if you think of MEMS and if you search, you will find MEMS as if a fascinating technology. This hall is named after APJ Abdul Kalam Sahab. He once talked about smart convergence. Smart convergence, he explained that it is not only one technology which is going to prove beneficial. You should have IT, BT, NT, CT. IT is information technology, BT is biotechnology, CT is communication technology, NT is nanotechnology. If they all work at the interface, then there will be smart convergence. And then you can do wonders. Why we say wonders? That many such things which you cannot have something on your backpack that this is a big device and this is going to serve some purpose. Now, many of the smart devices are there with you. They monitor your blood pressure, they monitor your blood oxygen, many such things are there. So, for example, these MEMS sensors can also be thought of that can sense smell, that can sense temperature, that can sense pressure, that can sense different kind of chemicals, radiation, and whatnot. So that also opens another area. And why it is more significant? If you compare one device with the MEMS, this is one such instrument measurement system, and this is the weight, 1,587 grams. The counterpart of this particular measurement system, which is conventionally available, if you go into MEMS, it will have only 10 grams, and the size will also get reduced. The power which is going to be consumed by this device will be 35 watt for conventional one, and it will become 1 milliwatt. So you know, same kind of functions can be performed by MEMS or NEMS at much faster pace, with reduced size, and also with the greater efficiency of power consumption. So if you take those devices, it can be on your thumb tip, and that can do wonders, variety of ways by which you can get. So this is the background and how you are going to use our facility. So I will give a good glimpse, try to give a good glimpse that what facility, I cannot cover entire area, but I have chosen only that part which can be used for material modification. So this is ion beam center, is primarily meant for implanter, but having this range of energy, 15 million volt. This was initially used by nuclear physicists, and I forgot to inform you that yesterday in the night I got a call from Archana Sharma ji. She was supposed to deliver a talk, but her mother was seriously ill, so she confirmed me to replace her, to give a talk, number one. Number two, to inform the organizer, Dr. Nandal Singh ji, that she will not be coming. So where she works, that facility is CERN, having energy range in giga-electron volt. Our facility is 30 years old, and the energy is limited only to 15 million volt, million electron volt. And if you go for different charge states, definitely it could go up to 280, depending on what kind of ion species you are using. So this is one such facility which is exclusively for the university researchers. So Sharma ji was referring to this part, that those who have joined this university, they should take a call. They should come to our center, find out where they can join hands, where they can find their contribution in terms of writing a proposal, getting a student, and working in that area. So many such facilities are there in the country. You have Raja Ramanna RRCAT. RRCAT is also available if you come through IUC, through UGC DA CSR. That facility can be utilized using this IUC concept. We are here at New Delhi. Then we have variable energy cyclotron facility at Kolkata. TIFR has similar facility what we have. We have 15 UD, they have got 14 UD pelletron, but that is not open to university researchers, and there are many other accelerators in Bhabha Center and also in other universities. Other universities, for example, Institute of Physics Bhubaneswar, IGCAR Kalpakkam, Punjab University, IIT Kanpur, where we have focused ion beam, Mangalore University, 3 million volt tandem at GGV Bilaspur, which was non-operational. We have taken a lead and we are going to make it operational. Kurukshetra University, and the one which I set up in Allahabad is 300 kV ECR-based ion implanter can be utilized by you people. So this gives a glimpse, and unfortunately, being a versatile facility, we are not known in the community. अगर आप जाइए किसी से पूछिए आसपास वाले लोगों से तो वो पूछते हैं साहब वो बम फैक्ट्री जाना है क्या? तो न्यूक्लियर फिजिक्स का मतलब हमारे यहाँ बम से मानते हैं। तो जब इसका नाम न्यूक्लियर फिजिक्स न्यूक्लियर साइंस सेंटर था तो आसपास के लोग उन्होंने दिमाग में बैठा लिया कि ये तो बम फैक्ट्री, और ये जो टावर दिख रहा है ना उसमें कोई ऊपर बम रखा हुआ है। तो कम से कम आप लोग अपने मन से ये भ्रांति हटा दीजिए और एक बार आइए एंड हैव ए लुक। हैव ए लुक का मतलब कि हमारा जो प्रेजेंस है इज़ नॉट ओनली लिमिटेड टू 1 or 2 यूनिवर्सिटीज़, वी हैव गुड फुटप्रिंट अक्रॉस द कंट्री एंड ऑल्सो आउटसाइड द कंट्री। पीपल कम, और एक बार जब आप आ जाते हैं तो फिर लगता है कि इसके अलावा कहीं और जाना ही नहीं है, तो दैट बिकम्स योर सेकेंड होम। सो एज ए डायरेक्टर इट इज़ माई ड्यूटी ऑल्सो टू इन्वाइट यू ऑल टू टेक अ लीड हाउ वी कैन मेक यूज़ ऑफ दिस फैसिलिटी इन ए बिगर वे। और कभी कभी हम लोग चिंता होती है ना कि पब्लिकेशन आएगा कि नहीं आएगा, तो पब्लिकेशन के लिए भी हमने एक स्लाइड रखी है यहाँ पर। जब शुरुआत की थी तो पहली बार एक आया था, लेकिन उसके बाद देखिए ये संख्या बढ़ती ही चली गई, और कुछ लोग कहने लगे हैं कि आप वहाँ तो कुछ भी डाल देंगे आयन बीम ले करके तो आपको मिलना ही पब्लिकेशन। ऐसा भी है, लेकिन हम उसको डिस्करेज करते हैं। वी शुड गो फॉर डिवाइस related research, we should develop something, and we should get some of the concepts cleared for ourselves, and also we can bring out the mechanism which is not known till date. So during this period, about more than 1,000 students, they have completed their PhD just around the facility what we have at IUAC. We go for inviting you the way I have come today, acquaintance program. There is a MSc orientation program, and this is some of the listed one, which is giving you MOUs. MOUs पर मत जाइए, जरूरी नहीं कि आप NSCT से में MOU करेंगे तभी आपको एक्सेस मिलेगा, बिना MOU के भी आप आ सकते हैं। We have got PhD teaching program, तो जो requirement है आपके पास कोर्स वर्क का, अगर आप इसके अराउंड करते हैं either nuclear physics, material science, we can also give you a time slot where the students who have enrolled here, they can take the coursework at my center. For new users, for those who have joined this center, this university as a faculty, हमारे पास ये 2 डेट्स याद रखिए, जुलाई का 6-7 तारीख और दिसंबर का 17-18। दिन कोई हो, कुछ भी हो, हर वर्ष इन 2 दिन जुलाई में, 2 दिन दिसंबर में हम आपको राउजिंग वेलकम के लिए खड़े होते हैं, जहाँ पर रेड कारपेट बिछा होता है। आप अपने प्रपोजल्स लाते हैं और आप ही लोग रिव्यू करते हैं कि ये करने लायक है कि नहीं, और करने लायक है तो कितना समय आपको अलॉट होना चाहिए। So that is another dates which you should remember. Those who are planning, they should come immediately because that is open, is all available on the website. उसके लिए मेरे पास भाग के आने की ज़रूरत नहीं है, ये वेबसाइट आपके पास है, इस वेबसाइट पर जाइए और इस वेबसाइट पर ये सारी चीज़ें एरियाज़ लिखी हुई हैं। उन एरियाज़ में कौन कौन से प्रपोजल कौन कहाँ कर रहा है उसके बारे में भी आपको जानकारी मिलेगी। तो जो आप रिव्यू ऑफ लिटरेचर करते हैं, कौन क्या कर रहा है, आप क्या कर सकते हैं, हाउ कैन यू ऐड टू द नॉलेज, वेयर इज़ द गैप इन द नॉलेज, साइंटिफिक मोटिवेशन कैन ऑल्सो बी फाउंड with the available literature what we have. We have made ourselves transparent and that is all available on our campus. The other important thing which I would like to add is I am going to set up 3 petaflop supercomputing facility. अगर आपको बिल्कुल मन नहीं करता है कि हमको लैब में जाके रिसर्च करनी है, आयन बीम के साथ में रात में बैठ के काम करना है, कंप्यूटर पर ही काम करना चाहते हैं तो आप मॉडल्स रन कर सकते हैं, सिमुलेशंस कर सकते हैं, तो उसकी भी सुविधा शीघ्र ही आपको मिल जाएगी. एंड दैट विल बी ए बिग सुपर कंप्यूटर, 3 पेटाफ्लॉप सुपर कंप्यूटिंग फैसिलिटी, एंड दैट इज़ फॉर यू. आप लॉगिन आईडी क्रेडेंशियल्स ले लीजिए, अपने प्रोग्राम रन करिए और उसको एनालाइज करके यू कैन ऑल्सो पब्लिश. ये हम दिखाते हैं, ये आपको इवेंट्स, इफ़ यू आर इंटरेस्टेड इन एनी ऑफ द इवेंट्स रिलेटिंग टू योर एरिया, ये सब कुछ है. ये हम चेंज नहीं करते हैं, बस एक आध लोग हैं जैसे डॉक्टर नंदलाल सिंह जी बैठे हैं, इन्होंने हमारा ये सब इसको तोड़ फोड़ किया था एक बार, तो हमने इसको मॉडिफाई कर दिया यहाँ पर. इनका एक वर्कशॉप है जो आप कराते हैं न्यूक्लियर ट्रैक सोसाइटी की तरफ से. अदरवाइज दिस इज़ ऑल फ्रोजन, इज़ वेल अनाउंस्ड वेल इन एडवांस इन द बिगिनिंग ऑफ द ईयर. यू कैन ऑल्सो आइडेंटिफाई an event where you are interested, you can join. और इस तरह से हम लोग देश भर में इस तरह के वर्चुअल स्कूल्स करना, लेकिन वर्चुअल स्कूल से इम्पॉर्टेंट ये है कि फिज़िकली आप आइए और इंस्ट्रूमेंट्स के साथ हैंड्स ऑन आप सीखिए. तो कोविड का दौर गया, और जब कोविड का दौर था तब भी ये चैलेंज था, तो हम लोग बैठ कर के ये तय करते थे. कई स्टेट से ये सिफारिश आती थी कि साहब बिना इम्तहान लिए लड़कों को पास कर दीजिए. फिर हम लोग सुप्रीम कोर्ट भी कुछ लोग चले गए, सुप्रीम कोर्ट में भी जाके लड़ाई लड़ी हमने कहा आप थोड़ा दूरदृष्टि देखिए. ये बच्चे अभी इनको लग रहा है कि इम्तहान दिए बिना पास हो जाएंगे, लेकिन 10 साल बाद इनको कोविड बैच कहा जाएगा. इनके कॉम्पिटिटर्स कहेंगे तो वो तो कोविड बैच वाला, इसने इम्तहान ही नहीं दिए कि पास हो गया. तो फ्रॉम दैट परस्पेक्टिव सुप्रीम कोर्ट ऑल्सो एग्रीड. सो एनी फॉर्म ऑफ एग्जामिनेशन शुड ऑलवेज बी देयर. सो वर्चुअल इज़ ओके, वर्चुअल में आप तमाम लोगों से जुड़ेंगे अभी, लेकिन डूइंग एक्सपेरिमेंट्स विद योर हैंड्स इज़ ए फन. सो दैट शुड बी. अब एक कठिनाई और भी है कि आप कहेंगे साहब वो बड़ा लंबा वेटिंग लिस्ट है, हम मानते हैं वेटिंग लिस्ट है, लेकिन इसके लिए हम एक नया एक्सेलेटर और लगा रहे हैं और इसी जून तक आपको वो एक्सेलेटर लग के मिल जाएगा. और इसके अलावा जो हमने बताया कि द मेनी अदर एक्सेलेटर्स विच आर नॉट यूज्ड ऑप्टिमली, यू कैन जॉइन हैंड्स विद देम ऑल्सो. सो उनको भी आप जा कर के टैप करिए और वहाँ आप जाके काम कर सकते हैं. इसके लिए हमने अपने को जो हब स्पोक मॉडल होता है कि वी आर हियर, वी विल बी हेल्पिंग देम in case of any maintenance repair, but they will be made operational for the use of researchers from different countries. So second part में हम आपको थोड़ी चीज़ें बताएंगे कि हम लोग आयन बीम से स्ट्रक्चरिंग कैसे करते हैं. तमाम चीज़ें हैं, इसके कई पार्ट्स हैं which I am not going to cover because the time is short, the program is delayed and I have another meeting which I have to attend. So I will be covering only one part, that is how we are going to structure with ion beams. स्ट्रक्चरिंग विद आयन बीम्स when जैसे हम लोग जब छोटे होते हैं ना, तो बचपन में क्या करते हैं, कोई चीज़ हाथ में मिली तो उसको पूरी शक्ति से फेंकते हैं कि देखते हैं कहाँ जाता है. और कभी कभी वो माता पिता के सर में टकराता है, तो कभी दीवार में टकराता है, तो एक आध स्लैब भी मिलता है कि तुमने मुझे चोट लगा दिया. यहाँ कोई आपको स्लैब नहीं लगाएगा, क्योंकि यहाँ पर आपके हाथ में जो दिया गया वो दिखता नहीं है आपको. दैट इज़ आयन एंड दैट इज़ एक्सेलरेटेड एट ए वेरी हाई स्पीड, हाई एनर्जी. And then you have got a substrate on which you have grown the film, the material which you are interested in. You are going to modify the property of that material. You are going to structure the surface. That is all possible. तो ये तमाम phenomena है कि whenever the charged particle interacts with the material, the matter, ये तमाम चीज़ें लिखी हुई हैं यहाँ पर कि इलेक्ट्रॉन पिकअप होगा, डिसॉर्प्शन होगा, सेकेंडरी इलेक्ट्रॉन निकलेंगे, स्पटरिंग होगा. ये सब तमाम फिनोमेना है. उस फिनोमेना में आप किस में इंटरेस्टेड हैं, यू कैन डिवाइज योर एक्सपेरिमेंट अकॉर्डिंगली. सो आई एम नॉट गोइंग टू रीड ऑल दोज थिंग्स. एंड द लास्ट वन इज रिटन एज इम्प्लांटेशन. हमारे यहाँ लास्ट प्रायोरिटी थी इम्प्लांटेशन, एंड नाउ वी से दैट वी मिस द सेमीकंडक्टर. बस हम बैठ के कोड लिखते हैं, लेकिन जो चिप है वो ताइवान से आती है. तो अब भारत सरकार कोशिश ये कर रही है कि चिप बनाने की भी सुविधा, और जो चिप बनाने की सुविधा हमें चाहिए. कोविड में सबसे बड़ी प्रॉब्लम जब आई थी वो चिप्स की थी. गाड़ी बन के तैयार है, गाड़ी खरीद कर नहीं ला सकते आप, क्योंकि उसकी जो चाबी लगती है उसकी चिप नहीं आई. तो लाखों की तादाद में द कार्स वेर रेडी एंड दे वेर रेडी टू बी पिक्ड बाय द कस्टमर. सो दिस वन एग्जाम्पल. मैनी सच एग्जाम्पल्स आर देयर वेयर द चिप्स आर इम्पॉर्टेंट. So whenever these charged particles interact, the energetic ions enter into the material. You have photo emission, you have electron emission, you have scattering, you have sputtering. It may be nuclear sputtering, it may be electronic sputtering, it recoils, gamma rays comes out, X-rays comes out. So what we do, if you are interested in X-rays, we can provide detector for detecting X-rays. If you are interested in gamma rays, we will provide you different kind of detectors. So our job is to provide you all those tools which are required for your research work. So that is what we do here. So when the ion-solid interaction takes place, so there are two regimes. One is nuclear collision, that is called inelastic, and the other one is elastic collision. That is nuclear one, and inelastic is stopping energy electronic, stopping energy nuclear. So another consideration which is for you, in which regime you want to work. क्या सेलेक्ट करना चाहते हैं आप, इलास्टिक में जाना चाहते हैं, इनइलास्टिक में, किस एनर्जी से आप काम करेंगे, वो आपको चेक करना पड़ेगा. और दूसरी बात ये कि there are many simulations also, packages are there, you can always calculate with the help of those packages how well into the depth it will travel, उसका struggling क्या होगी, उसका कुल range क्या होगा, that you can always come. I will give one example which is again a user of our center. आप ये देख रहे होंगे ये जो surface दिख रहा है यहाँ पर, ये surface ऐसे लग रहा है जैसे कि कोई चांद पर कोई टुकड़ा उकड़ा है जो दूर से आप देख रहे हैं. ये चांद का टुकड़ा नहीं है, ये आप आँख से देख भी नहीं सकते, इसको देखने के लिए माइक्रोस्कोप चाहिए. अब इस चांद के टुकड़े को जब आप बम्बार्ड करते हैं विद आयन बीम्स, तो यहाँ लिखा हुआ है 1.7 × 10⁻13 आयन्स पर सेंटीमीटर स्क्वायर. तो ये इस पर क्रैक्स डेवलप हुए. इसी को अगर आप थोड़ा और बढ़ा दीजिए, यानी कि 13 से आप 10⁻15 ले जाइए, तो आप देखिए कुछ स्ट्रक्चर इसमें डेवलप होना शुरू हो गया. थोड़ा सा और इसको अगर आप थोड़ा सा का मतलब 10⁻14 तक ले जाइए, तो यू सी अनदर स्ट्रक्चर कम्स आउट ऑफ दैट. और फिर क्या लगने लगता है जैसे कि टावर्स निकल आए, बुर्ज खलीफा की तरह, उसमें ढेर सारे छोटे छोटे. अब आप उनको नैनो स्ट्रक्चर्स हैं, अगर आपके पास कैपेबिलिटी है तो आप उनको प्लग कर लीजिए और उसको आप अपने सेंसर में लगा लीजिए, उसको फंक्शनलाइज कर लीजिए. A number of ways are there by which you can utilize the surface to volume ratio, having those nano towers which can be functionalized, which can be used in sensors for its ultra sensitivity. So this is one example in which you can use the ion-solid interaction for the purpose. Likewise, you can embed metal particles inside. And today in the morning, somebody was talking, NPL Director Sahab was talking about SPR. So you can tune SPR also. So I'm not going to cover that part, but nanocrystals can be formed by embedding these metallic particles. And once they are embedded, you can look at what is the surface plasmon resonance. And again, you can tune your energy range to look at different phenomena. And for that, there is a range of facilities. केवल एक शर्त यह है कि ये फैसिलिटीज़ आप जब यूज़ करें तो आप ज़रूर आयन बीम का इस्तेमाल किए हुए हों. अदरवाइज़ फिर वो फ़र्क नहीं पड़ेगा कि आप JNU के IRF में जाते हैं या हमारे यहाँ आते हैं. हमारा मैंडेट ये है कि यू हैव टू फर्स्ट यूज़ आयन बीम एंड देन कैरेक्टराइज. सो कैरेक्टराइजेशन की होल रेंज ऑफ फैसिलिटीज़ अवेलेबल which can be utilized, and this is a schematic which you could see here, how we are going to implant, how we are going to modify the surfaces using different beam lines. और ये in situ XRD, in situ Raman, कि आप बम्बार्ड कर रहे हैं और उसी समय देखिए कि स्ट्रक्चर कैसे बदल रहा है. XRD भी आप कर सकते हैं. तो ये आपके पास इस प्रकार की भी सुविधा है. माइक्रोस्कोपिक कैरेक्टराइजेशन सर पूछ रहे थे कि ऐसे SEM है कि नहीं, TEM है कि नहीं, AFM है कि नहीं. सबसे पहला जो आया था वो हमारे यहाँ आया था. और बिना इनके जो नैनो फिंगर्स हैं उनके आप नैनो टेक्नोलॉजी कर ही नहीं सकते. नैनो टेक्नोलॉजी वाज नोन मच बिफोर 1959 में कभी रिचर्ड फाइनमैन ने प्लेंटी ऑफ रूम एट बॉटम कहा था, लेकिन वो 86 के बाद जब बेनिंग रोरेर ने STM खोजा, उसके बाद से हमने नैनो टेक्नोलॉजी का नाम शुरू किया और फिर हम लोग उसको सिस्टमेटिकली अपने डिसिप्लिन का पार्ट बनाया. सो दीज फैसिलिटीज़ आर अवेलेबल विद यू. These are small spectroscopic measurements, photoluminescence facility, solar simulator, transport, low temperature, magnetotransport, thermopower. This again giving you a glimpse is all available on website. And also you can use the synthesis techniques to develop your film, your thing. And now everything has been brought under one umbrella because Government of India wants that this should be utilized optimally. It should not be in the custody of one single individual researcher. So We are hoping that we will also go for Sathi, Shriman kind of arrangement in which industries can also be made party to this kind of thing. Now coming to the other areas जो हमने आपको बताया उसको और क्या क्या हो सकता है, I'm giving you those areas, और इसके बारे में अगर आप थोड़ा भी इंटरेस्ट रखते हैं तो you are welcome. I can connect it with my scientists and they will give you how to work in that area. So the first important thing is ion beams based, if you wish to go for nanostructuring, surface modification. So the ripple that gets formed if you are bombarding, I have given one example. The band gap tuning, which I have given the applications, how you are going to make the use of storages in the core shell structure. Then sometimes instead of thermal annealing, we use Swift heavy ion induced annealing as well to make the surfaces stable. I have some view graphs. If time permits, I can show you how the D band, 2D band, if you anneal, the graphene structure changes. If you are interested in modifying those things, single layer, double layer, you can always use ion beams. Likewise, nanocomposites, you can enhance the catalytic efficiency of different kind of nanocomposites. You can work on the modification of work function of such kind of nanocomposites, and you can also enhance the thermoelectric power in these kind of systems. Some of the phases, especially in nuclear physics, some of the nuclei, they are formed but have very short-lived sort of, you cannot see. If the detectors are smart, they can resolve, but they don't exist, they don't live longer. Likewise, some of the new novel phases are also formed. So you can also look at, if suppose you are interested in another kind of phase, then the electrical conductivity, thermoelectric power, that can be modulated, that can be modified. Magnetic anisotropy, if you are using metallic ion beam, then you can modify the magnetic property in a desired direction or isotropically. This is all possibility. I worked extensively in the area of electronic sputtering, in which if suppose you bombard, पानी में आप पत्थर मारते हैं तो उससे पानी छलकता है. वो स्प्लैश जो है उसको किस दिशा में निकल रहा है, कितनी मात्रा में निकल रहा है, क्यों यही वाला निकल रहा है, वो आप सब देख करके बता सकते हैं, उसकी मैकेनिज्म पढ़ सकते हैं. दैट वी डिड extensively. Then again I've told you band gap modification, you can engineer band gap, you can plan doping experiments, the flux, pinning, novel phase, many such things. And most importantly, nowadays we have started working with the biological systems also. So biological systems, you can bombard a cell and kill or target the DNA, which is, and DNA as well as the mitochondria. If the mitochondria is killed, the cell dies. So another area is fascinating, and that is in coming days the hadron therapy. And Archana Sharma, she would have talked, because she is behind me, that you should take a lead and we should have hadron therapy facility in our country. वो उनका पैशन है, वो हमेशा वही बात करती हैं कि कौन करेगा, हम नहीं करेंगे तो. और आप जानते हैं कि हैड्रॉन थेरेपी का मतलब ये जो आयन बीम है वो पेंसिल बीम है. कन्वेंशनल रेडियोथेरेपी में आपने कोई रेडियो एक्टिव सोर्स रखा तो उससे जो रेडिएशन एमिट करेगा वो आइसोट्रोपिक चारों दिशा में जाएगा. वो आपके नॉर्मल सेल को भी किल करेगा और साथ में जो ट्यूमर है उसको तो किल कर पाएगा कि नहीं कर पाएगा, उसकी सीमाएँ हैं. इट कैन नॉट एंटर इनटू द बॉडी. कोई डीप सीटेड ट्यूमर है उसको तक नहीं पहुंच सकता, तो आपको पहले सर्जरी करके खोलना पड़ेगा कि इसमें ट्यूमर बैठा हुआ है, उसको फिर आप दिखाते हैं रेडिएशन, विच इज़ otherwise possible. You can use the energetic proton, oxygen, carbon beam, tune the energy and deliver the energy at a desired depth without affecting the medium through which it passes. जिसको हम लोग फिजिक्स वाले लोग ब्रैग पीक कहते हैं, sharp bragg peak. We can harness that kind of potential of ion beams in medical area for treatment of cancer. So that is one such area which is coming up. So if you talk about, if I have given these areas, what are the device-related applications? Detection of ovarian cancer cell by SPR. ये हमारे users हैं जिन्होंने किया है, इसलिए हम आपको दिखा रहे हैं कि ये केवल हवाई नहीं है, लोगों ने इसमें काम किया है. ग्लूकोज को डिटेक्ट करना using SPR. attachment of protein on a nanocrystal thin film, surface Denhan Raman scattering जिसकी बात सवेरे डायरेक्टर साहब कर रहे थे NPL के, then you can go for UV filter, you can internalize एक नैनो पार्टिकल को ले जा करके किसी सेल के अंदर डाल दीजिए, that is all possible if you use ion beams. समय कितना है मेरे पास? खत्म हो गया? ठीक है, ठीक, बहुत समय तक नहीं ठीक है, तो हम इसको कुछ रिजल्ट्स आपको दिखाते हैं कि हमने इतनी बात बता दी कि बड़ा ये भी कर सकते हैं, ये भी कर सकते हैं, उसके रिजल्ट्स कैसे हम इसको नॉवेल टूल मान सकते हैं कि बहुत बढ़िया टूल है जो स्ट्रक्चरिंग करते हैं, नहीं कि जैसे आप कैलीग्राफी करते हैं, कोई चीज़ लिखते हैं, लिखने के साथ साथ अगर कोई पैटर्न बन सकता हो सरफेस पर, कोई मेटेलिक ट्रैक बन सकता हो जिसका यूज़ कहीं और हो सकता है, वो पॉसिबिलिटी है क्या? तो आप जानते हैं कि जब पहला STM आया तो लोगों ने देखना शुरू किया कि कार्बन के एटम कहाँ हैं, दिखाई पड़ने लगे, वो विजुअलाइज करने के लिए। तो पहले स्टूडेंट जो हमारे थे, पहले हम लोगों ने भी कोशिश की कि क्यों ना हम लोग अपना खुद का STM बनाएं। हार्डवेयर किसी ने बनाया, सॉफ्टवेयर किसी ने बनाया, दोनों को जब उसकी मैरिज करानी चाहिए तो वो मैरिज नहीं हो पाई, सक्सेसफुल नहीं थी मैरिज। तो पहला अटेम्प्ट हम लोगों का 2000 वाला फेल कर गया STM बनाने का। लेकिन उसके बाद पीपल ट्राइड एंड एक प्रोफेसर है IIT कानपुर के सहदेव, ही डिड वर्क अ लॉट इन दैट एरिया, और उन्होंने खुद का अपना कंपनी बनाया और एक क्वेजार सिस्टम्स करके ही इज़ डेवलपिंग AFM विच इज़ मच बेटर दैन द कमर्शियल सिस्टम्स। सो दैट कैपेबिलिटी इज़ ऑल्सो देयर। इसको हम इसलिए कह रहे हैं कि आने वाले दिनों में आप ये मान के चलिए कि आप कोई नौकरी करेंगे के बजाय आप कितनी नौकरी दे सकते हैं। अगर आप स्टार्टअप के बारे में सोचते हैं, अगर आप इंस्ट्रूमेंटेशन में कोई चीज़ कर सकते हैं, कोई नई चीज़ बना सकते हैं, तो थिंक ऑफ दैट. You will not only contribute to the knowledge, but also you will give jobs to many people. One part. The second part, we are depending more on the foreigners. कि वो एक उन्होंने सामान पकड़ा दिया छोटा सा, उसके बाद वो कहेंगे साहब AMC ले लीजिए। हर बार वो अपना सॉफ्टवेयर अपडेट करते हैं और उसके बाद जो अपडेट आता है वो जब हमने ख़रीदा था 10 साल पहले उस मशीन से ज़्यादा पैसा मांगते हैं। और आपको ये भी खुशी होगी कि हमारे सेंटर ने MRI मैग्नेट, हमारा कप ऑफ टी नहीं, हम लोग उसमें काम नहीं करते, लेकिन चैलेंज मिला कि क्यों ना आप लोग MRI का मैग्नेट बनाए। देखना चाहते हैं तो वो MRI मैग्नेट इस समय हमारे पास रखा हुआ है। जून के अंत में वो चला जाएगा मुंबई फॉर अगेन मैरिज विद द सॉफ्टवेयर। वो वहाँ काम चल रहा है, वहाँ पर एक पुराना मैग्नेट खरीद करके उससे हम लोग इमेजिंग कर रहे हैं। बट द सुपर कंडक्टिंग मैग्नेट 1.5 टेस्ला एंड दैट टू एट टेम्परेचर व्हाट -268 कूल करके। और आप सभी जानते हैं सुपर जो कंडक्टिंग पढ़ चुके हैं कि एक बार उसमें करंट दौड़ा दीजिए तो हमेशा करंट दौड़ती रहती है। परसिस्टेंट मोड में डाल दीजिए आप, तो अस्पताल में तो ये ज़रूरत नहीं पड़ती ना कि रोज़ आए कोई चलाने वाला है कि उसको हैंडल लगा के चला रहा है। एक बार मैग्नेट बन गया, कमरे में रख दिया गया, वो काम करता है। उसमें उतना हीलियम भरा होता है। और दूसरी बात, चैलेंजेस क्या हैं कि जिस वॉल्यूम में हम मरीज डालते हैं वो 30 डिग्री पर होना चाहिए, और जिस वॉल्यूम में मैग्नेट का जो सॉलिनाइड का जो आपने कॉयल रखा हुआ है वो -270 पर होना चाहिए। -270 और 30 डिग्री का ग्रेडियंट कैसे मेंटेन करें? एक बात, यूनिफॉर्म मैग्नेटिक फील्ड होना चाहिए। और आप जानते हैं कि अगर आप सॉलिनाइड में एक्सपेरिमेंट करें तो आगे चल करके एंड पर डाइवर्ज कर जाता है। इसको कैसे यूनिफॉर्म करेंगे? तीसरी चीज़, जिस पावर सप्लाई से आप उसको एनर्जाइज करेंगे, पावर सप्लाईज में खुद फ्लक्चुएशन इतना होता है कि वो मैग्नेटिक फील्ड को वेरी कर देगा। और मैग्नेटिक फील्ड को आपने वेरी किया, हमारी इमेजिंग हो रही है तो उसमें घोस्ट इमेजेस आना शुरू हो गई। चौथी इंपॉर्टेंट बात, 1.5 टेस्ला तो उसमें है, और बगल में अगर कोई पेसमेकर चल के पहन करके कोई पेशेंट जा रहा है तो वो तो 1.5 पर चला गया। तो आपको वो मैग्नेटिक फील्ड कैंसिल करना पड़ेगा, जिससे कि आउटसाइड मैग्नेट दैट बिकम्स 5 गॉस। एन नंबर ऑफ सच कॉम्प्लेक्सिटीज़। और कोई बताने वाला नहीं, 3 प्लेयर्स हैं दुनिया भर में, फिलिप्स है, सीमेंस है। वो आपको क्यों बताएंगे कि आप कर लें, और गलत बता देंगे कि पूछे कोई कि इधर जाना है तो कोई नहीं उस तरफ चले जाओ, जिससे उधर जाके गड्ढे में गिर जाओ। ऐसी स्थिति। तो कैसे करते हैं? तो एक पुराना मशीन लाए, मैग्नेट का काटा, तब जाके अंदर पता चला कि ये तो खाली वायर ही नहीं है, इसके अंदर और भी तमाम चीज़ें. We developed many of the things. To cut the story short, ample opportunity exists for physicists. लेकिन उसके लिए क्या चाहिए कि केवल किताब का श्रोडिंगर इक्वेशन सॉल्व करने से काम नहीं चलेगा. और हम बार बार वो एग्जाम्पल लेते हैं कि हमारे साथ हम जब एक बार इन्विजिलेशन कर रहे थे तो एक बच्चा चिल्लाया, श्रोडिंगर इक्वेशन बताओ, भूल गया था श्रोडिंगर इक्वेशन. रिजिड रोटेटर की प्रॉब्लम आई थी. तो अब किसी की हिम्मत है, हम लोग खड़े हैं, तो उस समय तो इज्जत लोग करते थे कि उनके सामने नहीं पूछना है. फिर बाद में पूछा कि हो गया क्या? हाँ हो गया. उसको याद आ गया कि 5 पन्ने में उसका डेरिवेशन होता है. तो पीछे वाला उसको याद था रिजल्ट क्या आता है. पीछे से उसने डिराइव करना शुरू किया. फिर धीरे धीरे उसको इधर से आना शुरू याद हुआ और बीच में लाके कहीं चिपका दिया. और रिजल्ट भी जानते हैं हम लोग, कैसे कॉपी जांचते हैं वो भी अलग बात है, यहाँ नहीं कहने की बात है. ही पास्ड. सो दैट काइंड ऑफ अंडरस्टैंडिंग इफ यू आर ट्राइंग टू बिल्ड, कि आपने कोई चीज़ रट लिया बिना समझे हुए, तो दैट इज़ ऑफ नो यूज़. नाउ द सिस्टम हैज़ चेंज. एक कम पढ़िए, लेकिन जितना पढ़िए ढंग से पढ़िए, उसको ऐसे पढ़िए जैसे कि वो आप ही ने उसको जन्म दिया हो. ये आपका कॉन्सेप्ट होना चाहिए. सो कमिंग टू दिस सरफेस ऑफ हाईली ओरिएंटेड पायरोलिटिक ग्रेफाइट, इसका जब आप एसटीएम करेंगे तो आप इसको देखेंगे कि ये इस तरह से दिखता है. अब इसी को अगर आप बम्बार्ड करना शुरू करिए, तंग करना शुरू करिए, इसके ऊपर एनर्जेटिक आयन से इसको बौछार कराइए, तो आप देखेंगे इसमें से तमाम, कहीं पर क्रेटर बनता है, कहीं पर पहाड़ खड़े हो जाते हैं, कहीं पर गड्ढा बन जाता है. वो नाउ यू कैन सी इट यूजिंग एसटीएम, यूजिंग मैनी सच टूल्स. How it is going to help you? Sometimes C60 comes out of that. When it comes out of that, why it comes out only C60? ये सब चीज़ें आपको फिजिक्स उसके बारे में बताएगी. It will tell about the property of graphene, why it reacts, why it behaves that way. So this is all. Then you get the conducting tracks. Some of the images you could see here. You can tailor the property by कंट्रोलिंग द इलेक्ट्रॉनिक एनर्जी. चैनल को कैसे आप मॉडिफाई करेंगे, ये डिवाइस के पॉइंट ऑफ व्यू से. और हमने आपको पहले ही बता दिया कि ये डिवाइस नेम्स और मेम्स के लिए चाहिए. उस लेवल पर प्रिसिशन के साथ में अगर आप सेल्फ ऑर्गेनाइज्ड बिहेवियर ला सकते हो, वहाँ पर आप स्ट्रक्चरिंग कर सकते हो, देन इट कैन बी यूज्ड फॉर दोज पर्पसेस. सो इन केस ऑफ फील्ड एमिशन प्रॉपर्टीज़, जो ये फाउलर नॉर्डाइम इक्वेशन है, इसको फॉलो करते हुए कैसे आप नैनो वायर्स को बनाएंगे, कैसे इनको मॉडिफाई करेंगे जिससे कि ये फील्ड एमिशन के काम आ सके. C70 कैसे बनेगा? C60 का एग्जांपल था. C70 कैसे बना? जब आप फुलरीन का जो कार्बन नैनो वायर्स को आपने, these are all published things and is all available. Then how the nano dots are formed, ripples are formed using ion beams on a different substrate. How these ripples vary with different fluences on a surface which can be silicon carbide. How you can anneal the defect. जैसे यहाँ पर हमने आपको बताया था ना कि अगर आपने ग्रेफीन लिया तो ग्रेफीन में आपके पास ये एक पीक है, एक G पीक है, एक 2D पीक है. जब आप इसको डिफरेंट फ्लुएंस से बम्बार्ड करते हैं तो आप ये देखते हैं कि इसमें मॉडिफाई हो जा रहा है, DG कहीं घट जा रहा है, या इसका एरियल पार्ट जो है वो चेंज हो गया. जो एरियल उसके अंदर उसका पार्ट है, दैट गेट्स मॉडिफाइड, एंड दैट कैन बी looked at from the perspective of its application. कैसे इसको हम मॉडिफाई कर, कैसे इसको हम हारने, कैसे इसको एक्सप्लॉइट करने जा रहे हैं, दैट इज इंपॉर्टेंट. फॉर एग्जाम्पल इन दिस केस इफ यू सी हाउ दिस डी पीक, द एरियल इंटेंसिटी वेरीज. एरियल इंटेंसिटी वेरी करता है तो जो कौन सा फॉर्म है जो कि ट्रैक, जो डैमेज वाला पार्ट है, कौन सा उसका इलाका है जो कि अनीलिंग के लिए काम आ रहा है, ये आप डिटेल्ड में इसकी स्टडी आप यहाँ कर सकते हैं. ये सब क्यों कर रहे हैं? क्योंकि रेडिएशन स्टेबिलिटी चाहिए. रेडिएशन स्टेबिलिटी कहाँ चाहिए? जो आपका इलेक्ट्रॉनिक्स आप स्पेस में भेजते हैं, सैटेलाइट में लगाते हैं, आप जानते हैं कि वहाँ पर एक्सेलरेटर नहीं है, वहाँ पर कॉस्मिक रेज का बम्बार्डमेंट होता रहता है. और कॉस्मिक रेज आर एनर्जेटिक पार्टिकल्स. तो आपने तो पी टाइप एन टाइप का डायोड बना के, ट्रांजिस्टर बना के, उसमें डिफरेंट पर्पज़ के लिए कैमरा लगा के फिट किया, सब कुछ किया, लेकिन वो क्या होगा कि जब बम्बार्डमेंट उस पर लगातार हो रहा है तो पी टाइप तो बदल गया, कुछ और हो गया, उसमें डोपिंग हो गई. उसका जो फंक्शन था, एम्पलीफायर, ऑसिलेटर, whatever function it was performing, now it is completely changed. So that electronics which is sitting in space should be radiationally hard. उसको कोई फर्क नहीं पड़े. तो दैट पार्ट वी ऑल्सो डू कि जो भी सैटेलाइट में इलेक्ट्रॉनिक्स जाती है पहले मेरे पास आती है, तो अगर 5 साल उसको रहना है तो 5 साल में उसको कितना बम्बार्डमेंट झेलना पड़ेगा उतना हम लोग सिमुलेट करके 1 शॉट में देख लेते हैं कहीं कोई चेंज हुआ क्या। अगर चेंज हुआ तो उसको डिस्कार्ड कर देते हैं, देन वी गो फॉर फ्रेश इलेक्ट्रॉनिक्स unless otherwise it is proven it is hard. So graphene is one such example which gives you stability under given conditions. Radiation hardness आप उसमें पढ़ सकते हैं। और ये ढेर सारे अन्य पब्लिकेशंस हैं जो हम लोगों ने नैनो कंपोजिट्स, नैनो स्ट्रक्चर्स आयन बीम के थ्रू किए। एंड आई गेस आई शुड क्लोज हियर बिकॉज इज एंडलेस, ये स्टोरी बड़ी लंबी है, तो इसलिए भी क्लोज करना है कि आप बुलाएंगे नहीं दोबारा। तो जब कभी बुलाएंगे तो हम आपके पास फिर से दूसरे रूप में, दूसरे अवतार में, दूसरे एस्पेक्ट को लेकर के कवर करेंगे। थैंक यू वेरी मच फॉर गिविंग।
Thank you, sir, for such an amazing and interesting talk. Do we have some questions from the audience?
Thank you, sir. Nice presentation. Sir, I have one query about the graphene. Actually, graphene have insulator nature, not semiconducting nature. But still, we are applying graphene in many energetical applications. So, what is the basic reason about that?
You can play with the D band, G band, 2G band, and also the topological insulators, in which see the band gap of graphene is what? Nothing. But you can open up the band gap. So band gap tuning of graphene by modification is all possible. So graphene जो आप कभी ऐसे साहब हमारे जो आजकल है ना अजय सूद, इनकी टॉक आप सुनते हैं तो ये पंजाबी में कहते थे कि ग्रेफीन टू सी ग्रेट। तो ग्रेफीन टू सी ग्रेट इसीलिए हो क्योंकि उसकी प्रॉपर्टीज़, चाहे वो कंडक्टिंग हो, चाहे वो उसका whatever, is 1,000 times, 100 times more in case of its strength also. So you can modify the graphene, you can have one, and आप जानते हैं जो graphene का नोबेल प्राइज मिला, नोवोसोलोव और गीम was ब्रिटिशर, और उसके पास जैसे हम लोग PhD कराते हैं, कोई आया बच्चा काम करने के लिए, काम क्या करना है, ये करना है कि देखो ये HOPG है, इस पर से सेलो टेप चिपकाओगे, इसको उखाड़ोगे, इस सेलो टेप पर कुछ काला काला चिपका होगा, इस पर दूसरा कुछ चिपकाओगे, फिर इसको उखाड़ोगे, ये करते चले जाओगे और बाद में आखिरी वाले सेलो टेप को डिज़ोल्व कर दोगे और जो बचेगा वो उसको निकालना है। तो जितने PhD स्टूडेंट्स आते थे यही करने के लिए हमको PhD करना है। Novozolov was Russian at that time, he had to move from Russia, so he accepted that challenge. उसके बाद उन्होंने उस ग्रेफीन शीट को अलग किया, एक लेयर को निकालना मुश्किल है, और हम लोगों ने भी, मेरा खुद का पेपर है जिसमें इसका यील्ड बहुत कम है, एक ग्रेफीन का एक शीट निकालिए थोड़ा सा निकलेगा, चाहे वो आप CVD से करिए चाहे किस तरीके से करिए। तो इंटरनेशनली दोज हु आर वर्किंग इन दिस एरिया, सो दे गो फॉर, कोई ग्रेफीन दिखाता है तो जैसे लगता है कि झाड़ू लगा करके कूड़ा इकट्ठा कर दिया, दैट इज़ नॉट रिक्वायर्ड, बड़ा बढ़िया पैटर्न आपको चाहिए। हमने केमिकली सिंथेसाइज किया हाई यील्ड के लिए। तो कमिंग टू योर पॉइंट, that graphene has got all the wonders which are there. You can modify these bands by creating defect structure, and then you can do whatever you want. जब लैंडाउ लिप्सिड्स ने पहले बताया था कि it is difficult, it is impossible, you cannot have a perfect 2D structure. Theoretically आप प्रूव कर सकते हैं कि 2D नहीं मिलेगा, तो फिर ये ग्रेफीन कैसे आया? इसलिए आया क्योंकि वो परफेक्ट नहीं है, उसके अंदर रिपल्स है, उसके अंदर हिलॉक्स है, उन रिपल्स के कारण वो स्टेबल है। तो इट इज़ नॉट एग्जैक्टली 2D, बट इट हैज़ गॉट सम रिपल्स। सो दिस मटेरियल स्टिल इज एक्सप्लोर्ड फॉर वेराइटी ऑफ पर्पज। अगर आप और डिटेल में जाना चाहते हैं तो आ जाइए, हम आपको वो भी बताएंगे कैसे D, G और 2G को मॉडिफाई करके क्या।
First of all, very thank you, sir, for your wonderful talk. My question is very general. You talked about that we lack in semiconductor industry. So, as MSc students, how can we play our role in this industry, and what is IUAC is doing like from nowadays, like to improve the condition.
देखिए, एक तो हो गया ना, IUAC में हमने बताया आपको कि हम जब बने तो बॉम्ब फैक्ट्री बन गए, न्यूक्लियर फिजिक्स करने लगे, और लोग नाराज़ भी होते हैं कि साहब आपने न्यूक्लियर फिजिक्स वालों को किनारे करके मटेरियल साइंस करने लगे। तो आयन इम्प्लांटर एक ऐसी फैसिलिटी है जहाँ पर आप अपने ढंग से कोई भी डोपिंग कर सकते हैं, जो डोपिंग किसी समय में जिन लोगों ने खोजा 64 में उन्होंने किया। एक हो गया। दूसरा, हमने आपको पहली 2 स्लाइड्स दिखाई जिसमें आपको केवल 4th ग्रुप में 3rd या 5th की डोपिंग तक सीमित नहीं था। आप 2, 6, 3, 5 सेमीकंडक्टर्स, उसके बाद यू आर ट्यूनिंग द बैंड गैप, सो दैट इज़ ऑल पॉसिबल। आप क्या कर सकते हैं, जैसे हमने एप्लीकेशंस के दायरे बताए कि अगर आपको बैंड गैप बढ़ाते जाना है, क्यों बढ़ाते जाना है? क्योंकि हाई पावर का कोई हमको डिवाइस बनानी है, रेडियो फ्रीक्वेंसी के लिए बनाना है, रडार के लिए कुछ बनाना है, या सैटेलाइट कम्युनिकेशन के लिए बनाना है। तो यू कैन कम, यू कैन डिसाइड योर मटेरियल, यू कैन modify the property of that material, of that band gap, you can tune the band gap, use that material by having a different kind of ways कि आप epitaxial growth करते हैं या किसी तरह से आप उसको, जो भी आपके पास तरीका है, आप उससे डिवाइस बनाइए और उस डिवाइस का उपयोग उस कार्य के लिए करिए। तो ये समय ऐसा है कि जैसे हमने इन स्पेस का नाम लिया, इन स्पेस में ये कहा गया है कि अब सैटेलाइट में जो कंपोनेंट्स लगेंगे वो इसरो नहीं बनाएगा, वो बच्चे बनाएंगे। बच्चे कैसे बनाएंगे? बच्चे नए तरीक़ों का इस्तेमाल करेंगे, इंस्टीट्यूशंस का इस्तेमाल करेंगे, जहाँ सुविधाएं उपलब्ध हैं उनको करेंगे, और जब वो प्रूवन हो जाएगी तब वो उठा करके प्रक्षेपित कर देंगे। वो हम सैटेलाइट लॉन्च करने का सुविधा हमारे पास नहीं है। सो योर रोल कम्स नाउ, you have to identify what property you are going to modify, how you are going to tailor. There are a variety of ways by which you can tailor the properties. Which method is best suited for your particular material, and how you are going to utilize that in a device. So that is up to you. आप कर सकते हैं। हमने छोटा सा ग्लिम्स देने की कोशिश की थी जिसमें एप्लीकेशंस, कौन सा मटेरियल, तरीका, कहाँ, ये है।
Probably is interested to know the job opportunities.
जॉब अपॉर्चुनिटी हमने पहले ही बताया कि आपको जॉब खुद के लिए नहीं सोचना है, जॉब क्रिएट करने के लिए सोचना है। ठीक है, अब पैराडाइम शिफ्ट हो गया है। पैराडाइम शिफ्ट ये भी हो गया है कि हम लोग पहले सोचते थे स्टार्टअप, अब यूनिकॉर्न्स की संख्या बढ़ गई। और जो हमारे साथ हमारी बहनें बैठी हैं, आपको जान के खुशी होगी कि जो विमेन एंटरप्रेन्योर्स हैं, अभी इसी साल 7-8 तो यूनिकॉर्न लेडीज़ ने बनाया है। तो आप भी किसी से पीछे नहीं हैं, आपको बस आगे आना है। और जो आपका दूसरी बात थी, जैसे हम लोग अभी स्ट्रगल कर रहे हैं, तो इसरो में एक पहले सेमीकंडक्टर कॉम्प्लेक्स हुआ करता था यहाँ पर चंडीगढ़ में, उसको डिपार्टमेंट ऑफ स्पेस के बजाय MIT को दे दिया गया। वहाँ पर स्ट्रक्चरिंग चल रही है और हम लोग नेगोशिएट कर रहे हैं कि जो टेक्नोलॉजी ताइवान के पास है, ताइवान भी स्मार्ट है, वो जब कभी डर लगता है उसको चाइना से तो इधर आता है, फिर लगता है कि ठीक हो गए। तो वी आर ट्राइंग टू गेट दैट टेक्नोलॉजी ऑफ 45 नैनोमीटर सेमीकंडक्टर चिप। वी कैन सेट अप द प्लांट हियर एंड देन वंस दैट कम्स हियर, जैसे हमने एक उदाहरण बताया आपको MRI मैग्नेट का, मुझे पता लग गया कि हमको ऐसे बनाना है, अब हम क्या करेंगे? उतने तक सीमित नहीं रहेगा। क्यों 1.5, क्यों होमोजीनियस? हम तो अब उसमें कोशिश ये करेंगे कि हम ले जा करके अपने एम्बुलेंस में लगा दें छोटा सा हेड गियर, कि किसी को अगर कहीं पर ब्रेन स्ट्रोक हुआ तो उनको टेलीमेडिसिन के थ्रू पता लग जाए कि ये रप्चर था या एम्बोलिज्म है या कहीं पर स्टेनोसिस है, सो दैट ही कैन गेट इमीडिएट रिलीफ। So once you know the ins and out, it opens up an enormous opportunity. जब तक नहीं पता होता तभी हम लोग बस केवल वही, जैसे सड़क पर चलने के लिए घोड़े के लिए कहा कैसे चलो, वो हमने आपका हटा दिया, पट्टा हटाया है। थिंक।
Thank you, sir. Any more questions? If you don't have any question, let us thank Professor A.C. Pandey again. And sir, thank you so much for opening the opportunities for our students to come to you for the collaboration and for future work. Now I invite Professor Ranjana Jha to present certificate and a memento for invited talk to Professor A.C. Pandey. Thank you everyone for listening to the talk. Now we have lunch available at the same place where we had high tea. And before going to lunch, I request some members here to submit your presentation. Dr. Nirmal Kumar, Dr. Muskan Raghav, Dr. Preeti and Dr. Deepa Kumari. Kindly submit your presentations here. And after lunch, we have sessions parallelly going on in 3 rooms. So all the invited speakers and speakers are requested to go to your respective rooms and the participants can choose as per their interest. Thank you so much. I'm announcing the names again. Dr. Nirmal Kumar, Dr. Muskan Raghav, Dr. Preeti, Dr. Deepa Kumari. Kindly submit your presentations. And please proceed further for lunch. उनको दे दो. We will connect here again at 2:30. 2:30? Yeah. So we will connect at 2:30 again. Sharp at 2:30 we will start our next sessions. Thank you everyone. आ रहे हैं लोग. कर दिए.
ठीक है अब ये तो नेक्स्ट वाले से आपको करना है आपका काम कल का मॉर्निंग से
कुछ बोला ही पता नहीं है क्या करना है बता दो. बस आकर के उस जो आएगा वो बोल दो.
नॉर्मल ये वाली तो नॉर्मल टॉक ही है
नॉर्मल टॉपिक से बस सेशन चलता है.
जिप कर दूँ हाँ जिप कर दो इसको
This is the specialty of the material. And because here we have a elite gathering who can understand better that how the material can be very, very useful for water splitting if we are able to create nanopores into it and oxygen deficiency. And we are open. Means my lab, my other team members are open to support anybody on that part. If they want, they come to our lab. Even from here, the student is coming to us also for doing the hydraulic cell. And it's not only one institution. Almost in India, 22 institutions are working with us, including Indian Institute of Science or IITs, or you name any of the big university on hydraulic cell. Because objective was very clear that we wanted a device which should be a parallel, or I'll say the replacement of the solar cell. And the solar cell, why? Because I am the PhD on that, silicon solar cell. Why I am interested for the replacement? The answer is that I wanted it should be cheap, it should be easily available, and moreover, it must be a biocompatible, no e-waste should come out of it. So that was the objective of it. With the time, we could achieve that, accomplish it in such a way that it tells us that any of the material which we are talking these days can be transformed into energy material. Because if you talk about the nuclear energy, what is happening? You are having a uranium, then disintegrating, getting energy, right? In case of solar cell, we have the light, photon falls, it generates your electron hole pair, and we are able to separate them, collect them, and we get electricity. But the point is, silicon is very expensive. In India, unfortunately, we are unable to prepare even the silicon, so we are importing almost everything. And the technology behind solar cell is a very sophisticated, because I myself was fabricating solar cell 35 years before, and even later on for 15 years, P plus N, N plus structure, and then putting an anti-diffusion coating and doing it, and that too in a very clean lab. And the technology itself, diffusion, everybody knows that it's not easy. But in this case, it's a very simple. That this material, when we are talking, let's talk about a ferrite, because we started from the ferrite as a hydroelectric cell, as a base material. So on that base material, at the initial stage, we took magnesium ferrite. But we found that the dissociation of the water molecule was less. It means the power output of that material was less. So how to enhance it? So the way was, we substituted in it lithium. So we use the simple oxides, carbonates, and then put into the simpler way of solid state reaction method. So calcination was done, then sintering was done, and during this process, we know very well that if the processing is changed, those steps are taken in different way, we can create the oxygen deficiency and as well as the nanopores into it. So because that's a, we are not doing anything, but the steps are different in between. So the material is ready for water splitting. And once the water has been split, H plus and OH ion, then we have to collect them, separate them and collect them. That process my knowledge was, and my experience was in the PN junction, so I tried on that site. My student, Dr. Jyoti Shah, was also working with me. So she also did it, but we could not get the current more than nanoampere or a microampere. But we wanted the 100 of the milliampere current out of the at least our 1 by 1 inch square sample, so that it can match with this silicon solar cell. So what was to be done? We started working in a different way, that why not to substitute first. So like a lithium oxide, lithium carbonate was used to substitute the lithium into the magnesium ferrite. And we found it has made us happy that we were getting even the 100 milliampere, 120 milliampere in that. And the voltage, how to get it? Forgetting about the PN junction, then we took the help of our chemistry, electrochemistry. So what we did, we put 2 electrodes, which you can see very clearly over here. It's a brown color. On the top you can see, it's a brown color. It's a magnesium ferrite sample is like this, but it's a nanoporous. We are not showing anything on that. But on the top, white cross-fingered pattern is there. There is nothing but a silver cathode. And on the back side of it, on the other opposite face of that, of the silver, you will see that there is a zinc. So zinc foil is used for that purpose, and zinc is acting as an anode. So as soon as the water has been split into H plus and OH ion, zinc is taking a OH ion, goes towards that because of their electrode potential. And what is happening? Zinc hydroxide forms. With the zinc hydroxide formation, one can see is very simple even in that. What we find that the 2 electrons, zinc hydroxide is formed on the zinc and 2 electrons have been freed. Those 2 electrons will go through the shortest path through the wires and reach to the H plus, where the H plus ion are there on the silver side. And on the silver side, H plus ions are getting the electrons and just producing the 2 H plus ion, 2 electrons gives you the hydrogen. So we have got a device which has got the 2 things together. It's smartly providing us electricity, but also hydrogen. So we took it at the initial stage. It was invented in 2016. Of course, we were working for 14 years prior to that, only under this material. Besides my experience, Dr. Jyoti experience on the material science and as well as the device, I had a good experience. It took us a long time to reach to this stage, and once we have got it, what has happened? We found, we are very happy that we are getting currents in milliampere, and the voltage is also 0.98 volt on the one cell, and it is nothing but due to the electrode potential of the 2. So this hydroelectric cell, the name when we coined, it is a marvelous combination of material science. Material science means where we are having a oxygen deficiency, then nanoscience, where the nanopores are playing a big role into it for physicalization of the water molecule, means the water splitting, which are more than 30% in this material, in the one cell or any material what we talk. After this, nanoscience, and then we have combined the electrode chemistry, means the electrochemistry, and then therefore it is a combination of 3 sciences, interdisciplinary, and we get a hydroelectric cell. So we have a name. Today, more than 70 papers are available in the literature, which have been published in the last 3 years. Not only we, others are publishing, besides the other work. But during that time, we wanted to see that what are the problems associated with it. For us, zinc hydroxide was initially we were thinking that it is not a good for us. But later we realized that this zinc hydroxide is nothing but a high value industrial compound. Zinc hydroxide as such is used because it's a nanoparticle, 40 nanometer size nearly, or the lower than this. And also, the zinc hydroxide, if we heat it at 500 degrees C, it converts into zinc oxide nanoparticle, and the price is very, very high. That price is much higher than whatever with our cell and whatever we are doing. So the one byproduct itself, and it is a biocompatible, even if we don't want to use it, it is a biocompatible. After this, when we realize that the hydrogen is being generated as another byproduct, then we thought, why not to think that the hydrogen can be produced by it in a better way. So that time, in 2017, Ava Shukla, she's sitting over here, She's my student at the moment doing the PhD on this and this. So we said, okay, let's work on this. We are already working on the hydrogen generation. So why not to accelerate the water splitting? In other words, water dissociation. So how to do it? So the only way and only answer was that we apply outside DC voltage. So that is the second where my photograph you are able to see. You will see that it's a simple diagram which gives us, that's a prototype we have shown, that the cells have been put into water, hydraulic cell, and we are putting the 10 volt, 5 volt, and the current is of the order of 1 ampere. And then this process accelerates so much that the hydrogen produced is in fact 200 times than what we are getting as a byproduct. So that way, the whole device, the hydraulic cell, is really smart. We are able to get cleanest energy on it. Now, we are able to get the electricity out of it. Byproduct is also very important in terms of the business, because when I am going to industry, requesting them, okay, please get it and put it into the market for the large scale production, they only calculate first the only mathematics about the how much they are going to gain in terms of money, not for the science, not for the pride, because this itself is a big pride for the India. Not only for the big pride for the India, it is for the whole scientific community in the world. But the realization at the student level, it has got the ample opportunities to work on any of the material you take. It's not ferrite you take anyone, you take the any other oxide, you talk about the SNO2, you talk about the TiO2. In all we have already done, 29 compounds we have done already, which show our hydraulic cell. So you can imagine a person who, I was publishing a lot of papers, doing work in the very high-end research, but I left almost all those areas for last 5 years. Of course, if there is some important problem, then I work. Otherwise, I have left almost that, which I don't do for the sake of that this has come up, the hydraulic cell has come to that level, which is I have not seen in my research career of last 40 years. Internationally, means at a global level, as well as in India. I meet almost everybody, Nobel laureates outside, here, there, and they also praise for it, all the people who are working on it. It means this is the one which is really a smart material, energy material. We need not to worry for the nuclear radiations or that how it can really do it. Now, the another part of it, a boon for net carbon zero. If you look at the title, because title I have kept before coming to this place, I decided that what title should be given and does it make it complete sense what I mean. So that's a boon for net carbon zero, because what net carbon is again a word which is nothing but a carbon dioxide, because I have been working on environmental sciences, leading that group also. Therefore, my interest gets into that side more. And what we have found that the international terminology is carbon, for the carbon dioxide, carbon. But of course the carbon was put because it's not only the one carbon dioxide, but the greenhouse gas, means it should be a methane also. So which is a main content is carbon, and now we say net carbon zero, means we should not emit carbon dioxide or our methane. But because the maximum proportion is from the carbon dioxide, so I am focusing myself, for the carbon dioxide, the net carbon zero means in this process there should not be even not only this, from the beginning, from the mineral state to the final state and then the disposal of any of the device is to be known as, if there should be net carbon should be zero. Zero means if you have emitted, have you produced that much energy, so that which helps us as a green energy or a clean energy. So this does completely on that part, and that way hydroelectric cell once it is put into the production or our day-to-day uses, so it is going to help us a lot. तो मूवी नहीं कर रहा आगे they say another important history, because I'll just talk about, because I need not to tell you that, because I have already spoken that sintering, solid state reaction, but I'll show you important slides that at least you see that if you look at this slide, what we find that Volta cell was in 1800. These were invented. Dry cell 1886. Lead acid battery, of course it is a storage battery, like what is our session. It's not for the primary energy source, but I am speaking on the primary. Probably I am the first speaker on this session. So lead acid battery invented, and everybody knows that the lead is a carcinogenic, there are a lot of problems, sulfuric acid, but still we are using. Solar cell invented 1954, lithium ion battery in 1991. In fact, it was done in 1971. But so long period, and then the hydroelectric cell invented in 2016. So that way, if one sees that what we have done, you can see again graphically that even all these and where our lithium ion battery appears. And the applications have been shown at the bottom. The another part of this, the cell is totally invented in India, means all raw materials, even the furnaces which I have been using, students come to our lab, they find that everything is indigenous, because the raw material as well as, that is another important part, that we are doing everything indigenously, not that we are importing. How the hydroelectric cell works, you can see that animation, the water molecule is falling on the nanoporous one, and H plus and OH ion, zinc hydroxide has been formed. A simple way for the student to understand that how it is working. Then when we come to the another part, it tells us a very simple non-photocatalytic, because you know already there is a photocatalytic process for which 80 years, for last 80 years people are working, they are using photocatalysts. Catalysts are very, very expensive, and the amount of hydrogen produced is very small. If I compare with our results, we could publish a paper on the hydrogen production by the hydrogen cell. At that time also, in the 2018, it was 200 times larger than that. And in that, your photocatalytic activity, things were very, very different and expensive. But again, in this case, nothing on that side. You get electricity, eco-friendly, everything is there, no carbon dioxide, nothing. And advantages of this, I have been telling that how the advantages will be there, no harmful effects, no e-waste. For the material scientist or the physicist or the chemist, or I'll call even the metallurgist, for them, there are a lot of application open to it, because it absorbs the heavy metal also. It absorbs dye also, and that paper is already, our paper is under review on that one. We are doing it, and it has got another opportunity to act as a fuel cell proton exchange membrane. So many dimensions, but the problem is on a stage when I am speaking, so I always invite that please take up some other application and as well as this application, so that we can do something more on it. This is no point in energy fuel demand increasing, pollution is increasing, global warming. I will not come to because the carbon dioxide emission is at the moment in gigatons, 200 gigatons or so. Then these weather change, I will not come to this. I'll just come to only one or two more slides and try to conclude it. Even for the oil, because oil is producing oil means we are talking about petrol and diesel. You can just see 150 kg of carbon dioxide out of 150 liter of petrol and 150 liter of diesel. And we are burning, even in Delhi, million of the liters per day. So you can imagine how much carbon dioxide we are pumping into the atmosphere, forgetting about the NOx, forgetting about the PM 2.5, particulate matters. And another interesting fact, carbon dioxide in kg for the two-wheeler which runs for 50 kilometer in a 1 liter. So you can imagine that how much we are getting the carbon dioxide emission. And the most important, which is a hidden fact, that while it is being taken out, crude oil is being taken out from the wells and it is coming to us, means for the use in the vehicle, we are finding there is a lot more than that carbon dioxide is emitted in the process what we are burning out of those oil. Same is with the, can we utilize hydrogen before, prior to the oil? So that we have to take care. This can be taken up in case of our fuel hydrogen. Hydrogen production, even today, if we just look at the pie chart, I'm not going to speak anything, because the next is the hydrogen. It's not only electricity generation, hydrogen is to be generated, and we know all hydrogen mission in India, all over the world is being talked about, and they have started working in the West. In India also we have initiated already, but if you look at the hydrogen production share, you'll find with the electrolysis it is only 4%, but it is being produced because it's an industrial product, very important for fertilizers to generate ammonia, and also in other processes. You can see the natural gas is 48%, largest portion, oil 30%, burning of oil, and the coal is also 18%. That means the hydrogen which we are producing at the moment in industry is nothing but emitting lot of carbon dioxide. So it's not useful. That means we have to go and talk about the green hydrogen. And this is the answer. Our hydroelectric cell is the best answer, as a green hydrogen produces. And you can always look at, find out in the literature that what we talk about, is it really correct or not? Yes, only 2 minutes I'll take. You can see here our product, lab product in the prototype form. It's a here 2 watt LED bulb is being illuminated through our 2-inch cell, because that's a 2-inch hydroelectric cell, and in the 2-inch, not the one we are connecting 3. So they are connected in series to provide the higher voltage, at least about 3 volt, and then you can see the illumination. For the similarly, not only the bulb, you can see the even different type of the cells, these small cells. Rather than the big cell, then you can see the small cell which are the 1 inch square, and the bulb is glowing, LED bulb. It's open, it is put on one of the paper. Similarly, if you look at the other one, it's another one with your lamp is being lit, and that's it again a diya where the button cells we have created out of the hydroelectric cell, which makes a very clear thought that it is a good product and can be done. And if we can do in the lab, why not you people? Anybody, not this. This was with our award and the recognitions. It's here in the photograph, this side, I am there on the inner side. Outside is Dr. Jyoti receiving the RE award. And elsewhere had taken us already in our energy volumes, which is our encyclopedia, and international magazines, if you look at, which are the very reputed, which are US, UK, even at the bottom you'll see the World Energy Reports and all these. They write Indian scientists with the water have produced. So that makes a sense that if you have done something big, this was published in 2016 and 17, because that time it was a new, and they write as an Indian scientist. Of course, while it has been covered in India, they don't write it in Indian scientist because we are in India. So those news, and as well as all newspapers and TV covered this one. But I do not know how many you have seen, and I'll conclude it here that it is a really how much big. I'm not going to show you the list of the papers. There is a list of papers and other small things. I stop here and just get the time for the others.
Thank you, sir. Thank you for
Everybody is satisfied.
grand enlightenment to the academic community and this participant. I am sure all of you have got benefited from your this actual research by which you have developed this device and invented it and patented it. Thank you, sir. Thank you very much. वहीं बैठते हैं.
Now I would like to request Professor O.P. Thakur sir to acknowledge Professor Kotnala with a memento and certificate of appreciation. Next किसकी है? पहले बंद कर दो इनका. किसका है पहले? किसका है? 02 निर्मल. सर ये नाम इन्होंने मैं ही भूल गई नाम.
For discussion.
Okay. So our next presentation is from Amit Soni. The title of his presentation is Development of Low-Cost Blood Group Monitoring Device. So you are having 7 minutes for presentation and 3 for question answer round.
Good afternoon, all of you. My name is Amit Soni. I am a research scholar and working under Dr. Ashok Kumar. Today, I am going to present my work on development of low-cost blood pressure monitoring devices. What is blood pressure? The blood pressure is a pressure exerted on the artery walls during blood flow. The blood pressure is not a static value. It fluctuates between two values. The upper one is called systolic blood pressure and lower one is called diastolic blood pressure. According to systolic and diastolic blood pressure values, human health can be characterized in several categories which are listed in table. How we can measure the blood pressure? There are several techniques. First one is invasive technique, in which we use a catheter, which is inserted in the artery, and we measure blood in a glass column. This method, we need to puncture the artery. That's why it is risky and highly sufficient. High cost instrument are required for that, and doctor is also required. So to remove this dependency, the another technique, non-invasive techniques are there, in which first is sphygmomanometer. We know very well about a sphygmomanometer, in which a cuff is wrapped up in the upper arm, and we apply pressure in the cuff to block the artery. Then start deflating the cuff and listening beat sound with the help of a stethoscope. The first sound is corresponding to systolic blood pressure, and last corresponding to diastolic blood pressure. On the other hand, automated blood pressure devices are also available in the market. By pressing just a single button, it gives you the systolic and diastolic blood pressure values. To validate these devices, international universal standards are there, according to which 85% of total measurement, the error value should be less than 10 mmHg, and standard and mean deviation error should be less than 5 mmHg and 8 mmHg. Most of these devices are not working properly. They show higher values. So we have developed a device. It is a prototype right now. We have developed a device whose figure is shown here, and circuit diagram also. And another one is another figure represents the block diagram, in which a microcontroller Raspberry Pi Pico is used, and a cuff which inflate and deflate according to requirement with the help of air pump and control circuit. The pressure in the cuff is assessed with the help of a pressure sensor. It generates an electrical signal whose amplitude is too small. We need to amplify, and then the signal goes to Raspberry Pi Pico, ADC terminal of Raspberry Pi Pico. We also require oscillations in the cuff. To extract this oscillation, we use a band pass filter. The process, by just clicking the start button, motor start, or air pump start, and inflate the cuff. During the inflation, we observe small peaks, which is corresponding to area of interest. We apply pressure higher than the systolic pressure, and then start deflating the curve. Below the area of interest, we completely release the cuff pressure. To calculate the blood pressure values, we apply maximum amplitude algorithm in the deflation oscillation in the deflation region, in which we create an envelope over these oscillations and find maxima. The cuff pressure corresponding to this maxima is termed as mean artery pressure, and systolic and diastolic values are calculated with the characteristic ratio. We try to validate our device with the device NIBP simulator, which works as an artificial heart and generate oscillometric pulses with predefined value of systolic and diastolic. Systematic diagram is shown along with the experimental setup, and we have tested 95 different BP combinations, and found that the SBP, DBP, MBP values, calculated SBP, DBP, MBP values, and error values are within 10 mmHg. All points are within the criteria, and mean and standard deviation are well below the criteria. And in last conclusion, we have developed an automatic blood pressure device which is based on non-invasive oscillometric technique, and it uses a maximum amplitude algorithm to calculate the blood pressure values. The device gives systolic and diastolic blood pressure values. We have tested this device for different BP values for low to high blood pressure range and found that the device works, follow the universal protocols. Thank you.
Anyone? Amit, how do you prove your novelty of your work? A large number of electronic devices are available in the literature
Sir-
for blood pressure measurement.
सर जो भी मार्केट में अवेलेबल डिवाइसेस है वो मोस्टली डिवाइसेस बनाते हैं तो उसके लिए एक एल्गोरिदम का यूज़ करते हैं. तो उससे पहले वेवफॉर्म एक्सट्रैक्ट करके उसके बेसिस के ऊपर एल्गोरिदम बनाई जाती है. तो मोस्ट ऑफ डिवाइसेस उनका एल्गोरिदम इंडिया का नहीं है. हम लोग
भरा हुआ है, आप मार्केट जाओगे, you will get this blood measurement device in 10 rupees, 15 rupees, 20 rupees.
एक्यूरेसी इज मेजर कंसर्न.
Yeah,
तो
bed
सर
in form of bed. There are several devices. How you will be able to prove your nobility?
सर डिवाइस अवेलेबल है मार्केट के अंदर, वो सच है. पर डिवाइसेस जो वैलिडेट करते हैं मार्केट में है बहुत सारी अवेलेबल हैं, बट जो डेटाबेस क्रिएट करते हैं उसको बनाने के लिए वो इंडियन ओरिजिन का नहीं है. तो हम लोग क्या हमने ब्लड प्रेशर रिकॉर्डर बनाया जिसे हम ऑसिलोमेट्रिक वेवफॉर्म एक्सट्रैक्ट करके हमने डेटाबेस क्रिएट किया पहले, उसके बेसिस के ऊपर एल्गोरिदम डेवलप किया है.
Thank you, Amit.
Welcome.
कोई क्वेश्चन? Any question? No.
रेजिस्टिव प्रेशर सेंसर नहीं सर. रेजिस्टिव प्रेशर सेंसर लाइफ टाइम के लिए सर और रोबस्टनेस ज़्यादा होती है. व्हाट सर? एक्यूरेसी ऑफ प्रेशर सेंसर मार्केट में अवेलेबल या it generates about 100 millivolt for a 250 mmHg pressure. वो क्राइटेरिया चेक किया था सर हमने. नहीं सर है रेजिस्टिव ब्रिज स्ट्रक्चर के अंदर.
Okay, thank you. Thank you very much.
So next participant is Dr. Nirmal Kumar, and the topic of presentation is tungsten oxide based hydrogen gas sensors prepared by advanced magnetron sputtering techniques. दिया हुआ है सर, दिया हुआ है. This one.
Good afternoon, everyone. Myself Nirmal Kumar, and I am presenting tungsten oxide-based hydrogen gas sensors prepared by advanced magnetron techniques. So, as Professor Kornala already explained the importance of hydrogen, so I will continue from there because hydrogen is important. So, for the purpose of storage, transportations, and domestic uses, we need to take care about the safety. And for the safety purposes, because hydrogen is quite explosive, and we need sensors and detectors for that. So first, in our case, we gone through conductometric gas sensors. So it in the conductometric gas sensors, the resistivity or the conductance of the material changes when a target gas come in contact with the surface of the material. So here is a mechanism. So at higher temperature or above room temperatures, the oxygen ions are adsorbed at the surface of the material and form a depletion layer around the surface. So when we have hydrogen or another target gas come in contact with the material, it again provide the electrons to the material and change the electrical conductivity of the material by reducing the depletion region. So here are the challenges that we need to deal with during the formation of sensing devices. First, the sensitivity. The sensitivity should be higher. Then selectivity. It must be selective for particular gases. And interference of relative humidity. Humidity also reduce the sensitivity because it has also water, hydrogen in it. So, and the final one is low operational power. So usually sensors work on the higher temperatures, so we need to lower down the temperature of the sensor device to perform. And also it should be it should have higher response and recovery time. So there are some strategies that we started with. So first one is move towards the nanostructures. Second is introducing the catalyst on the surface, and then formation of N and P type heterojunction or N type heterojunction, and tune the oxygen vacancies. So I will discuss about these strategies which we have implemented in our research. So first we have prepared copper oxide nanoclusters. Copper metal is also a noble metal, kind of noble metal. So we deposited copper oxide nanoclusters by sputtering technique. So we have a cluster, gas aggregated cluster source where we produce the copper oxide nanoclusters about 7 to 10 nanometer of dimensions. And then we combine these nanoclusters with tungsten trioxide films. So as we increase the density of the nanoclusters on the tungsten trioxide films, we found that the response for hydrogen was increasing. So this is the response for pure tungsten trioxide film as deposited. And we increased the concentration of hydrogen in steps. And it was like a mixture of hydrogen, 1% of hydrogen in synthetic air. And as we introduced copper oxide nanoclusters, we found there is enhancement in the sensitivity. And further increase also gave us more improvement and more. And at the end, when we further deposit the copper oxide clusters, we found that response was completely opposite. So we came up with the strategy. So we were expecting that copper is P-type. Since copper is P-type and tungsten trioxide is N-type semiconductor, so it must have formed nano-sized heterojunctions on the surface. So and it is difficult for us with the limitation of facilities, it was difficult to verify from this geometry. So we came up with another geometry where we combined, where we deposited tungsten trioxide film on the half of the substrate and the copper oxide cluster on the another half. So after that, we found that in SEM, it is easily visible that this is the copper oxide clusters and this is the films. And at the center, we found both the layers. And when we measured IV characteristics, we found that it was forming PN heterojunctions there. So after using these techniques, we again go for an N-type heterojunction and change the combined material to copper tungstate. So we form copper tungstate by the process, by a two-step deposition process. So first we oxidize the silicon substrates and deposit copper tungsten trioxide over them, and then again deposit ultra-thin film of the copper oxide, say 5 nanometer, 10 nanometer, and 20 nanometers. And the deposition temperature was 400 degrees Celsius, due to which we were able to get copper tungstate on the surface of tungsten trioxide films. So we also did the reverse process, where we deposited copper oxide first and then sputter tungsten trioxide, and then decorated with these film with the palladium. And we found that at after stabilization at 200 degrees Celsius, we had two kind of structure of palladium. First, the palladium oxide film, and another palladium nanoparticles, metal nanoparticles. And here we can see these are the as deposited films, and this is the palladium oxide films or nano islands. And in between here, we can see the nano particles of palladium oxide. So after we measured the response, so we did without the palladium first. So we found that the response was good at higher temperature, say 350 degrees Celsius. So we found that for the lower portion of tungsten trioxide film or tungsten oxide film, because it was stoichiometric, so we used WO, and 5 means 5 nanometer and 20 means 20 nanometer of copper oxide. So we combined them, and we got best response for this film. And in humidity, we found the response was become worse. It was quite low. So we decorated them with the palladium film, as I discussed before. So at high temperature, again, the response in humidity was lower. This is for pure films, and at lower temperature. So here we were able to reduce the temperature to 80 degrees from 300 degrees Celsius. And here it was 0.8. It means like 0.8 nanometer of palladium film was deposited, which was optimized on 5 nanometer tungsten trioxide and 20 copper oxide. So these already form a bilayer, copper tungstate and copper oxide, and we deposited tungsten trioxide over palladium over this. And here we can easily see that the influence humidity was completely disappeared. So we got same response in humidity and dry air. So in that case, we were successfully able to reduce the interference of humidity. So this was the formation of heterojunctions again was the reason. And this is the mechanism when we deposited the palladium, like there is multiple heterojunctions. First, the copper oxide and copper tungstate, and then palladium oxide film with copper tungstate, and also the catalytic behavior of palladium support the selectivity towards the hydrogen, and also the PDO favors the adsorption of hydroxyl group on the surface, and this adsorption reduce the influence of humidity. So after this, we came up with another technique. So here we tune the stoichiometry by tuning the oxygen vacancies by varying pulse length during the deposition by using high pimps. So we found that by deposition, and we stabilize again at 200 degrees Celsius, we found that due to the oxygen vacancies, we have scope of further oxidation of the material, and it changes the crystalline structure. So I would like to, we got same response and it was enhanced. So where we have monoclinic phase, we found like almost 12,000 times improvement. And I would like to conclude there. So we prepared the nanostructures and use these strategies, and these strategies can be, like nanostructures and everything can be prepared by sputtering technique, and also we can tune the oxygen vacancies by high pimps. So thank you for your kind attention.
Thank you. Any question? What was the source material in the sputtering process you have used?
So we have used, we have a system with 2 magnetron targets. One was copper and one was tungsten.
What was the environment inside the
It
chamber?
It was vacuum.
Huh?
Vacuum. So we have produced plasma there, and we deposited at like 10 raised to the power minus 6.
Okay, thank you. Thank you very much.
Not like during that time we weren't able to like perform, but yes.
Ammonia or CO,
yes. So
like
we have we did we did test our samples for nitrogen dioxide, ammonia, and carbon monoxide with the collaborators in Italy.
So, and secondly, suppose because hydrogen, palladium is well known for this purpose. Palladium tin oxide is well known for hydrogen sensor.
Yes.
So how your sensor is better than that?
So we have like successfully reached to lower temperatures. So one of our specimen was working at room temperature as well, and but the sensitivity was too low, and we have issue with stabilization. So we didn't consider it like that well. But yeah, because I have completed my PhDs, but yeah, it is still good idea to.
IV characteristics, band gap. Because you're talking about heterostructure.
Yes.
This is heterostructure. What is the change in band gap?
So we have did I-waste characteristics for this.
When you are exposing to hydrogen gas, did you find any change in the
In the band gap? No, sir. We didn't do as I described earlier, we did conductometric gas sensors, not like optical we didn't test optical properties during the hydrogen.
That is just to prove whether it is a hydrogen is absorbed on the surface.
Yes.
Because copper oxide also gives you good sensing.
Yes, sir. Copper oxide also.
is also a good sensor.
Yes, sir.
So
But
how will you justify whether
by
it is only
combining,
electrostructure which is playing a role.
yes, by combining them, we were successfully
prove it
able
actually,
to
that will
enhance
see that
the.
part.
Okay, thank you. Thank you very much.
So next participant is Dr. Muskan, and the paper title is Plant-Based Microbial Fuel Cell and Hydroponics, a promising combination for sustainable energy and crop production.
Good afternoon, everyone. My name is Muskan Raghav, and I'm here to present my findings on plant-based microbial fuel cell and hydroponics, a promising combination for sustainable energy and crop production. So, as we all know that depletion of fossil fuels are increasing day by day, so there is a need for more affordable and globally feasible and eco-friendly energy resources. So for that purpose, we all know that there are microbial fuel cells available, but microbial fuel cells till date have not been able to reach to that point where it can compete with the fossil fuel energy generation. So because of several challenges, the first challenge is that the swift consumption of the substrate by the microorganisms, which ultimately leads to the halt in power generation, and the second is that it produces low voltage, because of which it is not suitable for commercial purposes. So here is a modification of microbial fuel cells in which the substrate is provided by incorporating the plant. So what happens is that basically when plant utilizes photosynthesis, it uses the solar energy to produce some hydrocarbons. So not all hydrocarbons are utilized by the plant for its growth or metabolism. Some of them are released into the soil through root exudation process. So this plant-based microbial fuel cell utilizes the phenomena in which microbes degrade those root exudates present and releases electrons and hydrogen ions. So these electrons are collected through external circuit using a electrode made up of which is anode, and then the H plus ions travel through the medium to the cathode, which is present in the interacting with the air. Here H plus ions interact with oxygen and forms the water. So this is the principle of plant-based microbial fuel cell. So workflow is just we constructed it using various design criteria, then assembly, data collection, and then optimization was done using various statistical techniques. First is fabrication. The first table shows that we analyzed a lot of plants on the basis of different parameters, such as what photosynthetic pathways they utilize, is it perennial or not, are they able to sustain the waterlogged conditions, vegetative phase hardness. So we analyzed various plants and came out and Canna indica came out to be the most suitable plant for this purpose, and we chose soil as the source for microorganisms. So, and for next is for electrode material. The electrode material has been a challenging task. First, initially we opted carbon with stainless steel mesh, but it was not feasible. Then graphite rods, they were expensive, and carbon felt what we ordered were not conductive. And then we settled down to carbon cloth, which was highly conductive. It provides high surface area. It is chemically stable, durable, and flexible. So here is the results of current production. From one plant, we were able to obtain 716 millivolts and 0.73 milliamperes. So by multiplying it, we can get the power, which came out to be 228 milliwatt per meter cube. So if we compare with the other PMFCs that are listed in this table of that has been taken from a review, so we can say that we obtain power density more than 90% of the available plant-based microbial fuel cells. So if we got the current density, now we wanted to increase it. So for increasing, we applied various optimization techniques. So the most common approach for optimization is first to screen out what are the most significant factors that contribute to bioelectricity generation. So for that purpose, we implemented Plackett-Berman design for 7 parameters that are plant type, EC, pH of media, area of the electrode, membrane, distance between the electrodes, and culture from where the microbes are to be taken. So after a total of 12 experiments were performed using the Minitabs software. So this yield has been obtained from the experiments, and on the right hand side we can see the graphs from which we can say that that is the plant type is the most significant factor that affects the bioelectricity generation, and the order is plant type, then pH, area, membrane, culture, and distance. EC had a minimal role, here we can see. Then we obtained the most significant parameters. Now we wanted to obtain the interactions between the parameters, and for that we performed RSM, that is response surface methodology, for which we performed around 20 experiments using 3 parameters, pH, area, and distance. From the model summary, we can say that the higher R square value, we can say that the model is a good fit for the data, and here is the regression equation from which we can find out the yield by putting these values. Here we have the linear terms, we have quadratic, and the interacting terms as well. And these are the graphs that show it as in the main effects graph, we can see that lower pH performs better, as lesser pH will give more H plus ions, because of which we'll have a higher redox gradient. And area, if the area is higher, the yield will also increase, as there will be more microbial attachment sites available. And then if distance between the between the electrodes was the minimum obtained, was the minimal yield, but if the distance between the electrodes will be lesser, then the bioelectricity production will be higher, as there will be less resistance. And from the Pareto chart, we can say that A and B, that is pH and area, combined will give the best results. And a bit extension was done by using machine learning. Here we have implemented a simple linear regression supervised machine learning algorithm, where if we enter the values of pH, area, and electrode, we can get a predicted yield value. And similarly, the data has been shown over here. In conclusion.
Any question? Any role of phytochemicals?
No, sir, root exudates, present in roots. Yes, sir.
This is your first year or second year PhD program?
This is PhD, M.Tech.
Huh?
M.Tech last year.
M.Tech. Okay, okay. Have you published any paper?
No.
No. Thank you, thank you, thank you very much.
So using multimeter. Yes, sir.
Yes, sir. Sorry, sir. So measure using multimeter, what voltage, what amperes, what current production is there. No, sir, electrodes are used for that. Carbon felt. Not on the surface, sir, on the pot, if you can say. So using multimeter.
In the top electrode, what is the metal?
Sir, yeah, if we can.
The top and the bottom? Okay. No.
Yes, sir, 400 लिया था हमने. So current भी नहीं sir, current भी किया. No sir, we didn't put any. Yes sir, directly. Yeah, yes sir. Yes sir, yes. So because lesser the pH, there will be more hydrogen ions present. So more hydrogen ions will increase the redox potential between the electrodes. Yes sir, yes sir. So if there is higher surface area, there will be more attachment sites for the microbes. So if there will be a better, more microorganisms present, so they will perform, they will increase the efficiency. If I found the optimum pH to that is why optimum range is to be there. I found 5.5 to 6.5 range, which supported plants and microorganisms both. Yeah. Not for all. I worked on one.
So next participant is Preeti, and paper title is Recovery and Analysis of Glass from Waste Solar PV Modules. This one.
Good afternoon to all of you. First, I would like to thank NSUT for giving me an opportunity to present my research work. I am Preeti. I'm working under Dr. Sushil Kumar from CSR NPL. So, today I will be giving presentation on recovery and analysis of glass from waste solar PV modules. So, moving on. Yeah, this is the outline of my presentation. I will be touching upon these topics and starting with the introduction. So we all are looking for the renewable source of energy. So these are a few examples of the renewable energy sources. So among these, today, solar and photovoltaic industry is the fastest growing industry. And India has installed more than 65 gigawatt capacity at the end of 2022. And India has targeted 300 gigawatt installation with the solar PV itself at the end of 2030. So these are the different generation of solar cells have been commercialized so far. So in first generation, we have a crystalline silicon solar cells. So this is a wafer-based technology. We might have seen these blue color silicon wafers type of rooftop solar cells somewhere. So in this technology, we use silicon cells, silicon wafers as a absorber material. And in second generation, we have amorphous silicon technology. This is the thin film based technology. So crystalline silicon solar cells are commercialized, and it has been there from since solar cells were invented from like 1954. So it is very mature technology. And thin film based are very less. These are only 5% of the market share till, and they include like cadmium telluride solar cells, copper indium gallium diselenide solar cells. In third generation, we have copper zinc tin sulfide solar cells, disensitized solar cells, quantum dot solar cells, polymer solar cells, perovskite solar cells. But these are not commercialized so far. So moving on to next slide, why we need to recycle solar modules. We know that solar cells contain some toxic materials in it, like lead, cadmium. So if after end of life, if they are not properly disposed of, they could cause harm to the human health. So we need to take care of these modules after their end of life. And it is estimated that these 5 countries will produce 78 million tons of the waste after 2050. It is estimated. And India is among one of these top 5 countries. So with the help of recycling, we can also reduce the landfill cost of these waste modules. And as we all know, that silicon solar cells is quite costly. So with the help of recycling the materials, we can reduce the cost further for the new devices. So in my research work, I mainly focused on the thin film technology. Starting with the amorphous silicon solar PV modules recycling, I have taken this module. With the help of mechanical treatment, I have extracted the aluminum frame and junction board separately. Then with the help of thermal treatment, I have extracted these layers, back contact, encapsulant material, and the back sheet. And after this, with the help of chemical treatment, I have extracted this TCO coated glass, which is very important for the thin film technology. All the layers are deposited for the thin film technology. All the layers are deposited on TCO coated glass, transparent conducting oxide glass, which allows light to enter into device while maintaining the electrical contact. With this, moving on, we have separated all the components that we use in the manufacturing of amorphous silicon thin film module. These are the different component here. I have shown that. And here in the result and discussion, I have characterized the extracted TCO coated glass in comparison to the commercialized TCO material. And we have found that the extracted TCO coated glass shows quite similar property as in comparison to new TCO coated material. And we can see that these peaks are quite similar to the commercialized one. The reference TCO coated glass is commercialized TCO coated glass, and the extracted TCO coated glass shows good transmission as well, more than 80% transmission in the visible range. So in conclusion, we can say that the extracted TCO coated glass has a potential to its reuse in the new devices. So I have also done the recycling of the CDT module, which we have procured from the NICE, National Institute of Solar Energy, Gurgaon, and we, with the help of all the treatment, mechanical, thermal, and chemical, we are able to extract the TCO coated glass from the cadmium telluride thin film solar modules as well. And it has some also laser subscribe line which used for the monolithic integration of the cells. And it can further reduce the cost to further laser scribing cost we can reduce, and it shows good transmission, more than 90% transmission in the visible range, and its structure is very similar to the commercialized TCO coated glass as well. And nowadays, like we are also collecting the waste perovskite silicon solar cells laboratory modules. Like many researchers are working on the perovskite solar cells recently, but they are not stable. Like after a few hours, their efficiency degrades, and they use very toxic material such as lead in that, and they just throw in the dustbin. And I have collected all these modules from the NPL laboratory only. And I was able to extract the patterned ITO coated glass from the waste modules, and it shows very good sheet resistance, quite comparable to the new one, and transmission as well. These are the parameters we have observed for the pattern extracted ITO glass. Yes, sir.
1 minute more.
Okay, sir. Okay, sir. So, extracted TCO coated glass shows very good morphology as well, as shown in the figure. In our lab, we are also doing the recycling of the crystalline silicon solar panel as well. And what we used to do is the crushing the modules first, and in earlier we used to crush the module, and in the pieces we were able to extract the glass. But nowadays we started to extract the intact glass of the crystalline silicon solar modules as well. And we have extracted this glass from the two methods, thermal and chemical. With the help of both methods, we are able to successfully extract the glass in the intact form. Thank you so much, sir.
Thank you very much.
Yes, sir.
Any question? No. My simple question is, in XRD pattern, what is theta and 2 theta?
Sir,
What is 2
this
theta?
2 theta is a Bragg's angle.
Huh?
Bragg's angle.
Bragg's angle
Yes.
is 2 theta.
Yes, sir.
No.
Diffraction
No.
angle.
This is the angle of diffraction.
Yes, sir.
Okay.
Angle of
You can
diffraction.
go.
Yes,
Hello.
sir. Thank you, sir.
Hello. I'm having one question. Excuse me. One question. You had uses the TCO glass for the transmittance power. If we just talk about the pyramidal lens, that is having, I think, the highest transmittance power.
Yeah, I have extracted the TCO coated glass from the already existing modules, thin film modules.
But you had told that that is having the transmittance power, high transmittance powers.
I have compared the extracted TCO coated glass with the new TCO coated glass that is available in market.
Okay.
For the comparison.
Are you having any idea about the pyramidal lens if you choose the pyramidal?
I have not worked on the pyramidal lenses.
Okay, thank you.
So next participant is Deepa Kumari, and paper title is Non-Enzymatic Electrochemical Glucose Biosensor Based on Copper MOF Coated on Graphite Sheet.
Very good afternoon to all the respected session chairs, respected faculty, and all the audience. Today I will be presenting my work on non-enzymatic electrochemical detection of glucose based on copper MOF coated on graphite sheet. So, myself Deepa, I'm pursuing PhD under the supervision of Professor Dr. Chaya Ravikant ma'am at Indira Gandhi Delhi Technical University for Women. So today I would be presenting my work on this topic. Okay. So basically, as we all know, that the diabetes cases are rising day by day. So my research is on this glucose biosensing. These are the basic trends of the glucose biosensing. As you all see, the first commercial biosensor was reported in 1975, and then these are the various generations. That is the fiber optic biosensor came in 1982, and then the present day, that is the handheld biosensor, came in 1992. So when you're talking about the glucose biosensing, basically we focus on the electrochemical detection of glucose. That is basically of two types, that is enzymatic and non-enzymatic. When you're talking about the enzymatic, the glucose oxidase enzyme is being used as a catalyst for the oxidation of glucose, and it is often coupled to non-structured metal oxides, that is such as zinc oxide, titanium oxide. And when you're talking about the non-enzymatic detection, basically we're using the nanomaterials or the nanoparticles as well as the latest metal organic frameworks as the nanoenzymes for the detection of the glucose. Further, when you're talking about the basic glucose detection mechanism, is basically we're having a bioelement which is detecting the analyte and the transducer which is converting the incoming signal. That is basically the signal output can be electrical, optical, or physical, depending upon the mechanism which is used. And this is the basic redox reaction which is taking place for glucose detection in the presence of glucose oxidase. That is, glucose is getting oxidized to gluconic acid, and there is a generation of electrons which has been detected by all the electronic circuitry. So basically, presently the commercially available glucose sensors, there is a certain limitation. That is, first of all, the glucose oxidase enzyme is very costly, and it loses it, and secondly, it loses its catalytic activity at higher pH, like greater than 8 or lower pH, and it is affected by surfactants, and it has poor environmental stability, and also there is a complex GOX immobilization. So it's better, the research which is going on is towards the non-enzymatic detection, that is the present 4th generation glucose biosensors, which in this work I'm focusing on the metal organic frameworks. Basically, the metal organic frameworks are they are the porous materials that are constituted by the metal ions with the which is surrounded by the organic ligands. That is, this is basically the structure of MOF, and it has certain properties like it has high surface area and porous crystalline structure, high porosity, and high flexibility and chemical stability. And it has a very easy fabrication techniques like listed here, like sorbothermal, electrochemical, and microwave assisted and hydrothermal. And it has a certain flexure capacity of the MOFs that it can imbibe the molecules, external molecules, and which helps in the detection of glucose here in my work. Like suppose when you are talking about the mechanism of glucose detection, in the presence of the glucose molecules, what in this structure, as you can see, the yellow balls kind of structure, they are the metal ions, and the blue lines are the linker molecules. If you're talking in a general way of MOF. So here, this metal can be anything like copper, nickel, or cobalt. So whenever in the presence of glucose molecules, the glucose molecules get undergo the redox reaction. That is, the glucose is converted into gluconolactone at these metallic centers, and the metal is also getting reduced and oxidized. That is basically the redox reaction is taking place at these points, so which is helping in the detection of glucose. That is a general phenomena which is taking place in non-enzymatic detection. So here in this work, I'm focusing on copper MOF Why I have chosen copper MOF? Because copper MOF helps in fast kinetics of electrochemical glucose detection. It is non-toxic, it is low cost, as well as it is having a lower redox potential, and it can give the oxidation of glucose at lower potential as compared to the previous work. So that's why I have focused on copper MOF here. And first of all, for this fabrication, we have synthesized copper MOF using room temperature steering synthesis. That is being shown here. In this, we have taken the benzene tricarboxylic acid, that is H3BTC, as our ligand molecule, and then we have used the copper nitrate as our precursor, and we have done the solvothermal synthesis of copper MOF, and finally the catalyst which is used is the triethylamine. So it's finally, we obtain the blue crystals, that is the copper MOF, by this synthesis, and the basic structure we obtain by this is like this 28-membered ring we obtain with connections with 6 rings, thus to form a 2D sheet. So this is basically the structure of the copper MOF we obtain after the synthesis, which I have taken from some literature review papers. So for confirming that the synthesis has been done, so we have done the FTIR spectroscopic analysis of this material, and we have got these respective peaks at those respective bonds, like availability in that material, like C double bond O at 1633 per centimeter, and then we have C double bond O stretching of the benzene tricarboxylic acid structure that is previously I have shown, and these respective peaks I have got which confirms the synthesis of copper MOF. And similarly, for further confirmation, we have done the SAM analysis also of the material, that is at the 5 and the 10 micrometer. We have got these structures, cuboidal shaped structures, that is a cluster of particles can be seen. How it can be done, much more specific figures can be taken like by FESM at nanometer level. So we got these structures which clearly show cubic crystals, finely arranged, that is truncated octahedral structures of copper MOF. So this shows that the copper MOF structure has been, we have obtained it, and it's quite significant also, and we are seeing the energy dispersive X-ray spectroscopy has also been done, and we are getting the respective peaks of copper at these energy levels, which clearly show the availability, the presence of those components like carbon, nitrogen, oxygen, copper in the material, and this shows its elemental composition also. We had also done the elemental mapping also, but I have not shown the pictures here, but we have done how the presence of the materials over the materials, different sides of the material. And also we did the thermogravimetric analysis of the material that shows that the material is stable till 200 degrees C, and after that it starts degrading. This shows the long-term stability of the material as well as the range to which the material can be used. Since it is stable at 200 degrees C, it is quite clear that this material can be used for the room temperature applications and for the fabrication of glucose biosensor. Because most of the glucometers which are using in the present generation or present day glucometers, they are working at room temperature. So it's quite significant that it is quite stable till 200 degrees C, and after that starts degrading this material. Then further, in order to study the glucose biosensing, we did the electrochemical characterization by this technique, and we got these respective results. It is quite clear that in the presence of glucose, there is a sharp rise in the current. This peak is being denoted by the oxidation of glucose. That means the glucose has been detected in the presence of this material. Actually, we prepared the electrode using the copper MOF over the graphite sheet, and then we studied its characteristics. Like at different scan rates, we studied how the current is increasing with the scan rate. So it is clearly accepting, or we can see clearly showing a linear relationship between the current density and the scan rate. That means it is a highly electroactive material. It's quite significant electroactive material because it is showing the change in the current with the scan rate. So the possible detection mechanism we analyze can be shown that how the reaction is taking place. The copper, the metal, which is first getting reduced, then it is getting oxidized. And similarly, the glucose is getting oxidized and giving electrons. So these electrons are being detected at the end, which is giving the increase in the current. So similarly, we did at 1 millimolar glucose solution, And then we did different concentrations we did, like 0 to 15 millimolar. We saw these change in the current. So, and we plotted this current density plot with the concentration. So with this, okay, sir. So we got the sensitivity around this 137 microampere per millimolar. And the LOD of, that is the limit of detection, is 0.016 millimolar. So basically the detection range is around 0 to 15 millimolar. So when I compared with this, all the research work which has been done earlier, so the basic speciality of this my work is that it is having a wider detection range, that is 1 to 15 molar, and it is quite lies in the physiological range. That is in normal glucometers like 9 mg per dl to like 400 mg material. So it can be a prospective material for glucose sensing if we focus on this research more. So this is all my work regarding copper-MOF. Thank you so much for your kind attention. Thank you so much.
I have one question.
Yes.
Suppose I want to make a solid solution, copper into nickel, copper into aluminum, and copper into copper. Which one will be easier to make a solid solution?
Copper.
Copper into copper, copper into aluminum, copper into nickel.
Sir, actually, I'm presently working on.
No, you are making a material.
Yes, a single MOF.
Yeah.
So we are also working on bi-MOFs also.
What are the parameters on which you pay your attention when you are synthesizing this material?
They should be quite stable also, and when they're combined, they should give a very stable material, sir, basically. And we are focusing on that. We're working on that.
Any question from the audience? Any question? No. Okay, thank you.
Thank you, sir. Thank you, sir.
At last, I would like to invite Professor Ranjana Jha to facilitate Professor O.P. Thakur with a certificate of appreciation for chairing this wonderful session. As we are getting late, we'll have 10-minute break for tea. So all are requested to be gather on time. Thank you. Those who have not submitted their presentation, please submit it. Thank you, ma'am. Thank you, sir. As we are getting late, We'll have 10-minute tea break. Please be on time. Thank you. अभी आ रही है।
The beauty of this device is here plasma sheath is formed. What is plasma sheath? In fact, plasma sheath is different from bulk plasma. In case of bulk plasma, Poisson utility condition is satisfied. Poisson utility condition says ion density approximately equal to electron density approximately equal to plasma density. But in case of plasma sheath, this Poisson utility condition does not hold. In this case, ion density is slightly greater than the electron density. So because of this density difference, there is a potential difference, charge difference and charge difference than potential difference, and this potential is responsible for producing of electric field, and this electric field is responsible for the for obtaining vertically aligned carbon nanotube or graphene. So this is beauty of this device. Using this device, we can get vertically aligned carbon nanotube as well as graphene. Graphene is this kind of structure, in fact, a single atomic plane of graphite, and is sufficiently isolated from the environment to be considered freestanding. So graphene is a one atom thick planar sheet of sp2 bonded carbon atoms that are densely packed in a honeycomb crystal lattice. And the name graphene comes from graphite plus ene, that is graphene. So this is in fact the structure, single sheet of carbon atoms, mother of all graphitic forms, and different configuration leads to different kind of structure. For example, zero-dimensional buckyballs, it can be rolled into one-dimensional nanotube. It can also stay into three-dimensional graphite. So this is in fact 2D graphene sheet. It can be rolled into single wall carbon nanotube. It also can be rolled into multi-wall carbon nanotube, just like a coaxial cable. Graphene carbon nanotube hybrid synthesis techniques. In fact, these are the techniques that is, for example, chemical vapor deposition. And chemical vapor deposition, here we are considering plasma enhanced chemical vapor deposition, RF plasma enhanced chemical vapor deposition, and microwave plasma enhanced chemical vapor deposition. So formation of one-dimensional carbon nanostructures in plasma enhanced chemical vapor deposition occurs on catalyst substrate surface at a lower temperature than in the conventional chemical vapor deposition process, which is a major advantage of plasma enhanced chemical vapor deposition. In fact, carbon nanotube graphene hybrid composite made of CNT and graphene, offering high surface area framework of carbon nanotube and also high edge density of graphene sheets. Rule of plasma, as I have told you, these plasma-based devices, the advantage of plasma-based devices, we can get vertically aligned carbon nanotube graphene as well as graphene carbon nanotube composite. This is a schematic diagram of this composite or hybrid kind of devices, graphene black carbon nanotube composites. Here this is silicon substrate. So using magnetron spattering, we can grow catalyst film, for example, iron, cobalt, nickel, and using thermal chemical vapor deposition, we can get carbon nanotube, and using microwave plasma enhanced chemical vapor deposition, we can get this graphene black on CNT. So this experimental schematic diagram is similar to our theoretical model. Now another experimental result, Dang et al. Have studied the field emission properties of plasma enhanced chemical vapor deposition grown few layer graphene on carbon nanotube array, or few layer graphene array on silicon substrate, or few layer graphene array on diamond like carbon in comparison with that of edge grown carbon nanotube array. So these are field emission current as a function of field between two electrodes for different structures, and this is in fact field emission current as a function of time for different kind of structures. Another, this QI et al. Have reported the effect of amount and size for a few layer graphene grown on the walls of carbon nanotube array, brought about by controlling total gas pressure and growth time in a plasma enhanced chemical vapor deposition process on the field emission property for carbon nanotube array. The beauty of this experiment, they have found that the density of few layer graphene increases repeatedly from the top to the end of carbon nanotube with the total gas pressure decreasing. So we have compared our theoretical result with these experimental observations. Another experimental observation by V.D. Bankar et al. Here, this one, in fact, multi-wall carbon nanotube and multi-layer graphene grown by microwave plasma enhanced chemical vapor deposition technique and estimated its field emission property. Here, this multi-layer graphene on multi-wall carbon nanotube turn on field, this one, and this is field enhancement factor. And after nitrogen doped multi-layer graphene on this one multi-wall carbon nanotube, turn on field reduces what field enhancement factor increases. So this is due to by dropping nitrogen, density of state near the Fermi level increases. Consequently, the emission of electrons in this field enhancement factor increases. Another experimental result also by increasing the concentration of nitrogen doping, the field enhancement current increases. So another experiment means by this experiment, this schematic diagrams indicate that this process is defect guided. In fact, so this defect guided process we have followed in our theoretical model. So this is in fact our published paper, effect of plasma control parameters on the growth of nitrogen doped nanocone vertical graphene hybrid theoretical investigation. And this is my PhD student Shruti Sharma. She has done extremely good work in this paper, and this paper was published in plasma chemistry and plasma processing in the year January 17, 2022. And impact factor of this paper is generally 3.55. So so from this onwards, we would like to present our published work. So here we have considered this model. In fact, three type of neutrals. This one type A, type B, type C, and then ions type A, type B, type C. Type A hydrocarbon, for example, acetylene, methane, CH3, and B type hydrogen, and C type nitrogen for nitrogen doping. And these are the ions for type A and type B and type C. So here again plasma sheath is formed, this whole process in presence of plasma, and plasma in presence of plasma sheath, in fact nitrogen doped nanocone vertical graphene hybrid is thus produced in the plasma sheath rather than in bulk plasma, where the microscopic electric field near the surface accelerates the ions toward the plasma exposed surface. This is in fact HELOC, and these are the this is plasma sheath and hydrogen species, then hydrocarbon species, then nitrogen species. So initially saturation of catalyst nanoparticle takes place by the adsorption, diffusion, and sticking of hydrocarbon species. Once the saturation of catalyst nanoparticle is reached, nucleation of nanoHELOC on its top takes place by additional carbon atoms, both vertically and radially, until the catalyst nanoparticle is fully covered. So nanoHELOC of increased height and base radius here. Base radius and height with a small slope angle is obtained, and which leads to weaker chemical sputtering or etching. Consequently, carbon species deposition takes place during the preliminary growth stage of carbon nanocone. Now, with the increasing deposition of carbon species, slope angle of nanoHELOC increases and chemical sputtering or etching becomes more effective, and the rate of deposition decreases. When deposition of carbon reaches equilibrium with the etching of carbon, so stable nanocone will be formed. This kind of. So these are in fact nanocone, and the defect formation occurs because of plasma sheath. So carbon atoms generated on the nitrogen doped carbon nanocone surface on account of several surface processes get captured by defect present on the nitrogen doped carbon nanocone surface, which then diffuse and agglomerate to form carbon clusters. Now these carbon clusters at the defective side diffuse and collide with each other, forming the graphene island. This kind of, and subsequently these graphene islands amalgamate or stick with each other to form large graphene island or flat graphene sheet with respect to carbon nanotube surface like this. So during the amalgamation of these graphene islands, internal tensile force FT, this one build up at the graphene island boundary, which may tends to align the upper edges of these graphitic layers in the direction normal to the nitrogen doped carbon nanocone surface. Under the action of resultant force, this one, resultant force and electric force due to plasma sheet, that is Fe and Fe, and continuous dissociation and diffusion of hydrocarbon and carbon species respectively, graphene sheets grow like plant leaves erected on stem carbon nanocone. Now, these are the plasma sheet equations, that is the equation of continuity for ions, equation of continuity for electrons, and then ion momentum equation, electron momentum equation, and this is Poisson equation using Maxwell first relation divergence E is equal to 4 pi rho. So, these are the plasma sheet equations. Then growth equation.
Hello, sir.
Hello.
Yes,
Yeah,
yes, you are
growth
audible.
equation of
Yes.
nitrogen doped nanocone. So again, volume of cone is 1 by 3 pi r square, simple, basic. So this is in fact R is the base radius and R1 is the radius of the tip. So this is in fact growth rate equation of nitrogen doped nanocone. These are different terms. This is in fact biometric growth rate of nanocone, and this term indicate etching term, which decrease the growth rate of nanocone, and this term indicates surface diffusion and incorporation of carbon monomers along with surface diffusion of carbon cluster with the various energy barriers over nanocone surface. And in fact, this term A in fact, this sticking of neutrons of type A and C over nanocone surface. Moving over here slide. Okay, next defect formation on nanocone surface. Since the growth of graphene sheet over the carbon nanotube surface is defect guided, and we try to develop a model equation representing the formation of defect over the nitrogen loop carbon nano cone surface by accounting the power balance at the surface of nitrogen loop carbon nano during its growth with the plasma of ethylene and ammonia. So this is in fact power balance equations. These are the different terms, that is neutralization of ions collected at the nitrogen doped carbon cone surface, and this term indicate ion sparkling, and this indicates surface diffusion and incorporation of created carbon species over nitrogen doped carbon cone surface, and this indicate etching of the nitrogen doped carbon cone surface by hydrogen, and this entire term indicate These, in fact, A, B, C means A type, B type. A type means hydrocarbon, B type means hydrogen, and C type means nitrogen containing. So this indicate power transfer to nitrogen group carbon nanocone surface due to its interaction with positively charged ions, neutrals, and electrons. These are the symbols and then explanation. In fact, area of nanocone, which is the tip area at the tip, and plus this curved surface along the length, that is pi RL of a cone. And this is H is length of nanocone, R1, I have already explained base radius and tip radius of it. This is in fact this neutral collection current over nanocone tip and curved surface. This at the tip, neutral current, and at the curved surface. This indicates the flux of impinging neutrals and positively charged species. And these terms indicate ion collection current over nanocone tip and curved surface. Then potential at curved surface of nanocone is given by this expression, and this in fact positive ion density in the plasma sheath, and this one in fact static potential inside the plasma sheath. Lambda D is the Debye length in plasma. So this J at tip and J at curve, electron collection current over nanocone tip and curved surface. Then rate of growth of hydrogen radicals over nanocone surface. This is in fact again this in dot indicate this is time derivative. These are the expressions and then explanations, complicated expression. Then rate of growth of carbon species over nanocone surface. And these are expressions and explanations. These are in fact values of symbols. Growth rate equation of graphene island. In fact, growth rate is graphene island of radius RGI growth relating to rate of change of area, that is nanometer square per second of graphene island. This is in fact area of graphene island as a function of time. So this is complicated expression. So this first term indicates the surface diffusion and incorporation of carbon monomers into the defective sites at a nanocone surface. And this term indicate accumulation of neutral atom of type A and C on the graphene island. And this term indicates surface diffusion and incorporation of carbon clusters. And this term indicates surface diffusion of graphene island. Then this, in fact, JIG, again, this is graphene ion collection current on the surface of graphene island. And this indicate neutral collection current on the surface of graphene island. These are the symbols and meanings of different symbols. This is growth rate of nitrogen grouped vertical graphene sheet over nanocone. Here we have considered three dimensional, that is L, GR means length of graphene, AG means height of graphene, and TG, this T means thickness of graphene. So in height and thickness, maximum change occurs and length is almost constant. So that's why we have taken it out. And we have considered time dependent of height and thickness. And this is in fact right hand side, we have balanced this equation. Then this indicate ion collection current at the surface of nitrogen group vertical graphene. Again, this is current density NEV kind of. This is in fact density. Then this is A area. In fact, length into thickness. This is again area. So this is current density kind of expression, ion collection current at the surface of nitrogen group vertical graphene. And this is in fact neutral collection current at the surface of nitrogen group vertical graphene. These are the symbols pertaining to graphene and the explanations. This is balance equation of electron density. Again, this dot indicates this is time derivative. So this is in fact rate of gain in electron density on account of ionization of neutral atoms. And this minus, this indicates decaying rate of electron density due to electron ion recombination. And this term indicates electron collection current at the nitrogen group carbon nanotube vertical graphene surface. Beta J is the coefficient of ionization of constituent neutral atoms due to external agency, and alpha as a function of electron temperature. This indicates coefficient of recombination of electron and positively charged ions. Gamma is the sticking coefficient of electrons. This is balanced equation of positively charged ions. We have considered three types of ions: A type, B type, and C type. Then balance equation of neutral atom, again three types. This is dot indicate time derivative, A type, B type, and C type. And in fact, experimental, we have used experimental parameter for calculating the equations. So we have done calculation of these coupled equations. We start from plasma sheet equations to all these equations using Mathematica software. So these are the parameters we have used in the calculation, that is electron number density 10 raised to 10 per centimeter cube, electron temperature, ion temperature, neutral temperature, substrate temperature, neutral density type A, and neutral density of hydrogen, and then SCN neutral density, neutral density type C, then ion density type A on hydrogen ion density, then NH3 ion density, NH4 ion density. So these parameters we have used in the calculations. So these are the result of our calculations, theoretical results. That is the effect of change of total gas pressure on the growth of nitrogen loop carbon nanocompound vertical graphene hybrid. So here ion energy as a function of total gas pressure for different ions. This clearly indicates this ion energy of the ions decreases with total gas pressure. And this in fact chemical sparkling yield as a function of hydrogen ion energy. So this clearly indicates this increases with hydrogen ion energy. So pressure increases is accompanied by decrease in the plasma sheet width and electron mean free path, resulting in increased collision among electrons, neutrals, and ions. Ions lose their energy faster. Increasing energy of bombarding hydrogen ions at normal angle of incidence on the growing nitrogen doped
Hello, sir.
nanocompound. Hello.
Sir, we are running late, so if possible, can you sum up in 2-3 minutes?
Okay. We are presenting our result also. Result only. So number density as a function of time for different ions, for example, NH3 ion and hydrogen ion and NH4 ion. So this clearly indicate for different total gas pressure. So this is in fact 1 means 5 torr, then 1.2 torr, and 950 millitorr. So it means 5, 4, 3. This increasing. So this total gas pressure, this increase means number density of these ions decreases. And then time variation of nitrogen loop nanocone height, and then nitrogen loop nanocone tip diameter, and then in fact nitrogen loop nanocone, this is in fact surface concentration of carbon in increasing with total gas pressure. This in fact by increasing total gas pressure, the surface and concentration of carbon increasing. Another very interesting result is this is in fact linear density of defect as a function of time for different gas pressure, and then vertical graphene sheet height as a function of time for different gas pressure. Here vertical graphene sheet thickness as a function of time for different gas pressure. So this indicates by increasing gas pressure, this linear density of defect increases, and vertical graphene sheet, this height also increases, and in fact vertical graphene sheet thickness, this also increases by increasing total gas pressure. This is another result effect of change of input power on the growth of nitrogen loop carbon nanocone vertical graphene hybrid. So ion energy as a function of power, and this indicates number density as a function of time for different power, and this is number density as a function of time for different power. So this indicates in fact power this indicate this 3 to 1 means the power increases 3, then 2, then 1. So by increasing power, this number density increasing. This is also surface concentration of carbon ions as a function of time for different plasma power. So this nitrogen loop carbon nanocone height as a function of time for different power, and this also tip diameter as a function of time for different power. So by increasing power, so this S is surface and concentration in fact decreases, and height of nitrogen loop carbon nanocone also this in fact this decreases, and this tip diameter also decreasing. So this in fact then field emission, we have estimated field emission current of this hybrid structure, and this indicates field enhancement factor as a function of plasma power. So field enhancement factor decreases with plasma power. So here we have a estimated field enhancement factor. In fact, in case of graphene, field enhancement factor is given by the ratio of the height of graphene sheet to the thickness of graphene sheet. And in case of carbon nanotube, field enhancement factor approximated by the length of carbon nanotube to the radius of carbon nanotube. But in case of hybrid, we have estimated in this way. This nitrogen loop carbon nanocone vertical graphene is given by field enhancement factor of nitrogen looped carbon nanocone into field enhancement factor of vertical graphene. So we have estimated field enhancement factor in this way, and we have found that field enhancement factor decreases with increasing plasma power. We have compared our all these theoretical calculation, theoretical results with the experimental observations. And these are the application of this hybrid material. We can use as a field emitter, we can use for lithium-ion battery, for fuel cells, gas sensors, supercapacitor, photoconductors, transparent conductors in space electric propulsion systems. So these are the application of this kind of hybrid or composite materials. This is our group. These are PhD students. In fact, this is Shruti Sharma. She has done extremely good work. This work has been done by her only. So these are students working in different areas. So total these 10 students working under me at present time, and all these are working in different areas. And recently we have started another area, that is carbon nanotube field effect transistor. Thank you for your kind attention.
Thank you very much, sir, for a wonderful talk. Your talk was audible to the online speakers as well as the offline speakers sitting here in our APJ 11. So the talk is open to the question, but we are running short of time, so we will take only one question. Any questions? Participants can chat, can put his question in the chat box. From here, any questions? So, okay, then if no question, I will again thank Professor S.E. Sharma for his wonderful talk.
Thank you, thank you,
Very much,
thank
sir.
you, thank you, thank you, thank you. One minute.
Next participant.
So I would like to invite Professor Anjana Sarkar to chair the session. Professor Anjana Sarkar has more than 30 years of teaching experience at NSUT. She has published various research papers in SCI journal. Her area of interest are mainly focused on organic, bioorganic, and bioinorganic chemistry. Thank you.
The first speaker is Dr. Mukesh Kumar Garg, and the title of his paper is Startup of Moving Bed Biofilm Reactor for Leachate Treatment. You have 8 minutes.
Good afternoon to all of you. Myself Mukesh Garg. I am research scholar in NSUT West Campus, Civil Engineering Department, also working in NSUT. The topic of my today presentation is startup of moving bed biofilm reactor for leachate treatment. As we all of know that the population is increasing tremendously since last 2 or 3 years, 2 or 3 decades. So there is a problem of generation of solid waste. As per the CPCB report, total solid waste generation is 1.5 lakhs tons per day, out of which 96% is collected and 47% is treated, and 27 of that generated land, that solid waste is dumped on the landfill side on unengineered haphazard manners. Thus, we also find from this report that 25.8% is uncounted this solid waste. So now, as my topic is the startup of the moving bed biofilm reactor for leachate treatment. This leachate comes from the by organic decomposition of the waste. During the organic decomposition of this solid waste, when rainwater percolate into it produces a highly polluted liquid from the landfill site. This is called the leachate. This leachate is highly polluted, which also pollute the groundwater and soil, as well as gives unpleasant odor and have public health hazards also. There are many conventional methods for treatment of the wastewater, like trickling filter, rotating biological filter, ASP, activated sludge process. As ASP is commonly used, but there are certain limitations of these conventional methods. There is the high sludge generation. Due to the high sludge generation, the land area is required more. So these conventional systems are uneconomical. Therefore, for overcome these limitations and limitations or more land requirement, there is one recent or advanced technology is used, that is called MBBR, in which land requirement is less, as well as the sludge generation is less. So it is very much popular choice for treating of the municipal as well as the industrial wastewater. It also uses less energy, also very much efficient for removing of the organic matter, nitrogen and phosphorus. This MBBR technology is a combination of both suspended and the attached biomass, in which wastewater is treated effectively. For suspended and attached biomass, we use the suspended polymer carrier, like a inert material, which have the density similar to the water, that is made of the material HDPE, having the density of 0.9 gram per centimeter cube. The objective of my study is the treatment of the landfill leachate using laboratory scale aerobic MBBR in terms of the COD and BOD, COD and the TSS removal. Apart from this, the objective is to determine the biokinetic coefficient parameters, including sludge growth rate, decay coefficient, and the sludge yield. The methodology used for this treatment, first of all, I have select the landfill site from which
from where we have to collect the leachate. For that purpose, in South Delhi, Okhla landfill site, we have selected because there is the surrounding area of the Okhla landfill is a residential area, so the coming leachate is also polluting the nearby groundwater, and there are other health issues also. So from that landfill site, we collect the leachate. After collection of the leachate, we determine the physiochemical characteristic of the leachate, and after that we make the treatment and getting the results, and we have further shows in conclusion. For the analysis purpose, we have used various methods and equipment for getting the various parameter. For pH, we can directly use pH meter. For TDS measurement purpose, TDS meter, and for TSS gravimetric method by using filter papers. Accordingly, COD and BOD, COD digester, BOD digester. For temperature, we have used in the mesophilic condition. Mesophilic condition means for temperature 30 degree plus minus 2 degree centigrade temperature. For that purpose, in a controlled environment, we have used the thermostat. Dissolved oxygen in the 2 to 4 milligram per liter we have used for that purpose. The physiochemical characteristics we have find out in laboratory from the collected leachate. pH was 8.8, COD was 19,000 to 22,000, total solids were 49,000 to 50,000, TSS total suspended solid 21,000 to 22,000, TDS were 27,000 to 28,000, and BOD was 7,000 to 7,500. As this is a combination, we have already told that this is a combination of the suspended and the biofilter. For that biofilter purpose, we have collect the activated seed sludge from the nearby Delhi Jal Board STP plant, which is located in Dwarka sector D, 20 MGD plant. BSS were find out it was 12.09 gram per liter. Total suspended suspended solid were 15.5, and the ratio of the VSS and TSS was 0.78. It means there was 78% of the organic matter, and remaining 22% were the organic and inorganic. The color was the black. Ma'am, thoda sa please. This is our laboratory setup. For this purpose, we have made this this MBBR reactor having the volume of 24 liter, and the working volume is 21 liter. Parasitic pump is used for continuous flow, and after the sedimentation tank, and for the aeration purpose, we have used this aerator by using the perforated plate, and after collecting the sludge in this sedimentation tank, we get the effluent for which we have made the study further. This is our lab setup. This is our MBBR, this is sedimentation tank, effluent, and the parasitic tank. For MBBR, the volume is 24 and working volume is 21. The media used in this biocarrier is the carbon media of the material SDP, SDP having the length 7 mm, diameter and surface area of 500 square meter, biosphere 800 square meter. For microbial growth kinetics, we have used the Monod equation for the mathematical modeling, Jacobs model. For this mu equal to mu max S upon S plus Ks. For this purpose, we have find out all the parameters I have shown in the further result in the results. We have made the study in the phase manner. For the first phase, we used the glucose 100%, in which the efficiency was BOD and in which the COD and TSS efficiency were measured, which were 95% and 89%. Similarly, for phase 2, we use the 75% glucose and leachate 25%. In phase 3, 50% and 50% glucose and 50% leachate. In phase 4, 75% glucose and 25% leachate. Finally, after 100 days, when we get the pseudo state steady state condition, in that condition we go for the 100% leachate. And finally we get the that the COD removal efficiency were the 84% and the TSS removal efficiency were the 92%. The temporal variation we have shown in the influent, we have taken the COD in the range of 1000 plus minus 20 milligram per liter. And from the phase study, it is very much clear the results. This is very much effective, which reduces the TSS and BOD. Temporal variation for the COD and TSS also shown for the 21 hours HRT from the same. Biokinetics, in the same phase manner, we have shown the results of the same. Is in the first phase, the result of the mu max was 0.2 and K value was 0.35. KD decay coefficient was 0.05, 0.04. It means the microbes were very active or effective. Because their decay coefficient was only maximum, it was the 4.4%. It means biokinetic study of this MBBR is very successful. So this is very efficient and effective method. In the first phase, we used the 100% glucose and the result was the 95% COD and 90% TSS removal. In phase second, it was 75% glucose, 25% leachate, 93% COD and 89%. Similarly, on the in the fifth phase, when we use the 100% leachate, 100% leachate under pseudo steady state condition, the COD removal was 84% and the TSS was 92%. From all phase study, we can conclude that the COD removal was more than 90%, as well as the TSS removal was also 90%. And the biokinetics also shows the growth rate of the biomass were very specific. So finally, we can say this MBBR technique is very simple and efficient. This also having the low footprint and the media having the higher maximum life of 10 to 20 years. So the reactor can be altered to space and required less space. So it is very much useful and economical. Future study scope for further study, we will reduce the HRT, hydraulic retention time, and increasing the organic loading rate by optimizing the reactor for the maximum efficiency and the high organic loading. Further, for post-treatment, we will also carry out the self-synthesized low-cost biochar in the laboratory method, by which we can use this treated wastewater or leachate for the purpose of the for the flushing of the toilets, as well as the for gardening purpose. We can use this. Thank you, ma'am. Sure.
You said that this is a very efficient method, but you are using glucose. Glucose you are using from 100% to 25%.
Normal glucose available in lab?
Powdered form.
Yeah,
Powdered form.
So how it becomes cost effective? Because in order to
Actually, in the phase manner, first phase we use the 100%. Further, we have used 75%, 25% leachate. Our aim is to go for 100% leachate. For survival of microbes, we have used 100%, and in phase manner we are reducing it.
to 25%. But even if you use 25% of glucose, then this leachate is in tons, millions of the tons. So how it becomes cost effective? Have you calculated the cost involved in it?
We will in the laboratory we have make the dilution by as in our reactor for 21 liter working volume we use near about 500 ml of that leachate. For that leachate after
Glucose you use for laboratory experiment?
it was 25 grams.
25 grams. So what is the cost of that 25 grams? Have you calculated as you just estimate? Forget it, this paper. But when you go home, you just estimate.
Okay.
That if you want to treat, say, 1 lakh tons of the
But sir,
how much glucose will be required?
Agreed, sir, but we are not using glucose for real scale purpose. Our aim is to getting the result or efficiency of using the 100% leachate. If our leachate is by using 100% leachate, the microbial growth is coming, so we need not to use that for testing purpose. For using this startup model, we are using glucose for only for the laboratory purpose. Thank you.
You can discuss in those terms as we are running late, sir.
Hello, yes. Our next speaker is Dr. Mimansha Gulati Babbar. Her topic is anaerobic digestion of pharmaceuticals. Acha. Okay, a waste to energy option. Our time is 10 minutes. Please, 8 minutes. And 2 minutes for discussion. 8 minutes, please.
Good evening, one and all. I am Mimansha Gulati Babbar, a PhD scholar of Civil Engineering Department, NSUT West Campus, and I'm here to present on the topic anaerobic digestion of pharmaceutical herbal waste, a waste to energy option. So these are the contents of my presentation. I would like to finish it in 8 minutes. I will try to do that. So these are the contents. I will start with introduction, then we'll move on to aims and objectives, materials and methods, expected impact on academics and industry, infrastructure which is required, results, conclusion and references. So the introduction of my study is that due to poverty and the population explosion, the solid waste is increasing day by day, and to manage that solid waste has become an enormous task. It's a task for us to manage it. And it is in turn creating environmental pollution, solid waste problems, transmission of contamination via food chain, landscape has become ugly, human health are facing issues, and this cannot be stopped because due to the rapid industrialization and commercial growth, the technological advancements, we have higher living standards, we cannot stop exactly the solid waste management. It is only that we can manage, we can treat the waste, we can use, reduce, reuse and recycle the waste, and further we can dispose of it in a very effective manner. So why am I doing this research, identification of the research problem? That a lot of work has been done to manage the solid waste and hazardous waste.
the storage, the collection, transportation, processing, and management of municipal solid waste and hazardous waste. We have seen a lot of research, lot of papers in journals on solid waste. But when we come to the herbal waste, the pharmaceutical herbal waste, there are lot more needs to be done. So India has an enormous gap to fill in this area. That is why I thought of this research problem. So now what is herbal waste? Herbal waste is the waste generated by herbal pharmaceutical industry in manufacturing of pharmaceutical products, and in packing of herbs. Herbal waste is generated, and it is seen that it is not treated and it is directly dumped without doing any pre-treatment. It is dumped or it is landfill, which is creating a lot of problem. So one waste to energy option I have taken out is bioconversion can be done, which can generate a profitable product. Now there are various methods, as we all know, of waste disposal, such as landfill, incineration, waste compaction, biogas generation, composting, and vermicomposting. Now why should we do anaerobic digestion? What is the interest in doing that? So it treats the herbal waste sustainably, produces the renewable source of energy, can help to reduce the greenhouse gas emissions, can reduce the reliance on landfill, and in turn can help save money on energy bills. Now, if you see this flow chart, herbal waste after anaerobic digestion give biogas, which is used for further purposes like cooking, lighting, heating, electricity, and gives digestate, which is again in the form of manure, can be used in agriculture. So now what is anaerobic digestion? It is a natural process that breaks down the organic matter in absence of oxygen and release a gas which is called as biogas. Biogas is primarily what? Methane and carbon dioxide, and may have small amounts of hydrogen sulfide and moisture. Digestate is again a nutrient-rich product, byproduct of an anaerobic digestion, which can be used as fertilizer and soil improver. So it is again a win-win situation if we do the anaerobic digestion of herbal waste. So there are few steps that are involved in anaerobic digestion. There are mainly 4 steps. Number 1 is hydrolysis, which converts the complex organic matter, that is carbohydrate, protein, and lipids, into soluble organic matter, sugars, amino acids, and fatty acids. Next comes acidogenesis, which converts into volatile fatty acids. Then comes acetogenesis, which converts it into hydrogen, carbon dioxide, ammonia, and sulfate. And then last process is methanogenesis, which converts it into methane and carbon dioxide. So these are the 4 steps which are involved in anaerobic digestion. Now, objective of my study. I have told you that why I am doing this, what are the objectives, what are the things I will be doing in this study. The present study has been undertaken with the objective to convert the pharmaceutical herbal waste into biogas through anaerobic digestion process using the batch test study method. Now, we'll be doing the batch test study method, and then characterization of herbal solid waste is being studied in my study. And also I'll be determining the biochemical methane potential, and later on methane gas generation rate constant under varying temperature and carbon-nitrogen ratio. Now these are the materials which I have used. Number 1, the sample which I have used is herbal waste collected from herbal industry located in Haridwar, Uttarakhand in India. Sample comprises of waste produced during the processes or processing of different types of herbal waste. Products like amla, yavni, yeasty, ashwagandha, kamal phool, salpni, satavri, agnamantha, and draksha were used. Now sludge has been taken from a sewage treatment plant which is situated in Dwarka. Now first step was I characterized the feedstock and the substrate. The physicochemical parameters including the COD, the moisture content, VSS, total suspended solids, and pH were assessed. All these physicochemical parameters of herbal waste sample was assessed. Before that, it was dried for 24 hours to decrease the moisture content of the herbal waste. Then the reduction in solid concentration has also been evaluated by the determining physiological parameters after the batch test study. Also, the seed sludge was assessed in the terms of phosphorus, total solids,
volatile suspended solids, TKN, that is total gel-dal nitrogen, and COD. Now sludge is again taken from the treatment plant. These are the parameters. Herbal waste was assessed and sludge sample was assessed on, and these are the equipments. I would not go into the detail. These are the equipments and the methods which were involved in assessing these parameters: the moisture content, pH, COD, total solids, total organic carbon, total gel-dal nitrogen, total phosphorus, and total volatile solids. Now, this is the batch test apparatus and the setup which I used. In this, the temperature was controlled. These are the serum bottles. I'll show you. These are the serum bottles which were filled with the sample, that is the herbal waste, the nutrients, and the inoculum. The temperature was controlled to 35 degree plus minus 2 degrees Celsius because we wanted mesophilic microorganisms to participate, because these are the most efficient microorganisms as they work on the anaerobic digestion of waste. And the inverted glucose bottle were filled with tap water, and also NaOH was added in the water, so that since biogas is the mixture of methane and carbon dioxide, so we want only the methane part. So methane part will be collected and carbon dioxide will be absorbed by NaOH. So this was the whole criteria which was included in. This anaerobic digester is a lab scale digester which we'll be fabricating in our further study. We have not done it yet. The herbal waste will be processed as, okay, I'm just completing. This is one thing which we'll be doing further. We'll be fabricating anaerobic digester. In this, for calculating the COD and everything, the FM ratio, which is very important, food by mass ratio, was fixed as on the methanogenic activity was studied. One objective is, I studied biochemical methane potential, which is BMP, and BMP is what? The methane at STP is converted into grams per methane of COD with the ratio of grams per COD fed, which is called as biochemical methane potential. And also sludge activity was calculated. Now sludge activity is again what? It is a parameter that is generated by multiplying the biochemical methane potential values by food by mass ratio, and this equation can be used. These are the major infrastructures or the inputs we required for our process: serum bottles, furnace, incubator, anaerobic digesters, grinders, glasswares, and chemicals. These are my result. So these are the parameters: COD, total organic carbon, total volatile solids, and pH of all the 10 samples. This is the cumulative methane graph, which shows that initial lag was there in 10 days because microorganisms were trying to acclimatize to the environment. So they were not actually attacking, and digestion process was taking place. And after that, methane degradation, the waste degradation started and methane production started. So these are the sample type with the substrate concentration. The substrate COD was calculated of all the samples. The inoculum concentration and medium concentration was kept as it is written, and the F by M ratio was taken as 0.75. Now, methane maximum value was taken. Again, the stoichiometric value of methane COD was taken. COD fed was taken. BMP was calculated by methane COD and methane COD fed, and then sludge activity was calculated by BMP into food by mass ratio. These are the graphs which I calculated of all the sample type. The observations, I'll be going very fast. The total organic carbon of the waste samples basically lies between 12.59 to 5.3%. The maximum total organic carbon was 12.59, which was observed for Draksha sample, with minimum 5.32% of TOC has estimated in Salpnani sample. The maximum 94% of VSS has been assessed in Yesti and Ashwagandha samples. The lowest 84% of VSS, that is volatile solid, has been observed in Yavani and Kamal Phool samples. The maximum COD concentration has been found in Yavani, and minimum COD concentration has been found in Ashwagandha and Agani Matha samples. The anaerobic biodegradation process ultimately results in the formation of methane and carbon dioxide with new cells as a sludge. After the end of experimental setup, the methane production was calculated by the CH4 COD values. Similarly, the biochemical methane potential has been contemplated as 100% sludge activity. However, the lowest sludge activity was seen of yeast tea. Thank you, ma'am. Thank you. Yes.
Hello.
You have collected the samples.
Yes.
You have not mentioned how much quantity you collected.
Okay, so sir, actually, quantity, I have mentioned the concentration what I used. Acha, okay, sir. Thank you so much.
Excuse me, ma'am.
Hello. The next speaker is Dr. Megha Prajapati. Her topic is waste oil derived carbon quantum dots embedded in nickel cobalt MOF for enhanced supercapacitor performance.
कौन से माइक में बोलना है? ठीक है, ठीक है.
The slides are not changing.
कैसे करो?
हो रहा है.
Good afternoon to all. My name is Megha Prajapati. Today I am presenting my topic, waste oil derived carbon quantum dots embedded in nickel cobalt MOF, that is metal organic framework for enhanced supercapacitor performance in International Conference of Advanced Materials for Emerging Technologies. I am working under the supervision of I am working under the supervision of Professor Shaira Vikant, ma'am. So this will be the content of my slide. I start with the introduction, then introduction of MOF, then I go with waste oil derived carbon quantum dose, then material and characterization. After that, electrochemical measurements. Finally, I conclude. So these are the list of abbreviation I used in my slides. So in recent years, there is immense increase in energy consumption, resulting in depletion of fossil fuels. So the need of hour is to use such renewable and sustainable energy resources like solar and wind energy. And their isolated nature evokes a great demand for energy storage devices. So in this regard, rechargeable batteries has been widely used because they have high energy density, but in spite of their advantageous properties, they have certain limitation like heat generation, which is the common problem in electrical vehicle. Another is low cyclability and low power density. Now comes the supercapacitors. So they are the ultra high capacity capacitor, offer high power density. There is no heat generation take place, which is the common problem in batteries. Also their cyclability is high, but one of the problem is low energy density. So supercapacitors are here to bridge the gap between capacitors and batteries. So that's why I choose the topic supercapacitors. In this regard, metal organic frameworks, abbreviated as MOF, appear as a promising candidate for supercapacitor applications. They are formed by the combination of metal ions and organic linker via coordination bonding. Because of the presence of large number of metal ion and organic linker, more than 20,000 of MOF have been reported and studied within the past decades. They have many advantageous properties which are required for supercapacitor application, like they are having high specific surface area, high porosity, design diversity is there. Also, they are having large surface to volume ratio. But one of the limitation is that they have low conductivity. So in order to remove this limitation, I use waste oil derived carbon quantum dot, which I took from one of the laminates. She derived the carbon quantum dot from waste oil. So they are having very advantageous properties, like they possess large surface area, high conductivity, which I needed for my sample. So combining both the material, I remove the limitation of nickel cobalt MOF, that is low conductivity. In order to synthesize this, I start with the stirring of all the chemicals like nickel chloride. These are the precursor I used. Then after that, thermal reaction was carrying out.
and then finally washing and drying. So these are the morphology of my samples. First two images are for nickel cobalt mauve. They shows the nanosheet-like structures. It means that provide the sufficient accessible sites for my rapid redox reaction. On the other hand, C image shows the quantum dose, which having the size of less than 10 nanometer, which I calculated from images software. So quantum dots are helpful in improving the conductivity and surface roughness. So these are the FTI curve, which I match with the literature. Then after that, confirming the material characterization, I prepare the electrode fabrication. So for this, I start with my prepared material, PVDF, to bind my material, then acetylene black for further conductivity. After this slurry preparation, it's drop casted it on nickel foam, or we can drop cast it on any substrate. After that, vacuum drying, press on hydraulic machine. Then I tested this material on electrochemical testing in 3 electrode configuration. So these are my result. So the black curve is for my nickel cobalt mauve, and for quantum dose, after I doped with quantum dot, surface area increases. Means it is the CV curve, more surface area, more specific capacitance. And it also shows the redox peaks, which having the battery kind of behavior. Next, the GCD curve at 1 ampere per gram. So the nickel composite shows the higher discharging time as compared to nickel cobalt mauve. So my aim is satisfied. Finally, in order to find the conductivity, I did the EIS measurement, and lower RS is found for quantum dots as compared to my pristine sample. So finally, these composite act as a promising material for my supercapacitor applications. So these are the these composite have the highest specific capacitance as compared to pristine sample, shows the lower value of series resistance, and quantum dots helpful in increasing the conductivity of the composite. So this can be a promising method for fabricating high performance supercapacitors. So these are the references. Thank you.
Next speaker, Megha. Sorry, she has already done it. Next speaker is Dr. Pooja Mittal. Her topic is Design and Dimension Analysis of Piezoelectric Based Vibration Cantileverate Low Frequency Energy Harvesting for Pacemaker Application. Are you present, Dr. Pooja Mittal? Okay.
Good evening, everyone. Myself, Pooja Mittal. I am currently pursuing MSc in Electronics from Department of Electronics, South Campus. So today, the topic of the presentation is the design and dimension analysis of piezoelectric-based vibrating cantilever at low frequency energy harvesting for the pacemaker applications. Yes, ma'am. So before going into the topic, first we'll briefly discuss that what is MEMS. So MEMS stands for Micro Electromechanical System. It is a device in which we embed mainly 3 parts: a mechanical part, a microsensor, and a signal conditioning circuit The range of the MEMS devices is generally in the size from few micrometers to few millimeters. So what is energy harvesting? The term energy harvesting refers to the complete process of gathering the minute amount of energy that is available in our ambient environment. So the figure 2 first shows the conventional energy harvesting techniques that we use till the date, like the solar energy, the thermal energy, the windmills, etc. But now the modern day research practice uses the energy harvesting from the ambient low frequency sources like human vibrations. All the human vibrations fall in the range of 5 to 20 hertz. So designing such devices that can harvest electricity at such low frequency can be a better option for the sensors and all the implantable devices that are being used inside the human body. So now going on to discuss what is piezoelectricity. So piezoelectricity is that property of materials that develop an internal electric charge when they are applied to a mechanical stress. So depending on the type of stress or voltage applied to a material, the piezoelectric effect is divided into the two parts, the direct piezoelectric effect and the indirect piezoelectric effect. So the first one is the direct piezoelectric effect, in which a mechanical force is given as the excitation, and corresponding to that a charge is being developed into the material. Conversely comes the indirect piezoelectric effect, in which a charge is applied to the material and a corresponding strain is developed. But here we will work on the direct piezoelectric effect, where we are giving the external frequency and corresponding charge will be developed in the material. So the figure 6 shows the phenomena of the piezoelectric and the reverse piezoelectric effect. In the piezoelectric effect, it is converting stress into the electric charge, and in converse, it is just the opposite, that is the electric field is being converted into the strain. The figure 7, it shows the hysteresis curve of piezoelectricity. So here it is very clear that when we are increasing the electric field, my polarization is also increasing, but when I tend to decrease my electric field, there will be some amount of polarization which will be left in my material, that we call as the remnant polarization. So these are the different energy harvesting structures that are being studied in recent days: the cantilever structure, the cymbal structure, cellular diaphragm, split cantilever, fan folded, and many more structures are also there. But the major research is going on the cantilever structures, because these cantilever structures offer a more amount of strain when applied to a less stress. So what is a cantilever structure? A cantilever structure is a structural element supported at one end and it is being free at the other end. At the one end it is being fixed, and to the other end it will vibrate according to the input frequency. So we have cantilever primary of two types, the unimorph structure and the bimorph structure. In the unimorph structure, there is a single layer of the piezoelectric material and a single mechanical layer. While in the bimorph cantilever, we have two layers of piezoelectric material while a single mechanical layer. So how a cantilever works as an energy harvester? First, we are giving mechanical energy, which is the vibration. So these vibrations are given to this mechanical structure of my cantilever. Now, according to the given input frequency, there will be a corresponding stress or strain developed in my cantilever structure. So since we are using the piezoelectric material, this strain will be converted to an AC pulse energy. But since we are using it for the pacemaker application, there we use a lithium battery, which we all know that works on a DC. So here we need a rectifier that will convert this output AC of the cantilever to a DC output energy. So now, how this energy harvester can be used in the pacemaker? As seen in the figure 3, we can see there are three main components of a pacemaker system: the LEDs, signal conditioning circuit, and battery. I have focused on the third part, which is the battery. We all know that the conventional pacemakers use the lithium battery for their operation, and the maximum life of this lithium battery is generally 7 to 8 years. So if a person who is having an implant of pacemaker at the age of say 10 years and he lives for an average 60 years life, so he has to gone through a surgery for the transplant of the pacemaker for about 5 to 6 times during his life. So if we can replace this battery with such a structure that can harvest energy on its own, then once we implant this pacemaker, then we need not to replace it again and again. So how this is working? Instead of this battery, we use our cantilever structure. There is a rectifier that will convert my output AC to the DC. So how this cantilever is working? This is the electrical circuit. This is my piezoelectric material. This one is the piezoelectric material which will generate AC. This will be converted using a buck boost technology where a level shifting is used in the DC to DC level. Then finally I get a DC output at the DC voltage at the output. So now coming to the design dimensions, these are the original taken design, 21 millimeter length. There is a fixed end, a proof mass with the respective dimensions. Originally the thickness of my cantilever beam was 0.16 millimeter, in which the mechanical layer was of 0.04 mm and two piezoelectric layers of 0.06 mm each. So to understand that how a cantilever works, we can equate it to a simple spring mass damper system. Here we can see this is the equivalent working of my piezoelectric cantilever. This is my mechanical part where we have the dynamic mass M. Here we have the spring constant. This is my damper force, and here I have the electrical part that will convert my mechanical energy into the electrical energy. Just 1 minute left. Okay. So these are the mathematics behind this simple spring mass system. I'll just skip it. So these are the variations that I have tried to done in my cantilever structure by varying its thickness, changing the proof mass dimension, varying the length of the cantilever, the width variation, mechanical and the material variation, and corresponding to each variation we have studied the corresponding changes in the resonant frequency and output power. So this is how the cantilever works. There is a fixed end where I give my input vibrations, and at the other end it is free to move. As it moves, it generates electricity. So these are the result. The figure 21, it shows the length versus resonant frequency of the cantilever. As we increase the length of the cantilever, we get a lower resonant frequency, and this is the only motive of our project, to get a least resonant frequency so that my cantilever can vibrate at the human body vibrations, which are very low, as I said, in the range of 5 Hz to 20 Hz. The second one shows the width versus resonant frequency. So it is clear that the width of the cantilever is not a major factor in determining the resonant frequency. The third curve, it shows the thickness of the resonant frequency. As we increase the thickness of my cantilever, the resonant frequency will also increase. Ma'am, just discussing the last part. So these are the material variations. Here I used, in the first figure, I used PZ85A, which is the lead zirconate titanate as the piezoelectric material, and then I varied the mechanical materials, namely aluminium, copper, brass, platinum, steel and titanium. And similarly, I performed the piezoelectric material by changing it with ZNO, lithium niobate and lithium tantalate. For each different material, I got different responses. So these are the cumulative results. Out of all the combination tested, I got 44 Hz resonant frequency for materials, PZ85A as my piezoelectric, and platinum being used as a mechanical layer. So depending on these two materials, PZT and platinum being selected, I designed 3 different models with some variations in the dimension. And based on all three models, I got the best result for my model 3. The corresponding lens are 25 mm, and for this I got the resonant frequency at 17 hertz. So this is the least frequency with this cantilever design specifically. From 71 hertz we moved to 17 hertz by varying its dimensions and materials. So this is the summary. Firstly, I designed the cantilever with some original dimensions that I mentioned earlier. Then material analysis was done and taking the materials. Finally, I optimized the dimensions. Thank you.
Any questions?
Yes, sir, simulation on the... no, sir, it's simulation on the console software. Yes, sir. Simulation based results. Yes, sir. Sir, actually... Yes, sir. Sir, PZT5A. PZT. Yes, sir. Sir, actually we get a small duration for our project, so... Yes, sir. Sir, I'm in Masters, MSc, final semester. Yes, sir.
Okay, next speaker is Dr. Manjita Priyadarshi. Her topic is Energy Potential Evaluation of Municipal Solid Waste, a batch test study.
Good evening, everyone. I am Manjita Priyadarshi. I am pursuing PhD in Nsut West Campus. My topic is characterization and energy potential evaluation of municipal solid waste. This work is under the supervision of Professor Atar Hussain sir. Okay, ma'am. Just content of my presentation is introduction, second is objective of the study, and third is the material and methods, fourth is result and discussion, and fifth is conclusion and reference. Let's start introduction. Solid waste generation. First, I will discuss about solid waste. Solid waste is a waste. Solid waste as a discarded or unwanted material that is not liquid or not gas. Solid waste generated from industrial, institutional, commercial and electronic waste. As you can see in pie chart, maximum solid waste in Maharashtra 8.1 million ton per year, and comes to West Bengal 5.7 million ton per year, and next is Uttar Pradesh 4.7 million tons per year municipal solid waste generated or solid waste generated, comes to Tamil Nadu 4.3 and Delhi 4.2 million ton per year generated, and last is Andhra Pradesh 4.1 million ton waste generated. Composition of municipal solid waste in India and regional variation. I show in table. Maximum municipal solid waste generated in overall urban India, like 1,30,000 tons per day municipal solid waste generated, and calorific value is 1,751 kilocalorie per kg. Now, solid waste management process. Solid waste management process is important point of discussion. First is the collection, second is the transportation, and last is the final disposal. collection of the solid waste management from various household, building, low-income colonies, door-to-door collection, street sweeping, and kabadiwala. To transport by haul container or stationary container or truck to the stations and dispose to the landfill site or recyclable plant or compost plant. And these are the waste disposal method. First is the landfill, second is incineration, fourth is composting or vermicomposting, and last is the biogas energy generation. Landfill is the most common method of waste disposal, and incineration is a burning of solid waste at a high temperature to generate energy. And composting is a solid waste composting method. Composting is another method of solid waste, and biogas generation is a generation energy generate to energy from by the incineration or pyrolysis at a high temperature. But here the problem, gases, some various gases is releases from the incineration to help to affect the environment and human health and wildlife also. And what is anaerobic digestion or anaerobic digestion process? Anaerobic digestion process is a natural process where organic matter are broken down into the biogas and digested. Biogas is a mixture of methane and carbon dioxide that is used as a renewable energy, and digested is used as a fertilizers. Digested is used as a fertilizers or soil rich byproduct by anaerobic digestion and can be used as a fertilizer and soil improver. Sorry. Why need to evaluate municipal solid waste energy potential? It helps to reduce our reliance on fossil fuel and decreases greenhouse gases emissions. Need to identify opportunity to recover energy from waste, which can offset of cost of waste management and potentially generated revenue. It also can be helpful to practice its diversion from landfills and focus on developing technology to recover energy from its. And overall, it is important steps in developing sustainable waste management systems. Now, coming to objectives of the study. First objective of the study is to evaluate the waste characterization and energy potential of municipal solid waste of Ghaziabad city. And my next objective is anaerobic digestion of municipal solid waste by batch test study under constant food to mass ratio. Now coming to material and methods. Here selected 5 locations for the in the Ghaziabad city. First is the city zone, Mohan Nagar zone, and third is the Vasundhara zone, fourth Vijay Nagar zone, and Kavi Nagar zone. These are mentioned in the figure: Vasundhara zone, Mohan Nagar, City Nagar, Kavi Nagar zone, and Vijay Nagar zone. Sampling method. Sampling method used as a diagonal graph sampling method techniques are opted. The solid waste sample were collected in cubical container of volume 0.011 meter cube. For measuring weighing balance, used capacity of 50 kg. Here some parameter that is determined in the lab: moisture content, pH, volatile suspended solid, total organic carbon, and COD, as they are using apparatus and standard procedures. Next is batch anaerobic digestion. This is the setup of BMP bottle setup. Here mentioned batch bottle, 120 ml batch bottle filled with nutrients and substrate. And second batch bottle is capacity of 500 ml that filled with the NOS pellets. And biochemical methane potential is a biodegradability of any substrate and is determine the monitoring cumulative methane production from a sample. Yes, ma'am. which is anaerobically incubated in the chemically defined media. And now, result and discussion. Physical composition of municipal solid waste in monsoon season and post-monsoon season of Ghaziabad city. Here mention maximum and minimum result of Mohan Nagar and Vasundhara zone. Physical composition of municipal solid waste is a paper, wood, plastic, organic matter, garden trimming, textile and other materials or other components. The maximum composition of so in the table, monsoon season 7,640 gram, and minimum results so in the Mohan Nagar zone in post monsoon season 1,775 gram. And next is the chemical characterization of municipal solid waste collected in monsoon and post monsoon season. Chemical parameters is a pH, conductivity, moisture content, total solid, volatile solid, S, total organic carbon, nitrogen content and carbon to nitrogen ratio. Maximum value is so in the Vasundhara zone is monsoon season 4.7 and minimum results so in the monsoon season Vasundhara zone 4.7 and maximum pH Kabi Nagar zone 7.1. And conductivity is also maximum Kavi Nagar zone but monsoon season. The highest pH value 6.7 and conductivity 4.47 microsiemens per meter has been observed in the sample of Kavi Nagar location during monsoon season. And highest moisture content value of 76.59 and nitrogen content value of 0.80% have been observed in the sample of city zone location. Biomethane potential, energy potential parameter Y maximum in ml its maximum value is so in the Vasundhara zone 132 ml and minimum results so in the Vijayanagar zone 491 ml and methane COD maximum value so in the also Vasundhara zone 2.66 and Vijayanagar zone is minimum gram per liter 1.4 and COD fat is also minimum so in the Vijayanagar zone and maximum city zone. And BMP is as a methane carbon dioxide methane COD 0.705 minimum value so in the Vijayanagar zone and maximum is the 0.955 in Vasundhara zone. Conclusion. The maximum CS production has been observed during post-monsoon due to high amount of organic matter in the waste. The maximum BMP value of 0.95 gram COD to gram COD fat has been evaluated in sample from Vasundhara location. Okay, ma'am. Thank you. Any question?
Okay, thank you. This was the last. I hope this session is over then. Will be having cultural function and after that dinner.
So at last, I would like to invite Professor Ranjana to felicitate Professor Anjana Sarkar with a certificate of appreciation for chairing this session. So the session 3 is completely over. Now it's time for the cultural function. So I would like to invite cultural committee, Dr. Nancy, over to you.
Recording stopped.
इसकी ज़रूरत नहीं है, लीव कर दूँ ना रूम? रिकॉर्डिंग कर दी। Thank you, Dr. Sushmita. Thank you, Professor Anjana Sarkar, for chairing the session. And with this, we have successfully completed the day one of the conference. And since morning, we had amazing presentation, research presentation. We have heard from the eminent speakers. And I can see tired faces now. Everyone is so tired. But I hope no one is hungry as of now, because we have been fed with good lunch and good high tea and then tea. But now, to cheer you up, to refresh you up, we have cultural event. And for the cultural event, we have some students of NSUT who are going to sing some very good songs for us. So these students are the freshers, first year students of BTech of the Crescendo, the Music Society of NSUT. So they will mesmerize you and drive you through the memory lane with their melodious performances. Please welcome them with a round of applause. कहाँ है? अभी तो यही खड़े थे सब. बाहर देखना, बच्चे होंगे, बुला लो. Okay, so now we have students with us, we have team with us. Please welcome them with a round of applause. I'll take their names here. We have Pranav Arora. Students, are you listening to us? Listening to me? Pranav Arora? Pranav Arora kaun hai? So we have Pranav Arora, Mohit Anand. Mohit Anand? Vidyansh Jha, Anmol, Shreyasi, Parth, Prateek, Jasronak, Harsh, Ankush, Swecha. If someone's name is missing, please let us know. Swecha. Swecha. So next 1.5 hours will be given to them, and it's over to you now, and good luck.
I request everyone in the audience to kindly take your seats. Everyone, kindly take your seats. थोड़े डांस के भी गाने होने वाले हैं क्या? डांस के भी गाने होने वाले हैं? ठीक है. Shall we start?
No, ma'am. तो mic से ही नहीं लगे.
अच्छा अच्छा. I request everyone in the audience to kindly take your seats. थोड़ा lights dim कर दे.